trivia last night. And we kick off this morning with tremors, chemical fingerprints, and climates. And our first speaker is Andrea Bryant from the University of Chicago.
Good morning, everyone. All right, so my name is Andrea Bryant. I'm a PhD student at University of Chicago, and today I will talk about investigating the use of long-period seismology to explore Titan's interior. I'm aware that I'm actually quite new to seismology myself, only began a couple years ago, so I will try to do a little bit of background for everyone. All right, so starting with Cassini, we learned a lot about the Saturnian system, but especially for this study, we learned a lot about Titan. And so there's actually a probe, the Huygens probe, that landed on the surface of Titan. And you can, if you go on YouTube, you can Google it or you can YouTube it and see the landing. It's landing through the haze, and you see some water ice pebbles on the surface. There's so much I could say about Titan, but for the sake of time, I'll just say it's an amazing natural astrobiology laboratory. I'm very excited to do some theory about it. Okay, so here is what we currently know about Titan. And so we know that there is a liquid water ocean underneath a very thick shell of ice that's between 50 and 150 kilometers deep. We don't know the exact compositions of this ice shell or the ocean, but we do know that there's water there. And also there could be some high pressure ice underneath the ocean. And this actually has very big astrobiological implications because it could actually act, if there is high pressure ice, it could act as a barrier from the enrichment of the ocean for potential life if it's there. And so, so that's something that seismology can help us to constrain whether or not that's there. Okay, so this brings me to NASA Dragonfly. And so Dragonfly is a rotorcraft that will launch in 2027, and it'll take about 6 years or so to get to Titan. But this instrument will be loaded with many, many different instrument packages that are really, there's a very large focus for astrobio, and in particular the seismometer, which is going to be on the other underside. You can see here it's like dangling, or it's up under the rotorcraft, but it's going to be tethered. It's tethered, and so it'll be lowered down at each location on Titan that's going to visit, and then measure the seismic activity there. And there also are these geophones, which are essentially less sensitive seismometers, and they're a bit smaller. They're going to be, there's two on the underside of the skids. And so, in particular, the seismometer, the geophones, and other instruments within this DragMet package are going to be looking to measure habitability. Okay, so Dragonfly seismology, in a nutshell, will help us to constrain the interior structure of Titan more precisely. And so seismology, similarly like on Earth, has helped us to understand more about the actual interior of Earth to like very great detail. And so we hope to be able to do a bit of the same on Titan. And so some possible causes of Titan quakes will be tidal flexing or cryovolcanoes, and then also like ice cracking events of various kinds. And this is, of course, not a non-exhaustive list. And so we'll be able to put like very precise, more precise, hopefully, measurements on what's actually going on there. Okay, so now this brings me to the namesake of this talk, long-period seismology. I'm talking about, so if you're familiar with seismograms, we have the body waves, so those are the P waves, compressive waves, and the shear waves, S waves. And then we have, later on, we have these surface waves. And so I'm looking, as opposed to using body waves, investigating, and particularly with these, I'm looking at methane clathrate models. What if I were to use the surface wave information, and particularly dispersion information, to be able to try to learn about Titan and maybe about the ice shell thickness. So let's see what I found. Okay, so starting with methane clathrates, for those of you who don't know what that is, so a clathrate is essentially, I like to say a water cage, and so you can see, I don't know if you can see this. This is essentially a structure of water molecules around, and they're entrapping a single molecule, and in the case of, or in the study, the molecule we're looking at would be methane. Okay, so imagine there's this molecule, and now we have tens of kilometers of these methane clathrates, and we think that this could be very possible and very plausible for the Titan conditions. And I think I forgot to mention, Titan surface is 94 Kelvin. So on the surface, methane, we have a hydrological cycle, but it's a methane hydrological cycle. 6% or 5 or 6% of the atmosphere is methane. And so we have, instead of lakes of water, lakes of hydrocarbons and lakes of methane. When we have this liquid methane and ice under Titan temperatures and pressures, they will readily form these methane clathrates, and this has been shown in the laboratory. So it's thought that there most likely will be lots of these methane clathrates on Titan. And so the models that we considered were essentially, they were all the same. So we were looking at 100-kilometer thick ice shell and just varying the clathrate lid thickness. So the clathrates were just at the surface, so hence the clathrate lid. These are all spherically symmetric models. They were generated with an open source code called Planet Profile. If you're interested in generating this, it's on GitHub. Also, I can show you how to get it, or you can just Google it. And there's a ton of other bodies you can look at there as well. And so we simulated a magnitude 3 quake, and then these were the data that we'll be looking at come from a 3-kilometer source depth, so 3 kilometers deep within the ice. Okay, so from this study, this was led by Angela Maruziak, who is now a professor at the University of Arizona. And so we actually saw some small differences in dispersion between two of the models in particular that we were looking at in that paper. So that was the 10-kilometer clathrate lid and the pure water ice shell. And so just as a primer about dispersion, it's related to the material properties of the ice shell, and particularly in the case of elastic waves that we're looking at here. And so this wave speed depends on frequency, and that's kind of like the meat of what dispersion is seeing how this wave speed or the group velocities, they change as a function of frequency. And so we saw like about 2% difference, a 2% difference between the dispersion. So that's looking at this group velocity curve here. It's very small differences, but they're small enough that if you have a really high precision seismometer, you could actually detect that, which is actually, I found that quite intriguing. So I was like, well, let's dig deeper and see what else we can find. So this brings me to the setup of the project of this long period study that I'm leading now. So I take theoretical dispersion curves. So it's all theoretical, but these are extra theoretical, and I can explain what that means later, or if you ask. So theoretical dispersion curves that are generated with a code called Minios, and I'll elaborate on that. And then take these other AxiSim and Sysez, that's another code. So the different methods of doing these things, seismograms to create these mock observational data of which I would go and pick and calculate by hand and with a computer the group velocities for each Titan input model. And I'll show that across a range of distances and frequencies. So now I'll talk about the theoretical group velocities. And so these are looking at group velocity as a function of frequency, so group velocity on the y-axis and frequency on the x-axis, and I'm looking at different modes. So I'll talk about what these group velocities and phase velocities are, or group velocities are, and then what the modes are. So group velocity, if you look on the right-hand side, it's the actual velocity of the wave packet that's encapsulating the bigger, larger scale structure of our seismograms. And the phase velocities, that's another measure of dispersion. It is the actual velocity of the peaks. And so when you have the group velocity not equal to the phase velocity, you know you have a dispersive wave. And so the tonal information, so modes, so if you remember from physics, the wave on a string analogy, or it's not an analogy, but it's the wave on a string representation of modes. The fundamental modes would be here. There's no node. First overtone, one node, second, third, second, and 2 and 3 nodes accordingly or respectively. And then you can go all the way up to, as many nodes and modes as you'd like to. So for this study, we actually looked at up to 3,000 overtones to create an entire seismogram. But here, we know that most of the information of this surface wave that we were looking at, and I forgot to mention that it's a Rayleigh wave, it would normally be in the fundamental mode. But there's a surprise that I'll show you in the next slide. And so essentially what we found was that when we're comparing, when we're looking at the data, and I went and used actually this other data set and took the seismograms themselves and calculated the group velocities as opposed to just them being spit out from a code for me. Consistently that the dispersion profiles, when we look at the different interior structures, they do like differ slightly, but then when we lay them on top of each other, essentially like there's very little differences, and it's so small that we probably would not, and not probably wouldn't, they would be smaller than what we could observe on Titan. And then also these Rayleigh waves, we thought they would be, the information would be in the fundamental mode, but actually it was in the first overtone, which is a little interesting, and it's consistently so that case. So there's this yellow line is the first overtone, and so this blue little cloud thing is the 1 sigma standard deviation from these group velocity measurements, which are taken over a range of distances and frequencies. And so, yeah, it's a pretty strong thing that's happening, or signal that we're seeing for it not being in the fundamental mode. And so then that just shows that this method, we wouldn't be able to use body waves to, the surface wave, this particular surface wave as to diagnose the thickness of Titan's ice shell. So that's intriguing, and so I will dig deeper and see more about that in the future. All right, so a quick summary. I use data-driven models of Titan's interiors to compute Titan synthetic seismograms for comparison to real data that we'll get from Dragonfly in the mid-2030s. And in the study, we investigate energy trapped in the ice shell to determine the structure of Titan and the presence of surface clathrates, and aka long period seismology. And while the surface waves observation that we saw in the study do not clearly determine ice shell thickness, we can constrain it using body wave arrivals, so PNS waves. And if you're interested in learning more about icy ocean seismology, and in particularly about some of the methodology that we were implementing, talk to me, or also consult Simon Stahler's paper. We're looking also at other icy ocean worlds as well. And then understanding the composition of Titan's interior, especially the ice shell and ocean, will have important implications for astrobiology and habitability studies. So thank you so much.
Hi, nice talk. So presumably, like in the lab, we don't have like kilometers of clathrates. So what does it take to extrapolate from just this lab-made amount to how it'll behave when it's this much as a medium?
Yeah, so we used this paper called by Kalasova and Sotan. I think it's in like 2020. But that was, their paper is where we got the actual thermal models to model to model this for the clathrates. Yeah.
Thank you for the talk. I have a question that may be outside of the scope of what you do, but I know that the ice shell thickness can be a proxy for heat loss, and that can also kind of provide clues as to whether the ocean may be like a transient feature, like or a more long-lived feature. Is that anything you can determine using the data that may be collected by Dragonfly or anything like that, or is that outside of the scope of? Because I mean, the longevity of the ocean, like if there is like a liquid water ocean beneath the ice layers, that could have implications in the habitability, whether it's like persisted over geologic timescales.
Yeah, I mean, we can constrain the with seismology, the composition and the depth, but regarding, yeah, it's a little bit outside of my purview.
Okay, I apologize.
No, it's okay, yeah. Good question, though, thank you.
So I'm curious, what is the amount of confidence we have that there's a high pressure ice layer on the bottom instead of, a direct contact with the ocean?
Yeah, I mean, we don't have like any confidence to say. I mean, we think that there could be. I think there's definitely a big camp thinking that there is, but it's highly debatable. So if I were to like look at that diagram, I could put a big, sorry, going way back, there. For the high pressure ice, you could put like a big question mark there because we don't know if it's there. We don't know how thick it is. It's like really deep down. We know there's no molten core in Titan from some Cassini measurements, but high pressure ice, we have zero idea. But it could be there. And so, especially because it's so cold, but then, yeah. And if it is there, there's different scenarios also that if we have porous high pressure ice and it's really saline, and then it could still, we could still have some enrichment of the ocean. So even if it is there, depending on its composition, there could still be enrichment of the ocean. So it may not necessarily be a barrier to life also, if it is there.
Thank you.
Yeah.
Hi, nice talk. I would like to ask you if you had considered the influence of the tidal dissipation in your models.
Oh, wait, so the tidal dissipation? Do I incorporate that?
If you had considered that influence in the generation of Titan quake, sorry.
Yeah.
So have you considered the influence of the tidal dissipation?
No, we're not considering tidal dissipation in the models. We're assuming just a very perfect Titan. But I also don't think we're considering attenuation within the ice shell, but tidal dissipation. We're not really thinking about, I think, and because, I don't think we need to.
Yeah, tidal heating on air provoked earthquakes. If you synthesize the seismic analysis and the influence of the tidal dissipation. So on Titan, I don't know how much is the contribution of the tidal. So that's why I am asking you if you have considered this.
We haven't considered
this parameter in your model. But could be great if you include also to see how much is the contribution of the tidal dissipation for the generation of Titan quakes on your models.
Yeah, I don't know if it has like a huge. So the tidal, I don't think that will have like a large effect, which is why we've left it out. But
yeah,
I think
also
it is worth.
Yeah, also depend of the distance between the Titan and Saturn. So I don't know. That's why I was asking you.
Yeah, thank you so much. Yeah.
Okay, one more question.
So I'm not a planetary geologist, but I do know that one of the limitations for our understanding of the interior of Mars with the InSight mission was that we only had a single seismometer.
Yeah.
In your data, are you modeling basically seismology being measured by a single seismometer? And do you think having multiple seismometers on the surface of Titan would give you further resolution in terms of the thickness of methane clathrate lid? Yeah.
100%. It would be amazing to have multiple seismometers on Mars, also on Titan. But I think just with experimental mission constraints, like they can only have one.
Have you done any modeling to see if you could get further resolution with multiple seismometers?
So it's not really about like getting the resolution with. So we can generate perfect seismograms. It's just how well we'll be able to see and detect things.
I see.
It's easier to like triangulate events and things with when you have multiple seismometers. But yeah, we can. Essentially, if we could see like deeper events if we have more seismometers, we'd have just greater sensitivity overall. But we unfortunately don't have that.
Yeah.
So we have to do what we can with one.
Thank you, Andrea.
Yeah.
So our next speaker is Hector Delgado Diaz from the University of Washington.
Okay. Good morning. Oh God. Good morning, everybody. My name is Hector. I'm going to be talking about the climates of GL 514b. This is a work I've been doing with Rory Barnes from University of Washington and Russell Dietrich and Mario Damaso. To give you an outline, I'm going to first give you an introduction and convince you why we study GL 514b. I'm going to show you what are the factors that we consider that affect habitability. Then I'll show you the methods that we use, and then the results, followed by conclusion and the future works that are deemed important to continue doing. So why study this planet? In 2022, Mario Damaso and his collaborators, they discovered GL 514b. And what's particular about it, it's that it has a high eccentricity. Eccentricity, it's how circular the orbit is. And when it's a high eccentricity, that means that the orbit is kind of like an oval shape. And usually when we study exoplanets, we look for planets that are within the habitable zone. And this planet, because it's very oval shaped, it kind of falls in and out of the habitable zone. So that makes it a particular object to study. It also, as you can see from the properties, it also orbits an M-dwarf star, which is the most abundant star in our galaxy and universe. And with that in mind, when we look at the multiple orbits that could happen in this planet, these are just simulations of what a 0.45 eccentricity orbit would look like. We see that they all go in and out of this green shaded region, which is the habitable zone, that we consider the habitable zone of the star. And the dashed line is just the best fit orbit. We still see it. All of them go through in and out. So that's what makes it very important to study for habitability, since we've never done that before. And another reason why we want to study GL 514b, in this graph I'm showing you here a plot of the eccentricity over the orbital period of the planet. So how long it takes the planet to go around its host star. The size of the bubbles, it shows how much solar installation or how much of radiation from the star is falling into the planet. On the top right corner, you can see the bubble for what would be like an Earth installation, so how much sunlight we receive. The bigger the bubble, the more radiation the planet is receiving. Gray dots represent that we don't have data for the installation, so they don't show any information about that. But in particular, when we look at GL 514b, which is in the middle of this graph on the top side, we see that it's almost unique to it. And when we have an orbital period that long around an M-dwarf, it gives us an idea, a better view to use next generation telescopes, such as ground telescopes, to study them and be able to directly observe them. If the planet is too close to the star, the planet would be really hard to see with direct observation. There's another planet that is really far away. We see it at 250 orbital periods on the right side, but it has a low eccentricity, so that's why we don't care much to study that one. There is a planet with 0.5, greater than 0.5 eccentricity, but it has a shorter orbital period than GL 514b, so it might be really hard to direct observe, and we want a planet that we can study in the future. And with that in mind, the next generation telescopes, such as the extremely large telescope, it will be a telescope that should be able to observe GL 514b. This graph is just showing what is that maximum angular separation that the planet needs in order to be observed, and the planet to star flux ratio, meaning that the bigger planet to star flux ratio, that means we can observe it better. And in the dashed line, that represents the boundary to be observed to the planets that could be observed with the ELT, the Extremely Large Telescope. And we expect that GL 514b will fall within that boundary. So we will plan to use ELT to observe this planet. Now, I hope I convinced you why study GL 514b. So now I want to talk about what are some factors affecting habitability. So there's many factors. When we talk about habitability, there's so many things that we can think of. But we focus on the ones that we've seen that in other papers that have shown that these are the most that affect and impact the habitability. And these are the eccentricity that I mentioned is how oval or circular that orbit is. The obliquity, which is that tilt of the rotation axis from the plane of orbit from the star system. The precession angle is the angle of wobbling of that rotation axis. And the partial pressure of CO2, which is how much CO2 is built up in the atmosphere of the planet. And because it's a 12-minute talk, I don't go into much details as to why them, but those are the papers that we mostly focus that show these are the factors affecting habitability that we want to use for GL514b. We use a software called vPlanet, which is an open source code that has 11 physical processes that simulate habitability for a planet. It includes binary systems, includes the radiation from the star, or disturbances in the orbit, disturbances in the rotation, many others. But the one part that we use from vPlanet is the one called POISE, which is an energy balance model. What it essentially means, this graph is a good explanation. I did not do this graph. Trembet and Fasulu did it. And what in essence, what it is, it's a balance of all the incoming solar radiation that comes to the planet and how much is that it's either absorbed by the planet or reflected back to space. POISE is a cloud-free energy balance model, so that we don't take into account the reflected sunlight by clouds in the atmosphere. So that means that we mostly focus in two parts of the energy balance model, which is how much is absorbed by the surface of the planet. And on the right side, top side, you can see that it says outgoing long wave radiation. How much of that is being radiated by the atmosphere itself in longer wavelengths. In essence, this is the equation that we use to explain it in a easy way. I would say that the first term represents that absorption of the heat from the surface. The second term represents how much is being dissipated throughout the atmosphere, so atmospheric circulation of the heat. The third term just shows the irradiation to space, and all of that should balance to the fourth term, which is how much of incoming solar radiation is falling into the planet. So another thing that POISE does, and this is good to know, is that it's not only an energy balance model, but it also calculates the ice sheets, or how much ice it's flowing around the planet. So is the planet covered in full ice? Is the planet just ice-free, meaning that it's all water? Or is the planet has a combination of polar caps or other types of ice configurations, which we deem important for habitability, since we've seen Earth throughout time has how much the ice has changed in that surface. And another part of the vPlanet that we think of is that outgoing long wave radiation. There are many ways, there are many theories on how do we calculate that, how much of that radiation is being dissipated to space. In vPlanet, there's 3 of them, from Spiegel 2009, Williams and Casting 1997, and North and Coakley 1979. So Spiegel and North and Coakley, those two outgoing long wave radiation, they're just as a function of temperature. And Williams and Casting includes a component of partial pressure of CO2. And we can see in this graph how much of that outgoing long wave radiation over surface temperature, it changes as a function of temperature, but with the difference that Williams and Casting, when we change the partial pressure of CO2, in this case, I'm having a partial pressure of simulating Earth's CO2 abundance in the atmosphere, and we see that it gives a more realistic version of how much of that radiation is being dissipated to space. So that means for our purpose of this study, we use Williams and Casting 1997 model to simulate how much radiation is being dissipated. Yeah. Oh, and to say that this Williams and Casting model is only valid from negative 83.15 degrees Celsius to 86.85 degrees Celsius, meaning that anything that goes, if the planet gets too cold or too hot from those boundaries, that means that our calculations of the outgoing long wave radiation are not exactly accurate. So we deem them as, if it's too cold, that the planet is just completely a snowball. And if it's too hot, we just deem it as a planet completely ice-free. in terms of many other parameters, so we're talking about partial pressure CO2, eccentricity, obliquity, and precession angle. There's other parameters that go into an energy balance model and an ice sheet flow diagram. So here I am just showing you most of the other parameters. Some of them are arbitrary, others are Earth's value. So, as every model, we had to make assumptions, and these are some of the assumptions. For example, the EBM, meaning the energy balance model, we run it seasonally instead of annually. So every season we check that energy balance. We run it for 4 years. So it's run for 4 years, and we run it every 500 years to calculate it. And we use the Williamson-Cassin OLR model, which is outgoing low radiation. The initial global temperature, we use 14.85 degrees Celsius, which represents the pre-industrial Earth's temperature. We have the deposition rate of snow, that's from Earth's value, and then the heat capacity of the land, of the water, and the albedos, they all come also from Earth's value. Now the land fraction, it's analogous, it's similar to Earth's. So we use a 25% land, and the 75% is just water cover. It's covered by water. To do our simulations, we divided it into 4 simulations. We first wanted to find values of CO2, eccentricity, obliquity, and precession angle that meet the Philae protocol. I'll explain to you what the Philae protocol is. The second simulation, we studied the latitudinal temperature for various eccentricities. The third one, we did a parameter sweep of eccentricity and obliquities. And the fourth one, we did a parameter sweep of CO2 and obliquity. All of this, we run all the simulations for 1 million years, and I did a total of 960 simulations. Why 960? Just because, no specific reason. And all of these are just static simulations, meaning that the obliquity, eccentricity, and precession angle of the planet are not evolving over time. So that means that for future work, just spoiler, we want to do a dynamic evolution of how we see this eccentricity, obliquity, and precession angle evolve, because we see that on Earth. We see those values changes. For the first one, the Philae protocol is just the functionality of ice latitudinal EBM tenacity. It's a protocol and intercomparison project from the Cuisines project. And what they want is to do an intercomparison of different EBMs. And the first benchmark case is to achieve global mean surface of 288 kelvins. And that's what we did. And we looked for what are those values. And we found many possibilities, but this one I'm showing you here is just the eccentricity of 0.45, an obliquity of 3 degrees, a precession angle of 90 degrees, and a partial pressure of CO2 of 7 bars. We notice that 7 bar CO2 is the one that gives the most stable climates throughout the different bars, partial pressure of CO2. In here, I'm just showing you how in the first panel is the insolation is being received per latitude. On the top right panel is the surface temperature, how it varies. On the bottom left is the ice mass balance, meaning that a clear color, ice is being deposited, dark color, ice is being lost. And on the right, we have the outgoing long-wave radiation. And what we see is that all of this correlates, so we have a validation of our code that it's working as it should. So that's why we wanted to do this as our first simulation. We're just trying to do kind of like a sanity check for our code. We then did a study of latitudinal temperature for various eccentricities. And here I'm just showing, remember that eccentricity is 0.45. But if we look at the error value of their calculation, is plus minus 0.15 to 0.14. So if we want to study this to 3 sigma confidence, that means we had to do a range of 0.03 eccentricity to 0.9 eccentricity. So that's what I'm showing here, how the different temperatures of the planet vary through the 1 million year calculation. On the top one, it looks weird. Yes, it is weird, and it's because the simulation gets too cold, and it goes out of boundary for our simulation of the Williamson-Cassin. So that means that the planet is just really cold, and it doesn't get to run anymore because it just fell out of the boundaries. So for that one, the planet falls out of boundaries, a snowball state. The second one, we get a global mean surface temperature of 26 degrees. So it's really hot, meaning it's an ice-free state. And for the last one, we have a 0.9 eccentricity, but the planet gets too close to the star at the beginning. So it's so hot that it's just fall out of boundaries from the other side. However, because the planet eccentricity is so long, that means its winters are very long. So when we were able to lower the eccentricity so that the code could run, we see that the global mean temperature is about 6 degrees. So it's not that warm. So we get a snowball state, even though it's a global temperature of 6 degrees. Simulation 3, and I'm almost done. This is just a parameter sweep of eccentricities and obliquities, how those eccentricity and obliquity affects the state of the planet. We see ice free is the dark blue, snowball will be the gray part, purple is the polar ice caps, and the outer boundaries is the region whether it's too hot or too cold. And we see that at least polar ice caps are formed. This is important because Earth has ice caps, so that's what we're trying to achieve if we can see ice caps in the planet. So this shows that for different eccentricity and obliquity, that happens. And we look at the global mean temperature for those different eccentricities and obliquities, and we get a 14.85 degrees Celsius at an eccentricity of 0.4 to 0.5, regardless of the obliquity. So we get kind of like a stable climate, regardless of obliquity for different eccentricities. Lastly, we did a parameter sweep of this time, instead of changing eccentricity, we changed the CO2. And we also see that polar ice caps are formed. And on the right side, we see that how many of those simulations are either polar caps, ice-free, or snowball. And we see that a lot of them are ice-free and snowball. There's very little of polar caps, but there is still a glimmer of hope because they still form. So that's a good thing that happens. And then I'll leave you to the conclusions. So I just want to cut it there. But in essence, we did find temperature conditions that can give a temperate climate, such as pre-industrial Earth. 7 bar CO2 would suggest that is the most stable one to create those polar ice caps. Most of the planet states are found in either ice ball or snowball, and precession angle does not impact much the ice state of the planet. And we don't need direct observations to assess the habitability of GL514b. And I'll leave it there. Thank you.
Thank you, Hector. So we have time for one quick question.
Great talk. So it seems like you're suggesting that a snowball state is a permanent state, and I'm curious as to whether or not your simulations show any deviation from that, because we know that that's a state that has been in flux on our planet. So I wonder if your simulations can account for coming out of a snowball state.
Yeah, so at least the simulation, what it's showing is that what I'm showing here on this histogram plot is the last state at the end of the simulation. But papers have shown that 1 million years is a good enough time for simulations for climates to stabilize. The thing is that because we're doing a static evolution, we don't expect it to change. But if we add the dynamic part, which is like changing in obliquity and eccentricity and precession angle while we're evolving the planet, then that could change. And it could have been like a snowball state at one point and then change to something else. But for the static ones, we're not expecting this to change since there's not much fluxes. Yeah. I think that's it. Yeah.
Okay, our next speaker is Evelyn MacDonald from the University of Toronto.
Thank you. Can everyone hear me? Excellent. All right. Hi, I'm Evelyn. I'm a PhD candidate at the University of Toronto, and I'd like to talk about some simulation work that I've been doing with my collaborators there, funded by NSERC. So I work on M-Earths, which, for the purposes of this talk, I'm defining as roughly Earth-sized rocky planets in the habitable zone of an M-dwarf star. And so because the star is small, the planet is close to the star, so we assume it's tidally locked. So this diagram over here just kind of shows what that looks like. So we have the star somewhere over here, light from the star hitting the planet at the substellar point, which is always at the same place because the planet has a permanent day and night side. And the terminator is kind of a cool word for the dividing line between the day side and the night side. So just kind of keep that in mind. I'll be using some of these terms. Now, the base assumption is that these planets have what we call an eyeball climate. So again, we have the star here. The assumption is that the night side is frozen and part of the day side is unfrozen near the substellar point where it receives the most radiation. And you would assume that's a circle. This is actually an oversimplification, but it's kind of a good starting point. So I have a few questions that I'd like to be trying to answer today. First of all, how does land configuration affect M-Earth climates? How does the mass of the atmosphere affect their climates? I'll be answering those using a 3D GCM general circulation model called exoplasm. And then the next part is, can we tell these climates apart in observations? I'll be using a radiative transfer model based on my exoplasm simulations to look into that. So to start, I'd like to talk about land configuration. So if you recall the eyeball climate, we kind of have a cartoon of this here. The idea is what happens if we put land in that warm, deglaciated region, because that's the region that's probably the most interesting. But what's going on the surface there should have a climate effect, presumably. So I've done this in a systematic way, as I'm showing over here. Basically, we have two opposite continent configurations where either all of the land is in a circle at the substellar point, so that's the substellar continent over here, with ocean everywhere else, and if the ocean is cold, there's ice instead of open water. And then the opposite, substellar ocean, putting land everywhere except for a circle at the substellar point where there's water. And we vary the size of the circle in all of these simulations, going from 0 to 100%. So here you can see that sometimes there's ice-free ocean and sometimes there's not. And these ones, there's always some ice-free ocean because of where the water is. So now what happens to the climate when we run the climate model with these? There's a lot going on here, so let's just take it slowly. On the left here, we have substellar continent models with different land fractions. So this first column is the land map, just looking straight down at the center of the day side with the night side not shown. And the second column here shows the precipitation and evaporation. So red is evaporation, blue is precipitation. You'll notice it always rains at the substellar point, and water evaporates from the ocean everywhere else on the day side. And this is true for these substellar ocean models as well. You get clouds and precipitation in the middle of the day side and over ocean, regardless of where the land is. So the water comes toward the center of the planet where it's warmest, rises, it condenses out, and you get rain. So we also get kind of a range of temperatures depending on how much land there is, with high land fraction planets having hot and dry day sides, which is what's shown in this column here. So these are some pretty significant climate differences, like on a spatially resolved level. This is what this looks like globally. On the x-axis, we have dayside land fraction, so the size of the circle for these two land map types. And on the y-axis, we have temperature on the left and water vapor on the right. You'll notice that there's the largest discrepancy between the two at partial dayside land cover. So when it's not an aquaplanet or a land planet, somewhere in between, it really matters a lot where the land is, because that influences the amount of ice-free ocean that's available on the planet for evaporation and putting moisture into the atmosphere. And these curves kind of follow each other. So this is already a climate uncertainty that we need to kind of think about. Now let's make it more complicated by changing another parameter, the mass of the atmosphere. So like land configuration, that's not necessarily something we can know about a planet in advance. So I varied it in my simulations. The idea is basically make the atmosphere thicker or smaller. That's what I've tried to show over here. And these are the same curves that were on the previous slide, but this time for a range of pressures. So increasing the amount of N2 in the atmosphere. And again, you get the same land fraction and land configuration dependence, but in addition to that, the curves are shifted up or down depending on the pressure. So they overlap. It's very confusing. There's clearly some climate effects here that need to be paid attention to. And so then the next thing we want to know is, can we ever know this stuff? Can we tell these apart in observations? So the way these planets will be observed is with transit spectroscopy, which is what JWST will do. I have a kind of image of what that looks like. Basically, when the planet passes between the observer and the star, it blocks out some of the star's light, which is measurable. And there's a wavelength-dependent contribution to the amount of light blocked, depending on the molecules in the atmosphere and where they scatter and absorb. So based on what wavelengths block the most light, we can tell what's in the atmosphere. This is really hard to do for small planets, but this is like the theory of it. So the question then, because most of the water, if you'll recall, was at the substellar point, is how much water is making it to the terminator, because the terminator, the terminator is where we're getting the photons from. We can't directly image the substellar point, so we're getting the light passing through the terminator. So I have some profiles here of specific humidity for the two different types of land map. This is just all at the same pressure. Basically, we have pressures, so going upward in the atmosphere on the y-axis, and specific humidity on the x-axis for near the substellar point and near the terminator. So looking for a relationship between the amount of water in the rainy zone and the amount of water we can see. Substellar ocean models all look pretty much the same, which makes sense. There's water there. There's a bit less at the terminator, but it's still there. For the substellar continent models, the ones with a lot of land have much less water at the terminator, but still some. So maybe we can tell the difference. So now I'd like to show some synthetic transit spectra I've made using only water. So I've ignored all other possible things that could contribute to this. So on the x-axis, we have wavelength that the instrument is observing at. And on the y-axis, we have what I've defined as amplitude. So basically the difference between the transit depth that you get, so the amount of light blocked from the star, and the minimum amount. So either the amount just by the rocky planet itself, or the lowest cloud deck, or the lowest part that would be visible. Because it's really this difference that we're looking to measure, more so than the actual size of the planet itself. So these are just for a few selected simulations from my parameter space. And so varying only the land and the pressure, we get quite a sizable difference in these water vapor spectral features. So these are kind of a range of what a specific planet might produce. And then on the bottom, we have the cloudy version. So these same ones, but with clouds included in the radiative transfer. And you'll notice that the features are smaller, but also they're not all affected the same way, depending on where, like how many clouds are at the terminator, which varies depending on different factors. So it's a bit confusing. I'd like to just focus on this feature though. So I'd like to show basically the top of this feature for a variety of models. And that's what this looks like. On the left, we have the cloud-free version. On the right, we have with clouds included. Again, these curves kind of follow the same shape as the temperature and water vapor from a few slides ago. But when you add clouds, it gets a lot worse, unfortunately. Basically, there's some correlations in the cloud-free version. These high-pressure, low-land models have much taller spectral features, so you might be able to detect that or tell the difference. But then when we add clouds, what happens is that these models with the most water vapor are also the cloudiest at the terminator, and consequently, the effect of clouds on the spectrum is much higher. So it gets artificially subdued. So it looks like these dry models over here have the most water, but that's not actually true. So observing this, it's going to be very hard to tell what's going on the surface of the planet. Just try to end on a happy note. There's a huge range of climates here. We can't necessarily tell them apart, but a lot of them could be habitable, and we might be able to detect water in some of them. So, I'm still cautiously optimistic, I guess, but it's more important, I think, to account for the fact that there are these unknowns instead of just trying to make assumptions about what's going on the surface of the planet based on its transit spectrum. I'll stop here, and I'm happy to take any questions.
Hi, great talk. Really interesting stuff. So I'm wondering about, you have these simulated transit spectra, and it looks a little pessimistic based on how close those lines are. But JWST has been delivering some exquisitely precise spectra. So I'm wondering if you have plans to model like the noise properties and stuff, and like actually simulate JWST observations of these kind of things to see if you can actually distinguish maybe a few things, because the transit spectra are so precise because of this incredible instrument that we have.
Yeah, it would be good to add some instrumental noise to them. It's also really hard to do that accurately. There's like, it's harder to get precise spectra for these smaller stars. Like most of what's been coming so far is, or sorry, smaller planets. Bigger planets are easier to get like good data from. But yeah, there's more photon noise in the far or mid-infrared compared to the near-infrared, so I think it'd be good to focus on that. But yeah, it would be, like it might be possible to tell some of them apart, but it would be a good thing to look into. Thanks for the question.
Taylor Plattner at Georgia Tech. Great talk. Also, just wanted to say all the other talks were very interesting this morning and super cool. I used to do exoplanet stuff when I was an undergrad, so you're taking me back to, I guess, my old days. Sounds like I'm an old person. But I had a question on, I know you're doing simulations, but are you going to eventually like look at specific planets? And if so, do you have like I don't know, there's kind of like, I used to do this like development of like a prototype instrument to put on ground-based telescope to like vet out interesting planets. So I didn't know if you had like I don't know, anything to like vet out interesting planets to you, like with JWST or with any other like telescope. Sorry if that's a terrible question, but just curious.
No, it's an interesting point. I'm not an observer. I'm mostly just waiting excitedly for other people to get data. I'm like, I would say the one I'm most excited about is probably TRAPPIST-1e, but excited and apprehensive at the same time because it'll be really sad if they don't find an atmosphere on it. But yeah, ground-based observations would be like another good way to look at these planets because you can get such a bigger telescope.
Okay,
Yeah.
just with JWST, how often is it like looking at, like if you had some planet that you're really interested in, how often is it like looking at that planet, or would you like, I don't know, I know TESS was another one that people like were really excited about, so I didn't know if that was easier to like get data, like to see that same planet more.
Yeah.
And I know, yeah, like you were saying, it's not as great. Everybody loves JWST for a reason.
Yeah, well, TESS is a planet finder, so it's found a bunch of candidates. So like anything that starts with TOI, I mean TESS object of interest, is what they're called. And then JWST is kind of needed, or it's like some large telescope is needed for follow-up to actually characterize their atmospheres, because it's much easier to find the planets than to see what's in their atmospheres, especially with such thin ones. Did that answer the question?
Yeah, yeah. Good talk, thank you.
Thank you so much.
Okay, we have time for one quick question.
Hi, that was also super. I'm pretty far removed from this exoplanet stuff. This is sick. So I have a question that I apologize for my inability to ask a more specific question about your work. That's just a lack of my understanding. But I'm curious that they were talking about how like this exquisite precision with JWST and all this stuff. And so how far off? Well, I'll preface by saying the past couple of decades, as I'm sure you're aware, our understanding of planetary habitability has really shifted with our increased understanding of these icy moons in our solar system and things like that. How far off is our ability to examine moons of exoplanets, given like a small enough star or something like that? Or is that just like so far off from reality given their technological abilities at the moment?
I would say it's far off.
Unfortunate.
Like, yeah, the problem is that you have to like detect the planet and then the moon going around the planet, and they're just really hard to find, and they'll be even harder to observe, which is unfortunate because I bet exomoons are really cool. And that would also deal with the tidal locking problem. Like if an exomoon was orbiting its tidally locked planet, the moon will not be tidally locked to the star, so it could have day-night cycles, but they're just really hard to observe. But yeah, thanks for that. That would be really cool. All right.
Thank you for the talk, Evan.
Well, thank you.
Okay, our next speaker is Zachary Fred from MIT.
Hello, can everyone hear me? So my name's Zach, and I'm really excited today to present on some of the work I've done so far during my PhD, which is mostly looking into machine learning of the chemical inventory and rare isotope logs of the protostellar source IRAS, excuse me, 16293-2422b. So first of all, let me give just a very high-level overview of what supervised machine learning for regression is. So the overall goal in this process is to learn a set of model parameters that can be best used to map some input features, some x values, to some relevant properties, some y values. Just the simplest and oversimplified possible example of this process is just 2D linear regression, something that could be modeled by y equals mx plus b. And what you do in this process is you provide the model with training data in the form of x-y pairs, and what it does is it learns the model parameters, in this case the m and the b, that can best map those inputs to those outputs in a way that minimizes some sort of loss function. And while this is a very oversimplified view of this whole approach, it can also be very effective for high-dimensional inputs and also include very complex nonlinear models as well. So now getting into the problem that I'm trying to tackle with this approach. So the overarching goal behind most of the work I've done so far is suggesting likely molecular candidates for detection in various regions of space. So let's first take a step back and ask the question, why do we even care about interstellar molecules? So because we're looking all the way out in space, we're not fortunate to be able to throw a thermometer in a reaction beaker, easily observe some sort of physical change during a reaction. Instead, in order to trace the physical properties and evolutionary history of interstellar sources, we oftentimes rely on the molecules that we detect along with the properties of said molecules. And just a couple of examples, D to H ratios provide information about the temperatures of the environment during molecular formation, and the detection of SIO can trace things like stellar outflows or shocks. So in the past, if we wanted to model molecular abundances and use this to predict new molecules for detection, we relied heavily on astrochemical models. And these, as can be seen on the screen, are vast networks of interconnected reactions, each reaction having its own rate constant, and ultimately, they can be used to derive the time-dependent molecular abundances of these species. And while these are excellent tools to gauge our current understanding of the specific chemical processes in space, there's a couple of drawbacks. First of all, in order to add a new molecule or reaction to the network, we oftentimes rely very heavily on chemical intuition. Additionally, the rate constants that are inputted into the networks are oftentimes either extrapolated or approximated, and the uncertainty that comes along with this when you propagate it through the whole network can result in some very uncertain or inaccurate modeled abundances. And finally, it's just difficult to include new molecules. In order to add a new molecule to the network, you have to include every single reaction that could create the molecule, as well as every one that could subsequently destroy it. So that's a difficult and oftentimes inefficient process. So in response to these predictive shortcomings, a previous postdoc in our group, Dr. Kelvin Lee, developed a machine learning method that's able to predict and model molecular abundances in space without requiring these complete networks. And instead, molecular abundances are expressed purely in terms of a chemical vector space. So in this process, the first step is you need to collect telescope data toward a specific interstellar source. From this line survey, you'll be able to decipher which molecules are present, along with the abundances or column densities of said molecules. Following this, for any machine learning application, you need to vectorize your input. So we have to make molecular feature vectors out of the molecules we're detecting. To do this, we utilize the mol-to-vec algorithm, which is an unsupervised algorithm that creates context-aware substructure vector representations that can be subsequently summed to form molecular feature vectors. So at this point, we have our molecular feature vectors, our inputs, as well as our relevant column densities, our outputs. And what we do, as mentioned previously, we input this into a machine learning model that learns the best way, the model parameters, to map those molecular features to the relevant column densities. And this is just a figure from the initial paper. And what it shows is that a very simple, regularized linear regression machine learning method, a ridge regression model, is able to far outcompete even the state-of-the-art Gotham Nautilus astrochemical model in reproducing and predicting the chemical abundances in the TMC1 dark molecular cloud. So while Kelvin's initial work was a fantastic proof of concept that this method can, in fact, effectively model and predict molecular abundances in space, there's a number of things that just remain simply untested. First of all, it's untested outside of dark molecular clouds. So the initial work was focused on the TMC1 dark molecular cloud chemical inventory, and this is a very cold and quiescent region of interstellar space. So we also want to ensure that these same methods can also apply to warmer, more turbulent protostellar sources. And for this, we looked at the class 0 protostellar binary, IRAS 16293b. This is an especially attractive source because it has a very dense molecular line survey, and it's been studied extensively with interferometric data. It's also vital that we can model the abundances in both these cold, dark clouds and the warmer protostellar sources, because understanding the chemical inventories of these two different sources allows us to investigate how the chemistry actually evolves as a star is forming. Additionally, in part due to the shortcomings of the mol-to-vec algorithm, there were initially no isotopologues included in the data set. However, IRAS 16293b consistently shows very high levels of isotopic substitution. As a result, in order to fill out the data set, we felt the need to include these molecules. Additionally, as mentioned previously, isotopologues provide information about the temperatures and timescales of molecular formation in space, and therefore being able to model these ratios effectively with this machine learning method would provide a straightforward and efficient way to gain additional astrochemical insight. So in order to include these isotopologues, we added hand-picked isotopologue descriptors at the end of our mol-to-vec representations, and more specifically, we added 19 extra vector dimensions that denoted which specific minor isotopes are substituted into the molecule, along with the chemical environment of said isotopic substitution. So just as an example, 3 of the vector dimensions denote whether the 13 carbon is sp, sp2, or sp3 hybridized, and we chose this feature because, as you can see, it has a notable impact on the mean 12C to 13C ratio of the molecules in this source. So now getting into some results, we trained both a Gaussian process regression and Bayesian ridge regression model to map the molecular features of the column densities. And what we were ultimately able to see is that the models are able to both effectively model the molecules provided to it in the training set, but also extrapolate quite well to yet unseen molecules in the testing set. Additionally, because we included isotopologues in our data set, we wanted to see how well these models are able to reproduce the column densities and isotopic ratios of the molecules in this source. So what you can see on the top row of the deuterium and 13C substituted isotopologues, using 5-fold cross-validation, the column densities are very accurately modeled. Once you extrapolate this out to actual isotopic ratio predictions, these are much more sensitive to small changes in column densities. As a result, a small error in the column density prediction can result in a large isotopic ratio error. So the bottom row of actual isotopic ratios is slightly less precise. However, just because of how nuanced the process of isotopic fractionation is in space and how simple our encoding is, we're very encouraged by these results that we're able to very accurately model the column densities of these isotopically substituted species. So as mentioned previously, due to the strong performance on the testing set, we have some sort of confidence that these models can extrapolate to yet unseen species. And as a result, we proceeded to input about 90,000 astrochemically relevant molecules into the trained models to see which undetected species are likely the most abundant in this source. And on the bar chart on the screen, you can see the top 10 predicted abundance molecules toward IRAS 16293b, and there's two things to point out here. First of all, 3 of these molecules, namely hydrogen peroxide, ethane, and carbon dioxide, have all been previously detected in different regions of space. Additionally, something you may notice in the bar chart is that many of these molecules are very oxygenated and fairly saturated hydrocarbons, and this is also a good sign because when looking at the actual chemical inventory of these sources, or this specific source, the most abundant detected molecules are also these very oxygenated hydrocarbons. So not only is it learning to predict known interstellar molecules, but at the same time, it's narrowing down to the correct region of chemical space relevant to this source. So as I mentioned, these 10 molecules have not been previously detected in this source, and the reason for that in many cases is just simply a lack of rotational spectra being taken in the lab. So now, next steps is we want to take that next step forward and collect the rotational spectra of some of these predicted high abundance molecules so that they can be searched for in these protostellar sources. One of particular interest is circled on the screen, methoxyethanol, and methoxyethanol is in the same chemical family as both methoxymethanol and methoxyethane, which have been detected in high abundance toward IRAS 16293b. But not only is this molecule chemically similar to several that have been seen before, but we also have some sort of mechanistic reason to believe it may be present. So methoxymethanol has been shown to form via reaction of the CH3O, the methoxy radical, with CH2OH on grain surfaces. So the high abundance of methoxymethanol also suggests that in the prestellar phase of the source, that the methoxy radical was highly abundant on these grain surfaces. As a result, it could feasibly react with the other high abundance organic radicals in this source, and we therefore believe that the methoxylated versions of these high abundance organics in this source may be strong targets for astrochemical study. So next step is to use chirp pulse Fourier transform microwave spectroscopy to study the rotational spectrum of this molecule, subsequently use the laboratory spectrum to search for this molecule in various protostellar sources, and upon its detection, learn more about the chemistry of this highly abundant methoxy radical. So that's all the work I've done so far, as well as what I'm working towards. I'd like to say a big thank you to my group shown on the screen. The picture on the right is us in the Green Bank Telescope, which is a very cool experience. I definitely recommend if you have the opportunity to travel there. But thank you for listening, and I'd be happy to take any questions you may have.
Thank you, Zachary. So we are running a little behind, so I suggest we use the break, and you can find Zachary in the break room to ask questions. And we'll meet again at 10:30 for the IC World session.
Hey. Oh, thank you. Thank you, appreciate it. first speaker will be Sarah Miller from Cornell University.
Thank you. So yeah, I'm Sarah Miller. I'm working with Professor Brittany Schmidt at Cornell University. And I am working to build a global circulation model for the ocean at Europa. So before we move on, I wanted to kind of point out the cover image I chose, which is primarily because I thought the colors made for a pretty PowerPoint theme, and secondarily because it shows some interesting kind of structures that exist on the ice crust on Europa. So as you can see, it's not a smooth ice skating rink. It's a very interesting and geologically active zone, which hints that probably the interior is a dynamic and very interesting place to study, which is what I'm going to talk about next. Before I dive into the science, I do want to take a moment to thank my team and kind of the people who have helped me bring my understanding in this field up. So I have a background in fluid dynamics and aerospace engineering, which I'll talk a little bit about throughout this talk. But these people have been really instrumental in kind of working with me on the planetary aspect, as well as my funding sources through an NSF GRFP and a NASA Finest and an Amelia Earhart Fellowship, and some wonderful people who support this work. Okay, so as I mentioned, Europa has a very interesting surface, and it hints that there is a dynamic ocean interior. And I think that the ocean circulation, the physical oceanography piece of this puzzle, is a really interesting one in terms of habitability, because when we look at Earth's ocean, the transport of heat and salt and nutrients throughout the ocean column is really what sustains our biosphere. So I think it has really interesting habitability implications on other planets as well. And specifically, I want to narrow this down even further. The region of our ocean that separates the glacially covered parts of our ocean from the liquid layer, that ice-ocean boundary layer, is really instrumental in setting far-field ocean properties. So that tiny boundary layer region between the ice and the ocean actually has an outsized effect on affecting global mass, water mass transport. And so I think that's very much worthy of intense study in the modeling realm for Europa. So I'm not the first person to attempt to build a global circulation model for Europa, but the state of the field is really kind of divergent. So models of Europa generally fall into one of two categories, depending on kind of how you set your boundary conditions and really how you set up this ice-ocean interface mathematically. So usually there's kind of an outsized effect of either the rotation-driven or buoyancy-driven, so kind of temperature salinity gradients in the model, and the results are very different. So global circulation models exist. They usually fall into one of these two categories, and they do not agree with each other. Now, if we look at terrestrial ocean models, on the other hand, they look very different, and that's because they've had a lot more scientific manpower and years of study and actual data, so how nice for them. So their models are very sophisticated compared to what we see in planetary ocean models. That being said, there are still kind of parts of Earth's ocean that we don't understand. So it's very much, ocean modeling is an active area of research, and there are still some mechanisms that remain poorly constrained, which is really humbling to think about doing this on a body that we have zero data for and know a lot less about. But I'm going to try anyway. So let me introduce you to the tool that I'm using. So I'm using the MIT General Circulation Model. So it's a 3D circulation model that employs the full non-hydrostatic incompressible Navier-Stokes equations. It also has some really interesting and very useful packages for Europa. So an ice shelf package, a deep convection package, which is really helpful because Europa, unlike Earth, has a really deep ocean compared to its planetary radius. And that is important when you're talking about large-scale flow features. So I won't kind of dive into the nitty-gritty. It's written in Fortran. So if you're a modeler, you probably just cringed. But yeah, it's a very powerful, very useful tool. So there's lots of knobs that you can turn within this model. And I'm working on turning kind of all of these through sensitivity studies throughout my PhD. But what I want to focus on in this talk is the role of topography underneath the ice shelf. So in this case, I'm talking about both the small-scale topography, so surface roughness of the ice, which affects things like turbulence in the boundary layer, as well as large-scale features on the ice that can form large-scale flow features. Now, you might be thinking, like, why would a turbulent boundary layer affect global ocean circulation, and specifically habitability for this interest? And I want you to remember that the ocean timescales operate a lot faster than planetary timescales, and that could be an important link for a habitability argument. So a quick review of kind of boundary layer physics. I took out the full equations because they're pretty ugly, and I just have these like nice kind of simplified relationships that I want to discuss. So I'm using kind of a widely adopted parameterization called the 3-equation parameterization. It's very creatively named. And essentially, it's just looking at the fluxes, those are those Q values, between a solid ice shelf, which is freshwater or fresh ice, a mixed boundary layer region, and then the mixed layer, the liquid ocean. So we're looking at kind of the 3 unknowns in these equations are the temperature and salinity of the boundary layer, as well as a melt rate, or m dot, which is negative if it's melting, positive if it's freezing. And that's kind of how we're constraining the phase change that's happening at this region. So I'm using a model that's kind of an ongoing international effort within the MIT GCM community to model this kind of physics for Earth's ocean. And so this is a simplified version of that math. So it's a 2-equation parameterization that's assuming the salinity of the boundary layer and the mixed layer is the same. Current research and kind of more recent results since submitting this abstract, I've been able to like use the 3-equation parameterization, but those graphs are still pretty ugly. So maybe next AbGradCon. Yeah, and kind of one other thing that's very common on Earth, but not a great approximation for Europa, is that often in ocean models, the pressure dependence of density is approximated by depth dependence. I mentioned that Europa's ocean is a lot deeper than Earth's, so this is something that I've removed as well, because I think no longer holds for Europa's ocean. So I mentioned it's probably not like a flat ice skating rink under Europa's ice shell. We don't know what it looks like, but it's probably not that beautiful and simple. It's probably not this beautiful and simple either, but to start with, to kind of demonstrate some of the flow features that might develop with ice shelf topography, here's like a very simple ramp that I'm introducing. So it's not a global model quite yet. It's just a rectangular domain starting at a fixed initial temperature, and we're going to introduce a heat gradient and a flow through ice melting and see what develops. So we're seeing some already, just with very simple geometry, interesting and kind of recognizable flow features. So we see the development of what looks kind of like a western boundary current on the left and an ocean gyre on the right. And these are happening because there is melting happening at depth. So if you remember the phase diagram of water, there is a pressure dependence on the melting point of ice. And so we see melting happening on the bottom of this ramp. And then as the fresh water is rising along the meltwater, the ramp, it's circulating, and that's creating a circular flow feature, this gyre. So we have on the left, these are just stream functions, the barotropic stream function, and then the right, an overturning stream function, just in a couple different directions. So maybe more importantly, the melt rate, what's happening. So we're seeing both regions of melting and freezing. The contours got a little dense for the melting, so I just kind of outlined that where that's happening there. But that's happening kind of as the warmer ocean mixed layer water is interacting with this frozen ramp. And so we see that kind of already just very simple geometry, there's lots of dynamics happening. There's freezing, there's melting, there's flow features. But this is probably not very realistic. Maybe more realistic is something like this. So this is a almost global topography that I stole from what Earth's ice shelves look like. I cut out the poles because of convergence issues. And it's a pretty coarse resolution, but it still captures a lot of the large-scale flow features that we see on Earth, as well as some turbulence and mixing effects from small-scale features that are missing. And so I think it's really important to think that like when you're modeling heat transfer, like your grid resolution is really important. So the size of your grid cell in your model affects kind of how quickly heat is transferred through your ocean. And so this is really too coarse to understand what's happening in turbulence and boundary layer effects. So I'm kind of accommodating that in the model by modifying the MIT GCM to have like spatial grid remeshing. So I'm slicing up the grid cells so that I can have melting and freezing happening within a single model run, which is not kind of the standard configuration, within the boundary layer. So this has been kind of very helpful in understanding turbulence and more quick timescale melting and freezing physics. Now, this is kind of one of several things that needs to happen to have a more realistic ice shell, is like greater spatial grid density in the boundary layer. There's also, but even so, it's not going to be a simple ramp. There's other things to introduce, like different heat and salt transfer coefficients, a mushy layer. There's interesting work that's being done by by Jacob Buffo, if you want to look at his work. So in my model currently, the ice is assumed as a completely freshwater layer. That's probably not the case. There might be zones of brines and interesting kind of pockets of heterogeneities that will affect these processes, but this is kind of all just taking steps to introduce more realistic features into an ice shell model, and then look at the global circulation effects of those features. So to wrap up this little bit that I've discussed, terrestrial models I think can be very valuable in the planetary community. Within those models specifically, I think there still needs to be a lot of work done on the ice-ocean boundary layer, which is what I've been focusing on this past year of my PhD, and the potential impacts for habitability of this kind of great resolution on an ice-ocean boundary layer could be very important for habitability. All right, and I'm happy to take questions.
So if you are assuming, so with the mushy layer, like a slurry, for instance, is the assumption of incompressible fluid still valid? And does that change? That makes Navier-Stokes much more complicated, right? So how would that really affect your modeling? Would you have to change some things, or?
Yeah, no, that's a really good question. So realistically, yes, you would change the kind of forcing equations. So the model as it currently runs, it assumes that, it's kind of backing up a little bit, the equation of state of seawater is a linear function of salinity. So if you introduce something like a brine, it's removing that kind of linear assumption. That said, the model as it currently stands, it does have a solid ice layer, so it doesn't look at brine pockets or mushy layers yet. If you wanted to do that, I do think that, yeah, you'd need to change the equation of state of seawater locally, to accommodate those.
And what about the incompressibility assumption?
I think that's a small enough one where if you're looking at the effects on overturning and flow, it wouldn't have an effect, but it would be a very cool sensitivity study. So it's a good question. Thank you.
Thank you.
Hey, sorry, really ignorant question. So with Europa, it seems like there's a very kind of noticeable temperature gradient. Is that just due to pressure, kind of? What's at the middle of Europa?
Ooh, interesting question. Okay, I think I have a backup slide that might help. So yeah, so the mechanisms that are kind of important for Europa heating and what's sustaining the ocean are tidal heating, that it have bottom heating from residual heat of formation, internal heat. If there is this dynamic ice shell that's freezing and melting, like I think it is, then you have heat fluxes from freezing and melting. Yeah, so there's a lot going on. The kind of weights of these effects is still very much unknown, and so that's why I'm really trying to use observations from Earth. So for instance, I'm using turbulent transfer coefficients of freezing and melting from Antarctic field studies to kind of influence this model. But yeah, it's really there's a lot going on, so it's really kind of the challenge is trying to figure out which one is driving, the thermal gradient.
Thanks.
We have time for one more question.
Taylor Plattner at Georgia Tech. Great talk, Sarah. You were talking about brine pockets to make the model more realistic. Do you plan on doing that with your model? And have they done it on Earth, like with like Earth models? Have they even thought of like incorporating brine pockets?
Yeah, it's a good question. So the answer is like no. Most like glacial models and global ocean circulation models don't include brine pockets because on Earth those are more seen in like lake environments or kind of like the like hypersaline lakes and flash frozen lakes that like Jacob works on. They might, Europa's different conditions though. And so they could exist there. So at most, I think I would do a case study on what would happen if brine pockets exist. So it's something I'm working on now, but it's not something I'd include in every run because it's just still very much an unknown.
Yeah, I was gonna say that was kind of like a loaded question, but I was just curious.
No, it's a good question. Yeah.
Thank you so much for the talk, Sarah.
Thank you.
Okay, our next speaker is Sam Nesraldin from the University of Arizona.
Hello. Pleasure to be here. So I'm in the program in applied mathematics at the University of Arizona, but I work with Professor Régis Ferrier, who's an ecologist, and postdoc Antonin Affolter, who is also an ecologist and a planetary scientist. So we develop these global models of Europa. And so what you see right here is the Europa Clipper mission, which is going to launch next year in October, hopefully. And I believe it's the largest, in terms of size, spacecraft that NASA's ever built because of those massive solar panels. Because when we're 5 times away from the sun at Jupiter, I think the brightness scale is like inverse square law, so it's 25 times less bright at that area. So why do we care about Europa? So beneath the ice crust, we have an ocean which potentially contains 2 to 3 times the amount of water as on Earth, which is, when I first discovered that fact, I was just so blown away by that. And we have an energy source from tidal heating, namely, we may have hydrothermal venting as a result of that. We saw that on Enceladus because we saw silicates in the plumes. We haven't confirmed that yet in Europa, but it's very likely based on the amount of tidal energy that we expect. And we also have a rock-ocean interface. So that's very essential for cycling chemicals needed for life. And we have a lot of convection, as Sarah talked about, which is very essential also for those energy gradients. So as a result, we need these models to constrain what we're going to see from the mission. So we had JUICE also, the ESA mission. Let's not forget about that. So we need to model all these different layers. So working off what we did for Enceladus to analyze the Cassini data, we're going to do that here, specifically focusing on the ecosystem aspect. And so what we want to do with that is provide clear constraints on what kind of biosignatures we're going to expect based on a number of different hypotheses of abiotic possibilities, biotic possibilities, and habitable possibilities without life. So as I said, our approach is very multi-level. We are going to first look at the bottom layer, which is the mixing of the core and the ocean, to assess, the chemical structure coming out through the water passing through the core, and what chemicals are going to come through that. We're going to have to assess how that mixes in the water to assess how much chemicals we're going to see coming out of the plumes. And then we also need to take some model organisms from Earth to understand the metabolisms that we might expect, along with the ecological and possible evolutionary dynamics of the life that we're modeling. So with this framework, we're going to estimate the likelihoods of certain data sets that we're going to see via a Bayesian framework. So to intimidate you a little bit, we're going to have some math. So let's talk about the mixing. We look at the dimensionless mixing ratio X and the temperature T. So we have a partial differential equation, which with spatial and time variables. Solving this partial differential equation gives us this steady state composition and temperature of the mixing layer with the mass flux density. So using that information, we can compute what we're going to see coming out of the plumes by integrating over the entire space. So we integrate, the integrand contains this mass flux density and the concentration of a specific chemical component that we're looking at. So whether that be glycine or other amino acids or cells potentially. So the concentration of this compound at the base of the ocean plume, assuming that the buoyant mixing layer mixes together as we described from the previous model, is given by this quotient of these integrals. So then we want to look at the cell metabolism and output, and there's a very large variety of possibilities we could be working with here. So we kind of run the model for tons and tons of possibilities of Earth analogs dependent on these environmental conditions. So we model this catabolic reaction rate of a specific organism using the Arrhenius law. I know that came up yesterday, Arrhenius, in one of the trivia questions. So the Arrhenius law is specifically this quotient here, and we use the catabolic energy constant given by this term, and it goes in here, to understand the ratio of inactivated to activated enzymes for the reaction. Now, critically, we assess the ecological dynamics of the system. So in this case, we are dealing with one population, which is given by a standard ODE model describing the dynamics, but we've been thinking about incorporating multi-species into this because there's actually a significant dynamical difference when you have competition between species in the environment. And that would seriously affect what we'll see when we go there. So we have to have multiple different ecosystem dynamics models. And so we solve this and get a steady state concentration of a specific compound from this. So what can we learn from specifically the Europa Clipper mission? So the Europa Clipper mission has some very interesting instruments. We have a mapping imaging spectrometer. So it'll map the surface and conduct the spectroscopy of the surface and the distribution of the organics. So as things come out of the plumes, they fall onto the surface, and we should expect to see an interesting chemical composition. I know they're already doing this with JWST from a distance. They haven't analyzed that data yet, but should be interesting. And then to sort of sniff the exosphere of Europa, we have a mass spectrometer, mass specs. It'll determine the composition of the ocean beneath by sniffing that exosphere. And then we have a surface dust analyzer. It'll measure like the solid particles coming out. And so in this image, you can see kind of a remote identification of NaCl via spectroscopy. So let's focus on this slide a little bit. So this is the overall framework. So at the top, we have those mechanistic models for the geochemistry and the biology that we discussed earlier. And so the flow of information goes from the top as prior probability densities that flow into as parameters into the general model. Then we pass those parameters into the biological model for physiology and evolution, which then goes to our habitability criterion. So the habitability criterion that we generally use here is, it's a differential equation describing the population. So essentially, if I were to take an Earth-like organism, drop it onto Europa, would the change in the population be positive or would it be zero? So the derivative of population growth, essentially. And so we pass that into Bayes' theorem as prior distributions. The posterior distributions come from these Actually, to be more specific, we simulate all of these models with thousands of data points to get what we call pseudo-data in what's called an approximate Bayesian computation. And so we pass that into the model, and we take the observational data, and we put that into Bayes' theorem. So if any of you are aware of Bayes' theorem, that is a way of assessing the probability of a certain event given prior information and given posterior information. And so now we have this cycle of information. So after we get a probability from Bayes' theorem, we can pass it back into the geophysical parameters model and then continue to constrain as we get more observational data. So here's an example of how we did that with Enceladus for Cassini. So in this graph here, you can see the blue dots are simulations for uninhabitable parameter space. The orange dots are uninhabited but habitable. And the green dots are habitable and habited. So what you can see from analyzing the methane content of the plume in Cassini using this framework was that the vast majority of simulations for all the possibilities we assessed fall under the biotic category, which is pretty exciting because I mean, that speaks for itself, right? So, but there's a very important constraint on this, namely the probability of abiogenesis. So what we do in this model is assess all the possibilities from probability 0 to probability 1 of abiogenesis. And so what we found was at a pretty low probability of abiogenesis, from the previous slide, with a low probability of abiogenesis, you see that biotic explanations are the most probable for what we're seeing in the methane content. So we really need to develop our models of abiogenesis to really limit this variable and constrain this probability. So the conclusion is, in order to find life, we really have to model these planetary systems with the assumption that there could be life there already. Because if we don't, we're going to show up there and we're going to think, okay, it's habitable, but why? Because potentially the habitability of a planet is actually coming from the life that's already there. So we have to incorporate that into our potential models. So this will allow us to really enhance mission data analysis beforehand. So, you know, when we had Cassini, we showed up there and we had no idea what was going on. We're like, wow, plumes, this is amazing. But it took many, many years to really assess this. So hopefully with Europa Clipper, we have this framework in hand as a software package so the data can be fed through real time. And the benefit of this is then we can narrow down in on specific areas of Europa that are of interest to us and really maximize the scientific yield of these missions. So with that, I'll take questions, and thank you.
Nice talk. 2 questions maybe. The first, did you choose a prior for abiogenesis?
Yeah, so we sampled the entire space from 0 to 1 probability in those 10,000 or so simulations. So basically, we can't pick a prior for abiogenesis. There's no constraint on that variable. So essentially, we have to run the model for all possibilities of abiogenesis. So like I said, specifically with the Enceladus data, we found that much less than 50% chance abiogenesis ensures that the biotic explanation is the most probable explanation. I believe is around 30% or less probability. But if you're beneath that threshold, then really the abiotic explanations are way more probable, even though the samples from the abiotic simulations are much smaller. But you know, when the probability of abiogenesis is really low, it's just not going to happen, right? So.
Okay, yeah, that answered my second question. Yeah, it's sort of right.
Great.
Hi, thank you for your talk. So for Europa, are you also, in terms of metabolism, are you thinking about methanogenesis or are
Yeah.
you, okay.
So that was the first step to consider. For Enceladus, it was kind of the most obvious thing to look at because of the methane content. With Europa, it's more complex because we don't have any real data from Europa. And also the environments on Europa are much more varied. You have subsurface pockets of water along with the ocean, and maybe you have like biofilms on the bottom of the ice. So it's a much more complex thing. So my hope is to run all the simulations for all the possible hypotheses that exist currently.
Okay. And I have one little follow-up question. So you very briefly talked about dynamic communities and you mentioned competition. Are you just looking at competition or are you looking at other sorts of consortiums? Like in a biofilm, there's competition, but there's also lots of sharing going on.
Right. So if we're including multi-species in our models, we're hoping to incorporate all the possible interactions between these species, which is really critical. I want to reiterate because, the competition can kill off like all of the life, so we need to sort of have an evolutionary perspective also and not just like a real-time ecological perspective to assess these things. So really good question.
Hi, Emily Barris, Stanford University. I was wondering, so in the biological part of the model, what kind of data goes into that and how can environmental microbiologists help modelers improve their models? What kind of data do you need for that?
Right. So we need Earth analogs primarily. We need the catabolic reaction parameters for specific Earth analogs. So we might want to go to Antarctica and see what's going on there. And that's our best way to constrain it at the moment. So that's how I think biologists really help us in that way. Yeah, exactly.
Thank you so much for your talk, Sam.
Thank you.
Our next speaker is Pavel Klyer from NASA Ames.
Hi, everyone. I'm just going to make a quick note before we start that it's great to be in an astrobiology conference because the background slides are going to go much more smoothly. I presented this at a microscopy conference a few months back, and it was a different experience. So thank you all for being here and being you. I'm going to talk, this is going to be a little bit of a pivot from some of the previous talks, but I'm going to talk about some of the methods that I've been working on to actually detect life on a mission, a life detection mission to Europa or Enceladus. I'm also going to make a note, so I'm going to be talking about life detection missions to Europa and Enceladus as a target for this, but once you have a space-capable microscope, this could potentially be applied to like all sorts of destinations. So there's lots of fun possibilities here. The aforementioned background slides. So when we're picking destinations to look for life, we like to look for places that have habitable conditions, things that have liquid water, abundant energy sources, and conditions that are suitable for life as we know it or as we might predict it may exist. And I'm just going to let Enceladus and Europa sit up there because we've already heard a lot of justifications as to why those are promising targets to find those conditions and why we might have had an origin of life or living organisms currently there. But when we're searching for life, we also have to think about how we're actually going to look for it. And so we can kind of break down life into some of the key components that make it up. Things like catalysts that help it metabolize, things like information storage polymers, so DNA or RNA and Earth-based life, but that might look very different for extraterrestrial life. and also compartments. Life on Earth, life as we know it, loves to put things inside of membranes, and then sometimes they put those membranes inside other membranes and have them connect to other even more membranes. But that packaging really helps it do some interesting chemistry. And so when we're then thinking about this in the context of a mission, we can start to think about how we might actually observe that and what analytical approaches we need to take to try and get at that. And so I put the giant table up here because these are all things that people are working on for life detection instrumentation. But we're going to be focusing for this talk on containers. And so the reason for that is that, again, as mentioned, life loves to package things into compartments, and those compartments can be directly observable by using a microscope to look for morphology and also for the colocalization of certain key chemical biomarkers. So in our team, we're working on a microscopy system that we call a luminescence imager for exploration, or LIFE. And there's two key hardware components of this system. One is the fluidic subsystem, and this is to deal with the actual sample processing and preparation for imaging something. So my background, full disclosure, is actually not in astrobiology. It's in fluorescence microscopy. And I spent like 5 or 6 years in grad school just moving fluids around in tubes and preparing things on slides before they actually get to the microscope. I've been told it would be expensive to send me to Enceladus, so this is my replacement. And then the other end is the actual microscope itself, so the optics system, which is going to have all of the things that you need to actually take your pretty pictures. So I'm going to break down what goes into these systems a little bit. So the fluidic subsystem, that silver plate on top, is the rotary filter stage. And so the stage can do 7 individual experiments. And so that accounts for, originally this was designed with the Europa lander mission concept in mind, where there would be 3 separate samples, each with a replicate and then a procedural blank. And then each of those individually has 3 filters of different sizes. And so that basically will let you sort out particles. So the filters are 10 microns, 1.2 microns, and 0.2 microns in size. And that's just so you don't end up with larger particles obscuring any of the smaller particles that you're trying to image in your sample. And that way you're not missing any of the good stuff that might be there. It's also attached to the fluidics manifold, which is the part that actually moves all of the liquids and fluids around. And it also has a lot of sensors for pressure, pH, conductivity, and also, crucially, some storage for the fluorescent stains that I'm going to be talking about a little bit later in the talk. And then these were the filters that I mentioned earlier. And so this is, again, for sample size sorting. But they're also made of a silicon nitride substrate that has a low fluorescence background. And this whole system has passed environmental testing. So one thing about microscopes and also fluidics has a fair bit of spaceflight heritage, but in general, hardware can break. And I'm sure everyone who's worked in a lab has dealt with a lot of issues before. So you want to make sure that these things are robust and you can actually get it to where you want to launch it to. The optics subsystem is a nice small compact box. And so this is a 10 centimeter by 10 centimeter by 13 centimeter cube. I have an image on my phone that I didn't upload to the presentation because the image quality is not that good, but for context, that's about as tall as a banana, which is very small for a benchtop fluorescence microscope. There's Fancier microscopes can sometimes be like the size of a person if you're trying to do crazy like 2-photon lifetime imaging or something. But even an epifluorescence scope would probably occupy like this podium normally. And there'd be a lot of like miscellaneous kind of assorted parts. So it's a really nice little system. And so that contains all of the excitation LEDs, emission filters, all the optics. And so this table is just kind of going through what the different bits of hardware that we have are, and to kind of like give the high level summary of why this is relevant. Basically, we have 3 LEDs that are common excitation wavelengths for different fluorescent stains that can also excite different types of autofluorescence. And then one thing that's actually relatively unique to this microscope, certainly no microscopes I've worked with previously have had this, is the 275 nanometer LED. So that's actually fairly far in the ultraviolet range. And that's really good at exciting protein fluorescence. So tryptophan, phenylalanine, the various aromatic amino acid side chains actually fluoresce quite brightly in the ultraviolet. And so that can help image native fluorescence of samples and also excite the fluorescence of many different kinds of minerals. The objective is also set up to help, well, it's robust to spaceflight, but also the part that I think is super fun is that most objectives actually can't collect light in that ultraviolet range. So it is a custom objective that's built for those sorts of experiments. It has a piezo stage that lets us do automated Z-stacking. And this has also been subjected to environmental and shock and vibrational testing, and also radiation testing to the specifications of the Europa lander mission. So we're now on our ongoing work is actually characterizing this microscope by imaging different types of samples to see what the limits are of what we can detect. So this sample is just kind of showing some bright field images from a sample that was collected from Lake Untersee in Antarctica. And so I'm showing here the 10 micron and 1.2 micron filter just to kind of highlight that we can image the objects of very different sizes, and you can see the physical size of the little holes there. And so if we were to just put this all onto one filter, that microbial matte looking thing on your left would probably obscure some of the smaller objects that we're seeing in the other filter sizes. And so, as I mentioned earlier, we can also excite native fluorescence, and so we can correlate this as well with the bright field images. So we can take an image of an object, say, oh, hey, that looks interesting. I wonder what that is. Look at the native fluorescence in different ranges and get a sense of, okay, wait, we've got a bunch of like organics that are fluorescing in the UV range that are all localized on this object. That's pretty exciting. And then we can also then stain the sample with fluorescent stains to look for more specific chemical signatures. And so in this case, I'm showing the same sample after it's been treated with a stain for primary amines and another one that stains lipids. And so we can look for both the presence of those molecules, but also their co-localization in space. And this is a really like unique and powerful kind of data that you can get from the microscope, is not just like what compounds are there, but seeing that they're associating with each other kind of gives you a good piece of evidence that you might be seeing some disequilibrium and some living structures. Microscopy data is also large, maybe not as large as some of the types of data that we've talked about in this conference so far, but certainly large enough that if you were trying to send all of this data back from Europa or Enceladus, it would be more complicated to handle. And so one of the things that we're able to do on this microscope is actually take a Z-stack of images and compress it down to a single image that's much less in data volume. And so the image I'm showing right now is an image set of images that were automatically collected at different focal planes in the sample. And then after it's run through the compression routine, you end up with a single in-focus image, and you're now suddenly gone from megabytes of data to kilobytes of data. And then you can even go further with that, and you'll notice that this sample has bright objects against a dark background. We don't actually care what the photon shot noise is on the background. For our purposes, that might as well just all be 0. And so the final compression step is actually taking that and setting it to 0. And so we're just recording the actual bright objects that are detected in the image. And so that all reduces the data size quite substantially without really getting rid of any of the information that we actually want to take out of that sample. So how would this work in a mission? I just talked about a lot of different parts, and now I'm going to bring it all back together into how this system could be implemented. I have the little Europa lander picture there. But basically, we pretend that the microscope is somewhere in that lander. You would take your sample, process it, pump it through the fluidic system. You can image it on the microscope. You're going to end up with megabytes of data that you can then compress back down to your kilobytes of data, send it back to your ground-based observer that will then be able to say, oh, okay, cool. We got a microbial mat on Europa. Time to hit the press. And so, yeah, just briefly, acknowledgements. There's been a lot of funding that's gone into this. I'll be happy to take any questions.
Great talk. This is Chad Pozoriski at Georgia Tech. So I'm really happy that you touched on compression, first of all, of the data, because that's incredibly important. And I was also really thrilled that you talked about the sample prep and fluidics, because I think that's something that a lot of people don't consider for these in situ missions. My question has to do with comparing microscopy and staining with perhaps something like Raman or IR, where you could get information about at least functional groups of the organics present and co-locate things at, I imagine, similar resolution spatially, but you wouldn't need to include those processing steps. So would you advocate for a system that's, I guess, maybe not redundant, but has both of those features, or do you think one is better than the other? Or?
Yes, this is actually a super interesting discussion, and we can definitely also talk more about it at lunch, but the high-level thing that I'm going to say is that you're going to have different pros and cons and get different types of data out of those techniques. So if you're doing, if you want to get spatially correlated Raman data, when you're building a microscope and you're trying to image something, unless you're using a super resolution technique, you're limited by diffraction in terms of like the resolution that you can get, and that is proportional to the wavelength that you're using. So when you start to get into like the IR, range and things like that, your spatial resolution starts to be more limited than it is in the optical range. The flip side is, you're right, you can get precise chemical information out without, adding labels. And so I think that definitely those are like in the perfect mission architecture, I think you'd do both. Unfortunately, it's unfortunate that we can't send all the instruments that we want out there, but like in my ideal world, I think that would be a powerful like correlative technique there to kind of get a strong sense of what you're seeing in your sample. But yeah, great question.
Thanks.
Hey, it's Emily again. Thanks for an awesome talk. This is really exciting. So I was wondering what sample prep looks like in the rover or whatever, and what the capabilities are for that. So could you actually do like incubation experiments and then look at it with microscopy, or is it coming straight from the environment and going straight to the microscope?
Yeah, so it's the design that we had in mind for sample prep here, and when I say we, it's not us. This was kind of built around the Europa Lander specifications, but essentially you'd have a sample cup that would collect an ice sample and melt it down, and so that was kind of the initial like thoughts behind the design here. But the fluidics processing system can basically handle anything that's in a liquid state, but the assumption would be that it's a relatively unprocessed field sample. Relatively unprocessed because obviously if it's like ice or something and you're melting it down, you are still doing something to that sample.
Thanks. Okay, we have time for one more question.
Hi, thank you for the great talk. My question is, maybe I missed that you mentioned, how are you going to differentiate any other particles from the living materials? Like, can you specifically stain genetic material or anything biological?
Yeah, so that's a great question, and so the goal here is to kind of pick up as many different breadcrumbs as we can to try and differentiate. And so you mentioned stains for genetic material. One of the stains that we would be launching with this is a stain for nucleic acids. Now, obviously, that would be really awesome if we found DNA on Europa or Enceladus, but it's kind of an open question whether we would. So the idea behind looking for something like the colocalization of amines and lipids is that gives you a more like agnostic idea of like, hey, that might be living material because you've got these chemical signatures that are collocating. The other thing is, so one of our collaborators, actually the person who helped build the microscope, has some ongoing work characterizing the fluorescence of a wide library of minerals to get a sense of like what they would potentially look like on the microscope, so we can hopefully differentiate between that and things that might be a little bit more biological, both spectroscopically and then also morphologically. So yeah, but great question.
Amazing. Thank you for the talk.
Our next speaker is Kenneth Seaton from JPL.
Hello. As Miguel said, my name's Marshall, and I'm an NPP fellow at JPL Caltech, and I work with Morgan Cable and Brianna Henderson, and I do most of my experimental work at Caltech in Paul Asimov's lab. But because this is a conference of literally graduate students and postdocs, I wanted to talk about the Planetary Science Summer School program, which is a program for graduate students and postdocs to teach you all how mission design for planetary missions actually happens and to learn the process. And so I'm going to be presenting the mission that my team and I developed during the PSSS, in which the majority of the framework for the mission was developed back in 2021 and that we iterated on since then. The Astrobiology Exploration at Enceladus, or AX for short. And I'm going to preface this by saying that this is an unholy amount of information to distill into a dozen slides. And so I did my best. Unfortunately, I can't go into a lot of detail with these slides, but if you have any questions about the science, ask a question. If you don't want to ask a question, come find me. I'd love to be stoked to talk about this stuff. Okay, so I'm sure you guys are familiar with Enceladus at this point, but that thing is Enceladus. It's one of Saturn's moons, and it's relatively pretty small. It's only about 500 kilometers in diameter, but there's some super cool stuff going on, even though it's this tiny little thing. That stuff coming out of the bottom of Enceladus is a continuous plume that's formed over the south polar terrain. And so if we zoom in a little bit closer, these are images from Cassini, and it's not actually blue like that, that's in false color, but that's just to show you where these fractures are. And the plume is sourced from those fractures that all it combines to form a continuous plume over the south polar terrain. And we have really strong evidence from some of the measurements by Cassini that this plume is directly sourced from a subsurface global liquid water ocean. And so this presents a unique opportunity, unique in our solar system, to sample the contents of a subsurface ocean in situ using a multi-flyby or an orbiter mission architecture. And we have some rough compositional information of the plume from Cassini using the INMS, or the ion and neutral mass spectrometer, and the cosmic dust analyzer. And so in the plume gas, we see water, small hydrocarbons, some simple and complex organics, and this is the paper from the Wade et al. Paper back in 2006 from the INMS data. But if we look at plume grains, we see that they're water ice, but we see a lot of different salts. But in addition to that, and I think a previous talk hit on this a little bit, we see silica nanograins. And that's really important because based on what we know, the only way that these silica nanoparticles could be produced within this size range are high temperature hydrothermal reactions. And that's huge from a habitability standpoint. And in addition to this, looking at the CDA data, the cosmic dust analyzer, we see evidence, not direct detection because of the instrumental capabilities we had at the time. This is like 80s technology. But we see strong evidence for macromolecular organic compounds. And so there's this complex organic chemistry going on that we don't really understand, and we don't know what's going on there, but like something's happening. And so we need to figure out what's up. And so with that being said, we have liquid water. We have a geothermal source of heat via the high temperature hydrothermal reactions. Essentially all of the chemical building blocks for life as we know it are present. Sulfur hasn't been published yet, but it has been detected in the grains. It should be published in the next year or so. So with all of this in mind, could Enceladus harbor life? We thought it would be sick to develop a mission concept that would be capable of finding out. And so just a brief overview of our mission architecture. It's be a multi-flyby mission where you're orbiting Saturn and do multiple flybys of Enceladus. And we would require 30 flybys for our science and would launch in 2033. And after a 9-year cruise phase and a 1-year pump down phase, we would enter 4 years of science operations where we would directly search for biosignatures through in situ chemical compositional analysis of the plume and contextualize these in situ measurements through a synergistic combination of geophysical and geomorphological investigations aimed at also assessing the habitability of Enceladus over geologic time. And we would do this using a mass spectrometer, a high-resolution camera, and just a high-gain antenna. So 2.5 instruments, because the antenna you use for radio communications. And so just briefly to talk about how, before I dive into the science objectives, how these objectives were formulated. NASA doesn't like as much when people when they're developing missions to like take this instrument, okay, we have a sick instrument, what kind of science can we do with it? Instead, we were taught and we were informed that NASA prefers that you first start by asking questions. Like, what do we not know about Enceladus? What do we need to know to ask more questions? And so that's what we started by doing. And if you do that, if you start from the science questions and what you're interested in and what you want to find out, the rest of it follows pretty logically. And so say we want to find out this thing. Okay, what do we need to measure to figure that thing out? Okay, then you have your measurement requirements. And then at what levels do we need to measure this? There you have like further established measurement requirements. Well, how do we make these measurements? And then you select your instruments and then so on and so forth. And so it just logically flows from, it's called a left to right approach. And so I'll talk a little bit about our science objectives. Of course, the first of which is to determine if the molecular and isotopic distributions within the plume are a result of biological activity or abiotic chemical processing. And we would do this just with your usual suspects, amino acids, fatty acids, and plume grains, and by assessing isotopic fractionation in the plume gas. And we would do this just using a mass spectrometer. And if you have any questions about mass specs or instrument selection, please ask a question or find me later. I'd love to talk about that. And the second of our objectives is to determine whether Enceladus is in thermal equilibrium and is therefore capable of sustaining an ocean over geologic timescales. And this is essentially just a heat balance equation. We want to know how much heat is being input to Enceladus through tidal dissipation from Saturn, and how much heat is being emitted by Enceladus through conductive heat loss. And you can actually determine the heat being generated within Enceladus by looking at tidal dissipation from Saturn. And you can do this using orbital migration rates. So you could look at where Enceladus is at in its orbital phase relative to what was seen by Cassini to see how the orbital migration happens. And from that, you could calculate a tidal dissipation quality factor. And you can determine the heat being emitted by measuring ice shell thickness, which is a proxy for the heat loss. And you can do that using gravity science measurements. The third of our objectives is looking at plume formation mechanisms to determine whether the plume material is being delivered to the surface via open crevice boiling or explosive cryovolcanic-like eruptions. And we expect there to be differences in the morphology of the vents at the surface that are expressed in each scenario. And you could actually sort of tease out how these plumes are being formed by high-resolution imaging of the vents. So for an open crevice model, we expect there to be vent width variations in response to tidal forcing throughout Enceladus's orbital phase. And for an open crevice model, we expect these vent width variations to be consistent along the strike of the vent. And so by taking multiple high-resolution images of a single vent throughout Enceladus's orbital phase and looking at vent width variations, we could determine if that were the case. Whereas for a purely cryovolcanic eruptive model, we expect these vent width variations to be restricted to the immediate vicinity of the vent. And so we could sort of tease out the relative contribution of each of these models to plume formation. And then our fourth and final science objective is to determine if the geologic activity that is modifying the south polar terrain, like we see in all those awesome images, if it's influenced other regions in the past over geologic time. And we would do this by looking at two things, both crater infilling and elliptical crater orientations. Because if you look at the depth diameter ratios of craters around the south polar terrain, they're pretty shallow compared to the rest of the crater population because of all that plume fallout that's infilling the craters. And so we see really shallow craters around there. But if you look at the global crater population, like typically, they have a pretty well-defined depth diameter ratio. And so if we were to survey the global crater population and find an area around Enceladus where we see anomalously infilled craters, that could be evidence that there was past plume activity. And another thing that we would look at are elliptical crater orientations to see if there could have been any ice shell reorientation in the past. Because given a preferential velocity vector in the impactor population and a small enough impact angle below about 15 degrees, elliptical craters are formed. And so, given a preferential velocity vector, we expect to see mostly east-west oriented elliptical craters. And so if we were to survey the crater population and see a shift in the orientation of these elliptical craters that is relatively consistent, we could infer past ice shell reorientation from that. And so for the mission trajectory, briefly, we would use Venus, Earth, 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 Venus, Earth, 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 Jupiter gravity assist, where we would do a slingshot around Venus and then a couple orbits around Earth, and then slingshot out to the Jupiter system, and then use Jupiter's gravity to slingshot out into the Saturn system. But getting out to Saturn isn't the problem. It's slowing down. That's the problem. because you're going like 15, 20 kilometers a second. And so after Saturn orbital insertion, we would do a one-year pump down phase and use multiple flybys of Titan using Titan's gravity to reduce the spacecraft velocity and tailor the inclination and altitude such that we could target Enceladus properly for our flybys. And then after that, enter a 4-year tour phase where we would conduct all of our science operations. That would consist of 30 flybys at least. And this requirement is driven primarily by our gravity science measurements that we need to make. And the surface mapping would require a total of 22 flybys. Not necessarily 22 flybys total dedicated surface mapping, but the data downlink would require 22 flybys. And so a minimum of 5 flybys at low altitudes as well for event imagery and in situ plume analyses. So key takeaway, Enceladus is sick, it's super awesome, there's a lot of really cool stuff going on there. And we would see what's going on there by looking at plume composition, heat balance, the different event formation mechanisms, and what the surface of Enceladus can tell us about its past. And this is important because in the most recent decadal survey, they specifically call out a New Frontiers mission to Enceladus using a multi-flyby mission architecture. And so there's so many outstanding questions that we just don't know about what's going on in Enceladus, and we need to go back to figure out what's going on. So as promised, a little talk about PSSS. This is my team that I worked with, and they're the most absurdly brilliant group of people that I've ever had the pleasure of working with. They're incredible. I'm still friends with many of them now. And so I'd like to talk a little bit about the PSSS. It's not really as much of a summer school as it is a rigorous mission design program where they teach you how to actually formulate a mission. And the deadline's passed for this year, but it's competitive. You have to apply for it, and they take 18 people per cohort. But you get to work with literally the best in the business. You're mentored by people that are on like Europa Clipper, Mars Sample Return, all that kind of stuff. And in the last week, you get to work one-on-one and are mentored by a member of NASA's advanced project design team, Team X. They're literally the best at what they do, formulating missions. And you learn so much, and it's incredible. If you have any questions, please come find me, ask here, or if you don't want to ask a question in front of a bunch of people, come find me, talk to me. I knew when I first was thinking about doing it, I was like, oh my God, I don't know anything about mission design. How am I going to do this? But everybody else in my cohort thought the exact same thing. So you don't need to be an expert in mission design. You just need to be interested and enthusiastic about doing this stuff. And this is the most incredible experience I've had of my professional career. So I would highly, highly recommend this program to anybody interested in mission design. Thank you.
Any questions?
Hi, Michael. I'm from UCSD, just up the hill. I was wondering, is there like, how quickly, or is it pluming? Like, is it gonna run out of water?
How quickly is it pluming? Nice. Well, it's been active for, I mean, Enceladus is anywhere between like 100 million and over 2 billion years old. And it's been, like the E-ring around Saturn is composed mostly of Enceladus plume material. So we know it's been around for a very, very long time. And we also know that the ocean is quite large and makes up a pretty significant portion of the mass of the moon. So there's not any evidence, as far as I'm concerned, or as far as I know, that it's running out anytime soon. And we believe it's still active.
I'm curious, does this program kind of have a component where you assess the costs of certain missions and sort of optimize for that? Because a
Does
lot
it
of
have a component? That's it's like the entire last week is like so the New Frontiers 5 cost cap is 900 million, and it takes like 700 million to take a piece of cardboard to Enceladus, and so yeah, it's a huge part of it, and that's like a huge part of like working with Team X is to try and do rapid iterations of your mission concept to see what you can do and what trade space you can explore to fall with under the cost cap, because the problem isn't like finding all the science to do, because like there's so much science you can do. It's finding it's doing the most science for the least money. And so unfortunately that is a massive part of mission design and formulation.
Thank you.
Hi, Colin Robinson, Brigham Young University. I was just wondering, I know one of the big hindrances to sampling organics from plumes on Enceladus is destruction of organics because in the sampling processes, right? Because of velocity, and you just go, at high speeds through the plume with like a cup to pick up all of that stuff, lots of the organics are just gonna be obliterated. So what steps were you guys thinking of taking to eliminate destruction of biosignatures?
Thank you so much for asking that question. That's the research that I'm doing at Caltech, is we're simulating hypervelocity impacts of ice grains using impact ionization mass spectrometry. And we're the only lab in the world that can do that at the moment, that can actually simulate a distribution of ice. Well, I don't want to I'll nerd out too much. Come find me to talk about that after this if you want. But to answer your question, yes. There is a velocity regime where you have both efficient ionization, assuming you're using an impact ionization mass spectrometer for analysis of plume grains, which is pretty necessary at this stage. Yes, there is a velocity regime that you have efficient ionization and molecular survivability for a range of compound classes. And the survivability velocity range depends on molecular functionality, but it's somewhere between 4 and 6 kilometers per second is like the Goldilocks zone that you want to sample at. So yes, that's a fantastic question, and that is a problem that a lot of very smart people are trying to solve right now.
In terms of that speed, 4 to 6 kilometers per second, is that fast enough to be able to stay out of the gravitational pull of Enceladus? Or?
Oh yeah.
Okay.
Yeah, Enceladus there's not very much gravity there.
Basically, yeah, it's tiny.
Yeah.
Thank you.
No problem.
Hi, I'm Veronica from Cornell. So this is a fracture question, but whether it's like a open fracture versus cryovolcanism, is that going to impact the types of biosignatures that could be detected?
Yes, very much so. And that's a fantastic question. In each case, the mechanism of plume formation that's underlying the surface, I'm trying to think of the best way to say it, but the way the grains are formed actually strongly influences the composition of the grains, because you have homogeneous nucleation where you just have like water that just freezes and is shot out, and like the open crevice boiling situation, where you have heterogeneous nucleation, where you have, well, I don't want to get too much in the weeds, but yes, for an explosive cryovolcanic scenario, like you mentioned, we wouldn't see very many compositional differences from grain to grain. Whereas for the open crevice boiling scenario, due to the different ice grain nucleation processes that can occur, you would see very distinct compositional differences in the grains, and we see that in the CDA data. That's where all those evidence for those organics that I was talking about before, those complex organics, that comes from ice grains that are composed primarily of an organic phase that were formed very likely through open crevice boiling. And so I guess that's a long answer to saying yes, that it very much matters. That's why we want to find out.
Okay, our lunch delivery is running a little late, so we have time for another question if someone has. Yeah.
Thanks, Marshall. I've heard this talk many times before.
You're welcome.
And every time, and every time it's enjoyable, and every time I feel like
Thanks,
I
John.
ask the question about what kind of mass spectrometer are you going to include? What kind of resolution or MSMS capabilities do you need to detect biosignatures, get isotopic information, get through matrices of the salt grains crystals?
Thank you. You gave me an excuse to talk about that now. So for the gas, the plume gas, you need some sort of like a QITMS or like mass specs type instrument that I'm sure you're familiar with that stuff. But where you need to be able to like have a sample inlet where you take gas in and then you determine the composition of that. And that's really necessary for assessing isotopic fractionation because those typically have very high mass resolution, which you need for looking at different isotopologues and things. Whereas for the plume grains, a lot of dust detectors don't have the same mass resolution just due to the way the instruments are designed. But you need information about the ice grain composition because all the cool stuff is in the grains, and the lower the bigger the grains are, the lower the velocity, the lower the altitude, the more interesting the grain composition is. And so you need, in theory, you could just use one, to answer your question, like a mass specs type instrument, where for those people that don't know, mass specs is an acronym for the mass spectrometer for planetary exploration. Well, planetary exploration, yes, mass spectrometer for planetary exploration. That's going to be going on Europa Clipper. But that can do grains, but those sort of instruments have issues with some of the more refractory organics and some inorganic species. And so what you really need to be able to do this, given that you have enough cost margin, is you need a dust detector or a grain, like some sort of impact ionization mass spectrometer that can utilize these hypervelocity impacts as an ionization source to determine ice grain composition, and also something where you can assess the composition of the plume gas as well. Thanks. So there are, if I go back to a couple of slides. So it's in eccentric orbit, the very eccentric orbit around Saturn. And so if you look at, I don't know, can you see the cursor? Okay, yeah, you can. Right here, see that little green dot? That's where every orbit you do like a small burn where you use a little bit of fuel to make sure that you stay in the orbit that you need to actually do these measurements. And so it's not as huge of a deal and doesn't require like a ton of delta V or like change in velocity of the spacecraft. But no, that is something to consider, and you're right. And that is something that we took into account when doing all these the orbital calculations. So that's before we actually start science operations, because upon Saturn orbital insertion, we're going too fast, and the spacecraft, the inclination, altitude, geometry, things like that, aren't suitable to immediately enter science operations to start doing targeted Enceladus flybys. And so we need to use Titan's gravity to further slow down so we can get within that Goldilocks zone that we talked about before for sampling. Thank you.
Okay, so lunch will be served soon in Surfside, and then we'll reconvene again at 12:45 for our second series of short talks.
All right, everyone. Hey, let's calm down a little bit, but get excited for stellar science. I'd like to go ahead and start our next session. These are short talks. All right, everyone's listening now. Okay, and I want to preface this again, just like yesterday's short talk sessions. These are going to be short 6-minute talks. There will be no time for questions after, but these presenters will also have posters outside at the poster session directly afterwards, okay? So save your questions for them. And without further ado, I'd like to welcome our first presenter today, Bolaga Olanrewaju from Ohio University, Athens. There you go.
Hi, everyone. I'm Bolaga from Ohio University. I'm a space biologist, a bit different from astrobiologists in that we send plant samples to space and we try to see how those plant samples adapt to the spaceflight environment. And then we use information from these to make them better adapt to extreme environment on Earth, or to also prepare how we can cultivate plants in space for future cultivation, future exploration. And so I work on Arabidopsis plants, which is a model plant. It's what E. coli is to microbiologists. And it's model because it has all the genome sequenced already. And so we can easily trace a particular phenotype to a particular genotype. So to the right up there is what the Arabidopsis seedlings look like after we get them back from the space environment. In this case, I mean about the International Space Station at the lower Earth orbit, where we have zero gravity, microgravity, and where we have ionizing radiation and altered flue gas dynamics as one of the extremities in that environment. So basically, we send seed to space. We let those seeds germinate in space. We let them grow for a few days. We freeze them, and we return them to Earth. And when they get back to Earth, I analyze them, transcriptomics and proteomics, to make sense of how such plant adapts to the spaceflight environment. And for us to conduct spaceflight environment, we use different hardwares, as you can see. On top here is the Advanced Plant Habitat. That's the most desirable hardware currently for almost everyone researching space plant biology. And here we have the brick hardware. I love using the brick. It got the name from the fact that it looks like a brick block. It's biological research in canister. I work with it. And this is the European modular cultivation system. It's being retired currently and being replaced by the multivariable platform. So these are just few of the many hardwares that we use to send specimen to space, plant, micro, but in this case, we use this to send our plant to space. The first multi-omics experiment conducted on plants sent to space was conducted by my lab, and then we discovered that comparing the log4 change of the transcript, that's the RNA, to the log4 change of the protein, while plotting a correlation graph of it, we discovered very low correlation between differentially expressed transcript and differentially abundant protein, which is indicative of the fact that post-transcriptional modification of transcript is one of the adaptive mechanisms of plants to spaceflight environment. That means not all RNA gets to become protein. And that also, it's underscore the need for us to study proteomics, to conduct proteomic studies of these plants that we send to space, because the proteomics will probably give more insight into the adaptive mechanism than the transcriptomics. Unfortunately, because proteomic study require large tissue mass, which we don't have the luxury of having large plants sent to space, most people conduct just transcriptomic study. Until date, globally, only 4 proteomic studies have been conducted on Arabidopsis aboard ISS. And these are the 4 proteomic studies. Different conditions, different variables, age of the plant, hardware, light condition, seed line used, the tissue type, and the type of protein extracted. They vary across all those 4 experiments. 2 of those experiments were conducted in the lab. I'm the one in charge of the last one in red, called the Brick LED project. So to get idea of to get idea of plants' response on the proteomic level to the spaceflight environment based on these field data set, we have to do what we call meta-analysis of the proteomic data set from these from these 4 experiments, and that's what I do. So this is the first stage of the meta-analysis. So we start from the left here. We intersected the protein abundance with the detected protein across all the 4 hardwares. And common to the protein across all the 4 hardwares these are 3 proteins, which are PCAP1, that's the microtubule destabilizing protein, which is involved in chromosome separation during cell division. It's involved in formation of cell shape, and it's also involved in transport, vesicular transport in plant. And also we discovered that common to these 4 data sets, protein, is that the protein involved in defense response and mRNA binding. Now, I went a step further and isolated the data set called EMCS, which is the data set called ABRS, Advanced Biological Research System. I isolated it from the general data set because they used a mutant seed line. So I compared those seed lines that were the wide type, and from intersection of the 3 data sets that use our seed lines that are wide type, we have these 8 proteins, and here are they. Here are the proteins. So conducting a protein interaction network analysis, we see that regulation of microtubule destabilization, microtubule rearrangement is a major adaptation mechanism of plants to the extreme spaceflight environment. And one thing we notice in phenotype of plants that we grow in space is that they are usually smaller, looking less healthy compared to those grown on Earth, where we have the full gravity and no ionizing radiation. Now, I went further to compare the BRIC dataset, which are the one that we conducted in our lab and we can be so sure of. So we have 2 of them. We have the BRIC LED, which were conducted in light. This BRIC LED hardware had light in it. And we have the BRIC PDFU, which had no light. So all these plants, these experiments were both flown to space, flown to space, but one had light, one had no light. Both of them had no gravity. At the intersect of them, the protein here, 186 of them, will definitely be due to the spaceflight environment. While the protein here will be due to photomorphogenesis, that's its growth in light, cross-interacting protein, maybe between the hardware and growth in light, and elusive protein due to the advanced technology that we use in the BRIC LED compared to the BRIC PDFU. While the protein here are those involved in scotomorphogenesis, growth in darkness, and cross-interacting protein. Now, I call this protein, due to spaceflight environment, I call them the BRIC intercept. So, comparing the BRIC intercept, this is the BRIC intercept, comparing it with another data set from the European Modular Cultivation System, where they had a centrifuge aboard the International Space Station, 1G centrifuge. Having a 1G centrifuge above International Space Station eliminates microgravity. So it introduced 1G gravity. So this data set, EMCS, has excluded microgravity. And everything in this data set is radiation. So comparing, intersecting this BRIC intercept with this EMCS data set, whatever is in the middle here will definitely be due to radiation or altered fluid gas dynamic. In the absence of gravity, plants don't pick water the same way they will do on Earth. And whatever we will have here is due to microgravity, definitely. And whatever we have here, proteins here, are due to the EMCS hardware and cross-interaction. Now, doing a protein-protein interaction network of the proteins that we believe are due to radiation, we see that most of them are involved in ribosome assembly, ribosome biogenesis, and protein translational machinery. So one takeaway from this is that Arabidopsis ribosomal activity is altered by spaceflight ionizing radiation. So currently, I'm comparing the transcriptomic data between these two data sets, and we're also trying to do a wet lab determination of the specific role of this intersecting protein. So we're hoping to collaboration on a proteomic meta-analysis of this spaceflight stuff. There are a lot of things that could be done on it. So my acknowledgement to Dr. Sarah White, that's my advisor, and then Dr. Colin Cruz from the National Lab in New Mexico, and to the NASA Analysis Working Group, Plant Omics, who sponsored this research. Thank you so much.
All right, thank you, Bolaga. Our next presenter will be Madeline Purnell from the University of Utah.
Hello, we're gonna jump right into things because I have a lot to say on this topic. So, extremophiles can help us predict the boundaries of life here on Earth and the possibility of life on other planets. Yet most extremophiles that we study are typically single-cellular organisms, leaving a gap in knowledge about multicellular life and its habitability limits and origins. And so that's kind of where our work comes into play for my lab. So we're a nematode lab, and nematodes are one of the most widespread and resilient animal phylums on Earth. They make up about 80% of all animal life and are found on every continent and in every ecosystem, including some found in like South African gold mines, Antarctica and the dry valleys, etc. So my work is based in the Great Salt Lake. It's an analog lake for the evaporated saline lakes on Mars. And it is also the 4th largest terminal lake in the world, meaning that it gets a large inflow of water, but the only source of outflow is via evaporation. It's also been geologically consistent for the last 780 millennia and was only once previously part of like a Paleohistine freshwater lake for a really brief period of time. But one thing that you might notice is that it has a really stark salinity gradient that's caused from a railroad construction that cut the Great Salt Lake in half, creating the north and south arms. So the south arm is about at 15% salinity due to the inflow of water, and the north arm doesn't get any inflow of water and so stays at about 27% salinity. 15% salinity, just so you are aware, is about 3 times more saline than the ocean and is well beyond the previous maximum recorded salinity gradient that nematodes have been found to live in. And so my lab went searching for nematodes in the Great Salt Lake. And so we chose 6 different sites, to look at. 3 which were from an inflow river that was between like freshwater to hyposaline conditions, and then 3 from inside the Great Salt Lake, which were well into the hypersaline conditions. And it is here that we found some nematodes. So one unique structure in the Great Salt Lake are these microbialites. They're organosedimentary structures, and they're built by photosynthetic microbes, and so are host to complex microbial communities, as well as our nematodes. They're also the oldest known evidence of life on Earth, some dating back to about 3.4 billion years ago. And so they can kind of offer us a glimpse of life before more complex life forms. And they range about 20 to 30% of the Great Salt Lake bottom. So we've found that these nematodes, through 18S sequencing, are novel Monhisteridae species. Monhisteridae are typically a freshwater nematode, though some are also found in marine ecosystems. And so our goal now is to look at their genome and transcriptome in order to be able to tell the presence and absence of gene families and see what genes are being functionally used here in the Great Salt Lake to potentially help with saline, UV, and temperature tolerances. And we're also looking at coevolution with other microbiota. So by isolating single worms, we can look at presence of microbiota in or on the worm. So we want to be able to look at diatoms, fungus, and bacteria. And so far, we've been able to do V4 region of 16S rRNA sequencing of bacteria. And we found a variety of bacterial orders that are found in and on our worms. But surprisingly, 70% of all the bacteria found are only unique to the worm and have never been found in microbial structures previously, meaning that these microbiota are possibly living in symbiosis with these nematodes and offering a variety of functions, such as phototrophic potential, solute accumulation, and arsenic tolerance that allows them to be capable of living in this extreme environment. So by identifying and reporting these communities, it can help us understand mechanisms that maintain a functional ecosystem in some of the most extreme environments on Earth, and could provide information about the evolution of life on Earth and also beyond. I'd like to thank my lab for all of their help, and thank you today, and I'll be at poster 4 if you have any questions. Thank you.
All right, thank you, Madeline. Up next, we have Fernanda Jamel from the University of São Paulo.
Hello, I'm Fernanda. I'm a PhD student from University of São Paulo in Brazil. And I'll talk about my work, microbial-mediated carbonate mineralization from Lagoa Vermelha, Brazil. So the motivation for this work is the importance of studying the evolution of life on Earth, as we know that the first signs of life are laminations and fossils of microorganisms, and within this we have the investigation of potential evidence of life, such as microbial fossils and stromatolites, that we need to differentiate from mimetic form of an inorganic mineral. So therefore, it's necessary to investigate the biogenicity, that is, that if that was actually formed by life or not. And also we have the dolomite problem. That is a major question that scientists have been studying in this region of Lagoa Vermelha. So calcite and dolomite are one of the most important records of rock from the past, and even if with the several studies related to dolomite formation, the results are still controversial, mainly due to the little understanding that exists and the difficulty of obtaining this mineral in laboratory conditions, like below 50 degrees Celsius. So given this, we have the so-called dolomite problem, which has been much debated over the last few years. However, it is possible to find a few current dolomite precipitation events in hypersaline lakes and alkaline environments, such as this region of Lagoa Vermelha and Brejo do Espinho, that is next to each other. And these are one of the few places in the world that has dolomite precipitation today. So in these places, there are microorganisms responsible for mediating the carbonate precipitation, which can serve as a nucleation centers for the mineral within their biofilm, their EPS, exopolymeric extracellular substance. And this photo was taken during my field collection, and it shows there a thick layer of dolomite sediment below, and above we can see like a microbial mat with a biofilm on the top. So talking briefly about bioprecipitation by microorganisms, in nature, environmental conditions modulate the communities, and within that, a lot of microorganisms, they are known for their ability to precipitate minerals. So these minerals can be precipitated by physical methods in which the microbial community serves as a nucleation site for the formation of carbonates, or it can be in a chemical way or as an inorganic mineral. So this precipitation occurs mainly due to changes in the pH, the amount of organic carbon dissolved in the medium or the environment, and the availability of calcium and magnesium ions in the case of dolomite, and the availability of nucleation sites for crystal formation that can be the exopolymeric substances present in the biofilms of bacteria. So some microorganisms have the ability to produce biofilms formed by these extracellular polymeric substances, which are mainly composed of exopolysaccharides, acidic residues, sugars, that have a negative charge and can bind to divalent ions such as calcium and magnesium. So the role of the EPS in the precipitation of carbonate occurs in two fronts. Initially, the EPS can reduce precipitation by sequestering metallic ions, but during the degradation of the EPS by some sulfur-reducing bacteria, the resulting high concentration of calcium and magnesium ions can favor precipitation. And in addition, the continuous supply of ions added to a more alkaline environment due to the microenvironment generated by the EPS may favor the bioprecipitation of these minerals. So now moving to the astrobiological importance. It's interesting to know that the environmental condition of Mars in the Noachian Hesperian period was similar to Earth. So at that time, it had a much denser atmosphere, higher temperatures, and the possible presence of liquid water on the surface, which indicates the potential of the planet to have supported microbial life. So in the face of it, some geological studies of G0 crater on Mars have demonstrated large carbonate deposits in the west region of the crater. And on Earth, regions of hypersaline shallow lakes are closely related to the biological deposition of carbonates, indicating great potential for identifying preserved biosignature in these regions. So I will just pass quickly through these objectives. So my objectives are testing carbonate mineral precipitation using allophilic bacteria from Lagoa Vermelha, and do structural, morphological, and optic investigation of carbonate minerals like X-ray diffraction, Raman spectroscopy, synchrotron light techniques, and then establish viable protocols for biosignature identification. So briefly, you can see more in my poster. For the precipitation experiment, the methodology of Montanelli, that is a reference that studies this region, was used to test if metabolically inactivated cells within biofilm could precipitate minerals only with the biofilm. So the experiment was carried out in a controlled environment at 30 degrees and was divided into these conditions that we had the EPS treatment that we let the bacteria growing for 15 days. Then we added the antibiotics to inactivate the cells with the biofilm form. Then we had the bacteria growing normally. Then we had a treatment with antibiotics being added from the beginning. And we had the control without bacteria. So we did this experiment to test if this was possible to form precipitates only with the biofilm. But we saw that we found viable cells after some time of experiment within this biofilm. So I think that it's really hard to inactivate cells in this way. So we are trying other protocols, and here is only my preliminary results, just giving a brief about this. I'll talk in my poster. After obtaining these precipitates, we analyzed the X-ray diffraction to identify the mineral phases present in the sample of the bacteria Idiomarina, the strain Kolb. Here in the right, we took a scanning electron microscopy of the precipitates from the same bacteria, and we can see the different morphologies such as dumbbell shapes and rounded shapes of calcium carbonates, and these morphology are usually associated with biogenic minerals. So we still need to analyze EDS spectrums to further confirm more exactly which mineral each morphology relates to, and finding minor shifts in the diffractograms and the Raman spectrums for establishing viable protocols. So this is my poster session, 22, and that's it. Thank you so much.
Thank you, Fernanda. All right, next, we're going to welcome Miriam Fernandez from the University of Colorado, Boulder. Thank you.
Hi, I'm Miriam, and I'm here to talk about the salts of the Earth and how they could help when looking for life in the solar system. Earth can provide us with analogs that can mimic exoplanetary environments, and one of the ones most often used for Mars is the Atacama Desert. I'm really proud of this graphic. So in the Atacama, life has been shown to live off the deliquescence of salts, but can the salts that I studied deliquesce in Atacama conditions? So for my project, I tried to answer 2 scientific questions. Could nitrate salts or their salt mixtures uptake or release water under Atacama environmental conditions? And could the temperature and relative humidity values lead to nitrate salt deliquescence? So to answer this, we used a Raman microscope attached to an environmental cell in which the temperature and relative humidity could be controlled, and we used this to study the phase transitions of our salts of interest. So we can answer our first question. Could nitrate salts or salt mixtures take up water under Atacama conditions? Well, yes, and thank you for coming to my talk. But let me tell you why. And so the first thing that we're going to do is look at the spectral series of the pure magnesium nitrate. So if we look at the crystalline nitrate, which is going to be shown by the black spectra at the bottom, it starts off at a higher wave number of 1062, and as we decrease the temperature and increase the relative humidity, it's going to stay there until it reaches the deliquescence relative humidity of 63%. At which point it shifts to lower wave number of 1052. So it's going to stay here, and this is really cool. It's going to stay here, and as we increase the temperature and decrease the relative humidity, it stays at that lower wave number until the efflorescence relative humidity of 23%, and that means that magnesium nitrate, the pure one, can maintain a metal-stable brine for over a 40% RH change range. So we repeated these experiments multiple times over different temperatures, and we made this lovely phase diagram. And it's as temperature versus relative humidity. So for the pure magnesium nitrate hexahydrate, the deliquescence is going to be shown by the blue dots, and the efflorescence is shown by the orange squares. And it was relatively temperature independent and occurred around 25% RH. So magnesium nitrate exhibited a very large hysteresis, which you can tell by the gap between the deliquescence and the efflorescence relative humidity. And this is going to be our metastable brine region. But I also mentioned salt regions, so what about them? So we did the exact same experiment, but we used different salts. So we have magnesium nitrate, so this is a 1-to-1 mixture, and we have magnesium nitrate on the left and magnesium perchlorate on the right. And we see that same shift in the nitrate peak, which we use to determine when deliquescence would occur. And so we took different ratios of perchlorate and nitrate, and we looked at how the perchlorate could influence the water uptake of the nitrate salts in the soil. And so the blue dots, once again, are going to be the deliquescence, and the orange triangles are the efflorescence. And then the lines in between is the average of the experiment. So what we can see is that perchlorates seem to be helping or assisting with the magnesium nitrate water uptake or deliquescence. And so if we look at our overall picture, so this is pure magnesium nitrate, and its deliquescence is at 60% RH. However, if we look at our perchlorate mixtures, we can see that the water uptake seems to be assisted by that, and we see this with the downward facing trend. So we also wanted to look at what effect a less hygroscopic or deliquescent salt would have on that. And so we did a 1-to-1 mixture with sulfate nitrates, and we saw that this did not inhibit the water uptake of nitrate because it's still below the deliquescence relative humidity of magnesium nitrate. So finally, we can answer our last question, which is, could the temperature and relative humidity values lead to nitrate salt deliquescence in the soil? So we took our phase diagram and we took relative humidity and temperature data from these 2 sites in the Atacama Desert, and both of these sites contain nitrates perchlorates in the soil composition and also sulfates. So site A, which you see above, was relatively close to the ocean and was therefore warmer and more humid. This was likely a contributor to why the nitrate salts in the soil could maintain a stable liquid brine, which is shown by the dark blue highlights, and a metastable brine, which is the light blue highlights, throughout most of the year. Then if we look at site B, this was more inland and therefore significantly drier and colder. But despite this, we do have points throughout the year in which the salts could uptake and deliquesce and maintain a metastable place. So of course, this is very highly variable, and that could be due to the different environmental conditions as well as the different soil compositions, and would need to be further studied. So if you have any questions, comments, concerns, or a job, please stop by my poster, which is number 23. So thank you.
Thank you, Miriam. I like the splash of humor in there. Keep us awake this time of day. So next we have Povilas Simonis from the University of California, Santa Cruz.
Hello, everyone. I'm Povilas Simonis, postdoctoral researcher from Lithuania, currently located at Santa Cruz, and my professor is Dave Dimmer. So, organic compounds, including building blocks of life, may be synthesized in the accretion disk of newly forming solar system and may fall down to Earth as a meteorites and dust. Phosphates, ribose, and all nucleobases were all found in meteorites, and under certain conditions may recombine into nucleotides, which are present in all contemporary life. Another essential compound is lipid, which is a membrane-forming amphiphilic molecule. And simple lipids were also found in carbonaceous chondrites, and even though their structure was way more simple, they can form vesicles. So if these compounds fall down to the oceans, they are lost in a dilute buffer. But if they make it down to the surfaces of volcanic landmass, they get a shot at participating in the origin of life. So compounds falling in from space, synthesized in the biogenic atmosphere, cooked up in hydrothermal systems, or through rock weathering, may accumulate on the surface, perhaps finding their way in a volcanic caldera. The key to getting things to interact is concentration. So small, hot spring pools may be perfect place to cook up some soup of life. And hydrothermal fields of interconnected pools could not only concentrate the compounds, but intermix them between reservoirs, subjecting them to different temperature, pH, elemental and mineral compositions. And for any system to move from simple to more complex one, it must be subject to cycling. And flows of compounds, including building blocks of membranes and polymers, may find their way into a pool, which fills up by a pulse from nearby geyser, dries down, and fills up again. A cycle or an engine is then formed when a polymers between dry lipid layers are synthesized. And during rehydration, they may assemble into membrane-bounded protocells. And the stabilizing effects of polymers and membranes allow the protocells to be tested with some surviving next dry down. As the protocells aggregate together, they form gel-like phase where metabolic cycles can arise. And as a grade fully dries down, the protocells are merging and forming lamellar structures where polymers can resynthesize, template, and allocate. So after many such cycles, simple biological functions can emerge, which simple biological functions can emerge. These ideas are backed by many studies. And here you can see a model of lasagna of life, where nucleotides are trapped between layers of lipid membranes. And such structures are confirmed by a X-ray diffraction experiment. And the trapping of nucleotides between the layers are beneficial because such structures allow prepolymers to form. And not only that, here you can see that blue lines are with lipid present, and if we compare the depurination reactions, which are degradation of purine nucleotides, in the samples with lipid present, those reactions are really inhibited. If we cook up such lasagna at sufficiently high temperatures, you can see in the last graph at 90 degrees, the nucleotides can really undergo condensation reactions and become, well, oligonucleotides, so RNA or DNA-like molecules. And the most important message from all this presentation is that this is a real system. Like, you can take your prebiotic soup and go to Kamchatka or New Zealand or even in California to hot spring pool, pour it down, and after a couple of cycles, you will see like real protocells with oligonucleotides, which are of sufficient length to already have enzymatic functions. So my goal for the rest of the year is to use nanopore sequencing to study those sequences to check whether I can find some functional ones. So these ideas and results brought our team to SETI, where we are running a Genesis engine, which is simulation chamber of volcanic landmass with a lot of pools where we can test different conditions. And our goal is to understand what fraction of habitable planets are actually urable. And by urable, I mean in what fraction of habitable planets the life can actually start. Not many people are talking about that, but conditions for life to start will be very different than the conditions which are needed for our life to thrive. Yes? So if you are interested in this project, you can learn more on the SETI website, and I invite you to stop by my poster where we can discuss how we can cook some soup of life and maybe even start a second Genesis. So thank you very much.
All right, thank you so much. Now I'm craving lasagna. Up next, we have Michaela Leung from the University of California, Riverside.
Alrighty, hi everyone. Thanks for having me today. My name is Michaela Leung. I'm currently a PhD candidate at the University of California, Riverside. I'll be talking to you today about my work on novel methylated biosignatures and specifically their application to exoplanets, which I usually don't have to say because I'm usually talking to astronomers, so that's kind of fun. There's a little bit of a breakdown diagram here on the far side. That's my left, so your right. That's kind of showing the processing of these molecules all the way from surface fluxes, atmospheric chemistry, the production of spectral features, and we're kind of thinking about how this will vary across a variety of stellar types. So that's kind of just a very quick summary breakdown. So let's jump into talking about why we're specifically interested in these methylated gases. And the answer is largely that there's a major false positive problem for the first biosignature detections. A lot of molecules like oxygen, ozone, methane, things like that, that we expect to be potentially potentially the first molecules detected that could be connected to life in terrestrial exoplanet atmospheres can also be produced by a variety of planetary processes, including thermodynamic equilibrium chemistry. And so these methylated gases are specifically almost exclusively produced by life, and all of the other pathways that we've investigated have been very minimal. So we're really excited that these gases could potentially be a very strong affirmative signal of life. And these gases are generated by the process of volatile methylation, which actually we believe to be a descendant or perhaps a relative in some way of the process of DNA methylation, which for you biologists out there, I'm sure you're all much more familiar with than I, but we see volatile methylation in a variety of different ecosystems, including microbial mats, the open ocean, and primarily actually a lot of terrestrial marine kind of crossover ecosystems. We also see it done by a variety of organisms, primarily single cellular life, but we do also see everyone's favorite brassica vegetables also produce methylated gases. And we think in particular that methylation is connected to the process of environmental detoxification, and that the need for life to kind of control its environment is possibly a fundamental characteristic of life itself. And so when we're thinking about, what life might look like under fundamentally different biogeochemistry, it's probably still going to need to be controlling its surroundings in some way. So we're really excited about that potential tie-in as well. We're not the first people to think about methylated biosignatures. There are previous studies, specifically Segura et al. 2005 and Domagal-Goldman et al. 2011, which specifically show, 1, an enhanced buildup level around M dwarfs, and 2, a secondary ethane biosignature that's produced by atmospheric photolysis of dimethyl sulfide and dimethyl disulfide. And that produces a potentially detectable ethane signature. And so we're going to follow a relatively similar pathway. We're jumping from lab land that we've been in for the last couple of talks to modeling land. Primarily, we're going to be talking about photochemical and spectral modeling, basically thinking about how these gases are processed in the atmosphere and what those potential signals might look like. Just jumping into some results, we have first here methyl bromide, which is, again, on your left, and we have methyl iodine, which is on, I think, your right. And you'll notice that, as I said before, for methyl chloride, they see an atmospheric buildup level that's much higher around these M dwarf cooler redder stars, and we actually see that buildup replicated and actually even more enhanced for methyl bromide. And this result for methyl iodide is from literally last week, so that's brand new. And we're also seeing, again, the same sort of enhanced buildup. You'll notice that it's to a lesser degree, and we think that's probably because it's just a larger molecule, and so it's a larger molecule, it's going to be hit by more potentially active photochemical light. So we use this photochemical model to create profiles of gases in the atmosphere and kind of figure out where everything is, where it's at in the atmosphere. And then we're using, like I said, a series of spectral models. So these are mid-infrared emission spectra. And the most important thing that I'll call your attention to here, there's kind of a lot going on, but the bottom row is actually showing an experiment that we did where we add multiple methylated gases, in this case, methyl chloride and methyl bromide. And you'll actually notice that the features that we see, especially for Proxima Centauri, which is going to be that plot all the way down in the bottom corner, that feature is actually a little bit wider and a little bit deeper than just kind of the simple sum of the features. And that's partially because we're doing self-consistent photochemistry, and so you do get higher buildup levels, and also because this absorption feature near 10 microns is actually the C to halogen bond, and so C to chlorine and C to bromine are sort of next to each other and overlapping a little bit, but really creating this much larger feature. And so we're optimistic that a future telescope capable of mid-infrared emission spectroscopy could detect these. And we also think that while this could detect a methylated gas, we could potentially fingerprint a specific methylated gas using extremely high resolution ground-based spectroscopy. And potentially one mode that we could use for the emission spectroscopy that I was just showing is the LIFE telescope, which is a concept mission that's actually run by the European Space Agency, where they're using interferometry to essentially get a larger approximation of a telescope rather than putting like a 100-meter telescope in space, because that's actually going to be very difficult to do. And so you could see here that there's simulated error bars for the observations, and that there's kind of a noticeable difference between the atmospheres without these methylated gases and especially the higher flux cases. And we can also look at this as a kind of comparison to the sigma of the detection, and you can see we get some pretty significantly large features here, and we're optimistic again that if any biosignatures are detectable on these planets, these are very optimistic planets we're simulating for, but hopefully these methylated gases will be among those biosignatures that it's possible to detect. So I will leave you with my conclusions. I think I am right on time. I'm at poster 9, which is right on the other side of this wall, or you could feel free to contact me. My information's on the slide.
Thank you, Michaela. Up next, we have Jordan McKeag from Georgia Institute of Technology.
Great. Hello, everyone. My name is Jordan McKeag, and I am a PhD candidate at Georgia Tech. I'm working with Dr. Chris Carr on using solid-state nanopores to detect biosignatures and think about potential for agnostic life detection. So throughout our universe, or throughout our solar system rather, there are a variety of planetary bodies that have conditions thought to be hospitable for life. So things that are in the middle of this Venn diagram containing the right raw materials, energy sources, solvents, and climate conditions for living things to possibly persist. Many of these environments are aqueous and saline environments. And as we've discussed previously, today and yesterday, salts have a major influence on the ability of an organism to live in an environment, as well as the potential for biosignature biosignature preservation. And I'm particularly interested in how salts can interact with these biomolecules in terms of doing detection with nanopores. So specifically the biosignatures that I'm interested in are nucleic acids and ribosomes. Nucleic acids, that's your DNA and RNA. It's a linear charge polymer that is responsible for storing and regulating genetic information. Ribosomes are cellular machinery that translate this information into usable proteins. Nucleic acids and ribosomes are ubiquitous to all known life and are part of the central dogma of biology. So this is a paradigm in biology that traces the flow of information from these charged polymers of DNA and RNA through proteins. So it's been proposed that molecules of similar structure and function, but different biochemistry from some of these things could actually serve as evidence for life as we don't know it. In 2017, it was proposed that linear charged polymers with repeating units, analogous to nucleic acids like DNA and RNA, could serve as an agnostic biosignature. And we are also working on a paper arguing that translation-performing molecules of a quantized size, analogous to ribosomes, could similarly serve this function. Since these don't have the same biochemistry of life as we know it here on Earth, it would require detection with a method that doesn't necessitate any specific chemical composition, which leads us to solid-state nanopores. This is an agnostic mode of detection, which requires a molecule to be suspended in a conductive solution. So your nanopore here is a nanometer scale pore that's drilled into a membrane. A current is passed over it, and a voltage or a pressure differential drives molecules through the pore. As things go through, these translocations create blockages in current, which can be used to get information about the biomolecules. And I just want to highlight, again, this does not require specific biochemistry, making it exciting for not only investigating living things here on Earth, but also potentially elsewhere in the solar system. So what we did was show a proof of concept for something called the Ontera nanocounter, which was a proprietary solid-state nanopore instrument. And these are all of the different biomolecules that we analyzed, including some DNA samples, RNA, and ribosomes. And if you'd like to hear more details about how specifically this went down, please come talk to me at my poster. And then also I have some of the example results. So first we have a few graphs showing just different example events with signature-specific events for each biomolecule structure, and then some heat maps showing the change in conductance and the dwell time for all of the events in a specific run, and then some overlaid samples of what all of these events looked like. And what I just want to highlight here is, let's see, do I have? Okay, great. I have overlaid DNA events all here in the blue. This is a circular plasmid, so just a circular piece of DNA. And it is a pretty short dwell time, but also a much larger change in current. And this is probably due to the circular structure instead of a linear polymer. So when you have a circular piece of DNA going through the nanopore, you would have 4 strands of DNA instead of the 2 strands that's in a regular linear fragment. Similarly, for linear fragments, we have these 2 right here, with this one in red being a shorter fragment and the one in black being a longer fragment, which is reflected in that longer dwell time. And then I also have the data for the ribosomal detection. So there are a few key classes of results here. The ones in box A, we interpreted as being intact ribosomes since they were larger, and then things in box B would have been smaller particles, which we actually think were ribosomal fragments. So we thought that maybe we had some issues with the buffer causing that precipitation, which allows us to not only analyze the exact intact ribosomes as well as fragments themselves. So if you'd like to hear more, please come talk to me at my poster. I'll be at number 19, which is kind of over by the window. Thank you all.
Wonderful. Thank you so much, Jordan. Up next, last but not least, Justin Park, coming from Rensselaer Polytechnic Institute.
Hello, everybody. My name is Justin Park. I'm a second-year PhD student at Rensselaer Polytechnic Institute. And one thing we're interested in doing in our labs is reconstructing ancient atmospheres as they pertain to important evolutionary steps in our atmosphere's history. So what I do is I look at ancient atmospheres trapped in halite fluid inclusions. So halite, as we've seen in previous talks, is an evaporative mineral. It forms in these really dry, arid environments where evaporation is the dominating force. As it does so, it can form these things called fluid inclusions, as shown on the top right up here, and they can encapture air or brine in the mineral matrix. Now, these can be primary or secondary, meaning they form at the time the mineral precipitates, or forming sometime later with some secondary fluid event. And oftentimes, they form in assemblages of hundreds or thousands of inclusions at once. Now, what I'm interested in doing is looking at the gases that are trapped in these primary inclusions and saying something about the evolving composition of the atmosphere. Now, we do have some evidence for what we think the atmosphere looked like and how it evolved. Here I have plotted one of the major models suggesting the change in partial pressure of nitrogen, oxygen, CO2, and methane as a function of time, starting with the moon forming event 4.5 billion years ago. Now, if you'll notice here, there is a lot of uncertainty in these measurements, and this is due to them being made with indirect proxy measurements. Now, also, in the period between 2 and 1 billion years ago, here, we have this period known as the Boring Billion, and it's aptly named for the apparent stagnancy of the atmospheric evolution. Now, what we're interested in doing is providing ancient atmospheric constraints using fluid inclusions in the period between these 2 points, using direct analysis from 1.4 billion-year-old fluid inclusions. So we can do this by loading our samples into a special crushing device, crushing them. This ruptures our inclusions, and we can pass the gas directly into a quadrupole mass spectrometer. When we do so, we see peaks in our signal that correspond to each crush. These peaks can be integrated and quantified by comparing to known calibration points. Thus, we can get an idea of the composition and known amount of moles of nitrogen, oxygen, argon, and CO2 present in these inclusions. When we backtrack and calculate the ancient atmosphere composition, we do have to be wary of any aqueous contributions. As we know, Henry's law tells us this atmosphere may also be dissolved in the brine phase in its equilibrium. So when we did this, we saw some variability in our results. Here I have plotted the mole fraction of nitrogen, oxygen, argon, and CO2 as a function of the size of each sample. One thing we can notice is that the primary and secondary inclusions do capture different atmospheres that are distinct from one another. Now, we're very interested in the primary inclusions, as that's the environment that the mineral formed in, and we can compute an average partial pressure or density of each gas and compare it to the modern atmosphere. When we do that, we saw some very interesting things. Back 1.4 billion years ago, we found atmospheric nitrogen was roughly the same partial pressure as it is today. Atmospheric oxygen was around 1/10 as dense, argon was about half as dense, and carbon dioxide was actually 8 times more dense. Now, each of these gases has really important implications, but due to time, I'm only going to have time to talk about oxygen today. So when we looked at our oxygen results, our measured partial pressure revealed some pretty interesting things. Here I have it compared to many of the predicted models that have been proposed. What we saw is that we captured more oxygen than these models would have proposed. This indicates that these direct measurements might be able to capture things that the proxies are unable to. And this has some pretty important implications. The oxygen that we measured is above theoretical lower limits necessary for the early evolution of life, and it's also in agreement with some evidence suggesting there was a developed ozone layer at this time. Now, on the right here, I have plotted a phylogenetic tree showing the marked diversification of red algae in the Mesoproterozoic. Now, red algae are very important as they're some of the first photosynthetic eukaryotes. That gives them an evolutionary advantage to produce more oxygen than their predecessors. And this becomes really interesting when we compare this to our timing of the deposition of our samples. We can see they're roughly contemporaneous, and thus our elevated oxygen measurements are likely due to the presence of these red algae. So I hope I've shown here today that the atmospheric oxygen here is pointing a more dynamic picture of the boring billion, and it might not have been so boring at all. We have important implications of these ancient red algae evolving at this time period that led to this. So with this, I hope I've shown that fluid inclusions can capture and maintain direct evidence of ancient atmospheres for hundreds of millions of years, if not billions. With mass spectrometry, we can probe the contents of the gas that are trapped within these, and we can look into how the atmosphere has evolved. We aimed to make compositional measurements of the atmosphere 1.4 billion years ago, and we found something very different than our present atmosphere. Hopefully, in the future, we can make isotopic ratio measurements and see any further evolution trends. So with that, thank you all for listening. If you have any questions, I'd be happy to talk to you at my poster, number 14, after this.
Wonderful. Thank you so much, Justin. All right, guys. So our final poster session of the conference will be beginning just now out here, and we will meet back here at 3:30 for our sadly final talk session, technosignatures and life detection. All right, we'll see you then. And I want to say one more time, if anyone is interested in having a party like we did, come and talk to one of us, okay? Thank you.
Thank you.
But before we start the talk session officially, Jaime Cordova would like to make a quick announcement. So I'm going to welcome him up for that.
Alrighty. So hi everyone. So I'm Jaime. I'm at UW-Madison. This is Rachel from UCR. We are both part of the Early Career Committee for the New Life Research Coordination Network. Just to make you all aware, so Life Research for the Life RCN is the newest RCN, part of NASA Astrobio. We are a network of astrobiologists focused on the evolution of on the coevolution of Earth and life. We are looking to explore ways to advance this science and its implications for the search for life on other worlds. We just wanted to make you all aware of this. You can see our website here. We have a Twitter, and we also have a YouTube channel where we have our seminar series. The QR code that is on the screen right now is for our main website, but we do have a seminar series that we started. We just had our first seminar series last month. Actually, no, this month. We just started in May. Our next seminar will be taking place on June 5th. This is by Dr. Maria Rebolleda Gomez from UCI, and she'll be talking about innovations and constraints, evolution of metabolic rules and their ecological relevance. You are welcome to scan the QR code that's there, and that'll take you to our Resume registration. It is all virtual, and it's going to be taking place on the first Monday of every. Anything else you want to add?
As many of you know, we also have stickers for the Life RCN, so if you would like one, come see one of us.
Yeah, we've probably already given out like
a lot,
100 of these, but if you want more, we've got more. So, well, you're welcome to come get some from either of us. And if you have any questions about the Life RCN, please come up to us, and we're happy to talk about it. Cool. Thank you.
All right, thank you so much, guys. And we already have our first presenter on standby. I'm here to welcome Rachel Surprenant from the University of California, Riverside.
Great. Hi, everyone. So my name is Rachel Surprenant. I'm a PhD candidate at the University of California, Riverside, and today I'm going to be talking to you all about the sedimentological signatures of mat grounds in the Precambrian, a novel method for their detection, automated detection in remote contexts, and implications for the search for life on Mars. So it's well accepted that in Mars's past, there was liquid water on the surface, right? So this provides the potential for there to have been past microbial life. And when we're thinking about looking for evidence of this past microbial life, a lot of people in this room like to think about signatures of this microbial life that are microscopic or molecular. But as a paleontologist, I'm more interested in macroscopic textural signatures that we can observe in the sedimentological record from standard imagery, right? So to find these types of signatures that could be useful for the search for life on Mars, we can turn to the Precambrian Earth, which is a really useful data set for us to think about how past microbial life expresses itself in the sedimentological record, because it is dominated by a record of organic mat grounds during a time when life on Earth was very simple, right? And luckily, these organic mat grounds formed by a consortia of prokaryotes and eukaryotes, mainly single cellular, have a significant impact on the sedimentological record. We heard earlier today about something called the extracellular polymeric substance that microbes excrete when they are forming a mat ground. It's just kind of this like sticky substrate, and this has an impact on the sedimentological record in that it binds, baffles, and traps sediment that it is living on and within, and thus prevents erosion and stabilizes sediment. In part, this contributes to in carbonate settings, things that you're probably familiar with, like microbialites and stromatolites. But I'm more interested in how this is expressed in siliciclastic settings, which is broadly applicable to the Martian geologic environment, right? And one way that it can be expressed is in textured organic surfaces or iterative organosedimentary surface textures. I'm showing you an example of that up here on the right. That's actually a fossil surface. And they also impact sedimentological packaging in a way that we can identify in cross-section. So when I'm talking about kind of these background biosignatures, I think this brings up a really important question that I want to kind of frame my whole talk in, which is that if life ever existed on Mars, was it ever abundant enough to form organic backgrounds and impact the sedimentological record on a macroscopic scale like we see in the Precambrian? And my answer to that is, I don't know. And the more I think about it, the less I'm convinced that it ever did. But this is still an outstanding question that we need to think about, and there's one way to find out. And again, this is to leverage the Precambrian rock record. So as I mentioned, we have billions of years of evidence of mat grounds existing in the Precambrian, a lot of which is fossil evidence of mats, like what I'm showing up here on the right. These are not great biosignatures for the search for life on Mars because to identify them, you would need to excavate bedding planes, and it also relies on the fossilization of these surfaces that necessitates a lot of a suite of complex taphonomic or preservational processes that are not guaranteed to have existed on Mars. So instead, I'm interested in looking at the impacts of mat grounds and the extracellular polymeric substance that they secrete on sedimentological packaging as it manifests as discrete sedimentary structures that cannot occur in the absence of biological mediation. So one of these sedimentological signatures that I'm talking about today are called palimpsest ripples. So I'm showing you images of those here. These are from the Nilpena Ediacara National Park in South Australia, which was recently opened as a national park. Oh, my animations are weird, sorry about that. But if you want to read more about it, it was published a little story about the national park in NASA Astrobiology recently. But palimpsest ripples are defined as stacks of sandstone bedding planes that have rippled bottoms and rippled top surfaces. So we can see if we look at this bedding plane here, there are ripples preserved on the top as well as on the bottom. But what does this mean in terms of like evidence for life, right? We can look at this figure here to see kind of the biological processes behind the formation of these palimpsest ripples. So looking at section B of this figure, when we think about Precambrian ecosystems, microbial mats were ubiquitous within the world's oceans, covering the seafloor. So when these mats grew on the seafloor, what they would do is stabilize the rippled surfaces. So when a new depositional event occurred, the ripples were not eroded and are thus cast on the base of the new depositional event. And then the two bedding planes remain as discrete bed forms that are not amalgamated together. So this then continues as a process resulting in stacks of these sandstone bedding planes with no fine-grained inner beds, and is a definitive signature of past life that cannot occur in the absence of biological mediation. So this is potentially a really interesting biosignature for us to keep in mind when we're thinking about the search for life on Mars. And just you can compare it to kind of modern processes or broadly Phanerozoic conditions where we don't have mat grounds. If you get the deposition of sandstone on sandstone, the ripples are going to erode and the bedding planes are going to become amalgamated, resulting in a cross-section something like this. So you can tell that they're very distinct cross-sections, one with definitive evidence of past microbial life. So all in all, we can see that palimpsest ripples are potentially good biosignatures for us to keep in mind because they cannot be formed by abiotic processes. And they can occur when a mat is very thin, so they can even occur under biofilm mediation, so where it's not dependent on the presence of eukaryotes. And they're easily identifiable as macroscopic features in standard imagery, so you don't need a ton of analytical methods to identify them.
But this is not to say there are no limitations, right? Firstly, this is restricted to rippled facies. You have to have ripples occurring in order for this to be identifiable in cross-section. But we know these are preserved on Mars, so this doesn't preclude the use of this feature as a biosignature. And additionally, the lithological criteria is narrow. You have to be able to identify the fact that this cross-section is comprised of only sandstone and no like clays or silts. But again, this is an ability we have to ascertain on the Martian surface. So with this in mind, we can kind of think about, well, then how would we detect them, right? I could go through by hand and look at all of the images coming out from the Mars Perseverance rover, but that's time consuming, right? So there's some things we need to consider in actually using this as a biosignature. First, there's a large number of images. We would ideally like to have rapid identification of these features, like as the images are taken, so we can identify target sites of interest for further analysis, because palimpsest ripples alone will not be enough evidence for us to be like, oh, there was life. You would need expertise in backgrounds and their impact on the sedimentological record. And of course, you want to minimize human error. So with all of these caveats in mind, I was kind of thinking, maybe the best way for us to approach this problem is to use an automated technique to identify palimpsest ripples in images of cross sections. So this is exactly what I did, but I am not an expert in this, so I collaborated with the Visualization in Intelligent Systems Laboratory, or VisLab, in the College of Engineering at UCR, and worked with Dr. Birbanu and Padmaja Janalagada, who did a lot of this work with me. And the first thing I did was show them my data set from the Precambrian sedimentological record we had starting about 200 images of palimpsest ripples, because this project was born in COVID and I had no access to the field. So we started with this relatively limited data set and identified caveats of the data set that the program would need to overcome, including variable scale of images, variable resolution of images, and it would need to have the ability to account for extraneous features that are not related to palimpsest ripples, like plants, fractures, talus, dust, and shadows. And all three of these problems are problems that we would also have in like Mars, or images coming from Mars, besides the plants. So we started developing this program, and phase 1, we developed the scene-aware perception augmentation using composite embedding for segmentation, or SpaceEgg, which uses Cora and SGE to identify images, palimpsest ripples in images of outcrop. So these are just kind of a schematic of those different methodologies. If you're interested in the actual computer vision aspect of it, I encourage you to look at our paper, Janalagada et al. 2021. And this first pass, our phase 1 development, was able to identify palimpsest ripples in cross-section. So you can see in the pink box, that is SpaceEgg, and it outperforms other state-of-the-art techniques for identifying planar features in imagery, and identifies palimpsest ripple bed junctions with an 89% accuracy rate. But 89% is not that great. We thought we could do more if we had more images. So once COVID restrictions lifted a little bit, we took 800 more images to kind of do phase 2 of this project, wherein we developed SpaceEgg 2.0, which instead used a combination of Aurora and BaseNet, shown here. This paper is currently in review. And this gave us a 92.32% accuracy, so much improved. And again, we see that it outperforms other techniques as well as our original SpaceEgg. So you can see it's much better at segmenting out the planar features that we are interested in and like really concentrating on the regions of interest. So to kind of conclude, palimpsest ripples are an important and definitive biosignature that should be included in target structures on Mars, and we have developed a technique for accurately detecting them using automated methodologies, which is potentially useful for our search for life on Mars. And just to say, our next steps, this project is not done. Our next step is to develop a classifier where we can feed through a bulk of images of different geologic features. It will be able to sort out between likely palimpsest ripples and non-palimpsest ripple cross-sections. And then those likely palimpsest ripple cross-sections will be fed into SpaceEgg 2.0, and that will give us a probability of the presence of palimpsest ripples, and we'll also have the ability to classify morphology and other aspects of these features. So with that, I would like to thank my funding sources, as well as everyone who contributed to this project through taking imagery or ground truthing. And I would like to thank Ross and Jane Farger for access to the Nolpini Ediacara National Park on their property, and acknowledge that this land lies within the Adnyamathanha traditional lands. And again, there's a QR code for the Life RCN. Thanks.
Okay, fantastic, Rachel. Do we have any questions? See, this hand came up first, I think.
I was wondering, first of all, thank you for a great talk. I was wondering, does anything about those ripples and texture or any other factors change over the course of the Precambrian? So like, are there any connections like major events like oxygenation or other things? And if so, like, can we infer anything? Can we infer any, like, make any past climate inferences for something like Mars?
This is a really good question, and talk to me after I finish my postdoc.
I will.
Anyone else?
So I'm wondering if there's any images from Mars that this can be applied to now, or we just have to reorient the cameras to sort of start doing that?
There are definitely images that this can be applied to. Like, that's kind of why I'm like harping on this biosignature, because it's like most of our imagery we're getting is of cross sections from the Martian surface. So yeah, once we have the classifier, we're gonna start running them through. From what I've seen, just like looking at them, I don't see anything that would look like it, but it's an experiment we need to run.
I was just wondering if you guys were using any kind of like depth data for this, because it feels like these sort of in the images it looked very like quite 3D, and you know, if you have like two images, some kind of
Yeah, so we did take that into consideration, kind of looking at the depth of the images, and it didn't really change kind of the performance of the program. So I believe it's incorporated into it, but it's not a huge aspect of it.
Thank you.
Yeah.
Okay, we're gonna take one more over here. Oh, Mike is itching to ask a question.
Hi, interesting talk. Kind of similar. Have you ever thought about applying this to like maybe like debated diagnostic like biofacies that are in the fossil record, like just as additional Earth constraints?
I'm not quite clear on what your
Like
question is.
just similar, like at least other like stromatolite or microbial
Oh.
like, systems that like have debated like sources.
Yeah, that's a really interesting question. No, so this is like specifically developed just for like this one feature. I think it is work that other people are doing that are not me. But yeah, there's definitely other like computer vision programs that have been developed to identify similar features.
Thank you.
All right, we're gonna let Mike ask a question. He's been working hard for us back here.
Okay, this is actually my question, not online. I'm just curious, if you did see something on Mars, what would you need to actually confirm that? Could you do it visually, or would you need sample return, or?
Yeah, that's a really good question. From my perspective, I think it's like a first pass ID. I think like it is a definitive biosignature, but I would never want to just like say, oh, SpaceEgg 2.0 said there is like a 99% chance and that's definitive evidence. I think, yeah, sample return or like further analysis of that section would be needed to like really definitively say anything.
All right, thank you, Rachel. Our next speaker is John Malloy from Arizona State University.
Oh, thank you. Yeah, I'm here to talk about a different kind of biosignature, kind of introduce assembly theory. I don't know if this is the right group to be very controversial about it with, or if you guys all accept it. So we're gonna see what happens. But mostly the main reason I'm a fan of this theory, the reason why I talked about it, is that there's two major problems that is currently in the field of astrobiology, at least from my opinion. The first one is that we don't have a universal definition of life. Again, not sure if you guys agree with this or if that's really controversial. No idea. But mostly, we don't know what we're looking for elsewhere. And because of that, kind of the biochemistry that we see, or could potentially see, we have no idea what that could look like comparison on Earth. So kind of what we need to do is find a universal pattern of life first, and then build our detection methods based on that. I think going out there, seeing what we see is incredibly useful, incredibly interesting, but then you end up with like a phosphine problem of how do we explain what we see? If we determine what we're looking for first and then build a method based on that universal property, we're able to be a little more stringent, a little more robust about what we're actually finding. So given that kind of solution, the basic idea of assembly theory is that life produces complex things. For example, if we were to go to Enceladus and find an iPhone sitting on the bottom of the ocean, somehow, unless Steve Jobs flew on a plane and put it there, we would say something in Enceladus made a complex thing, made an iPhone. That's weird. That's interesting. That would certainly be a really interesting biosignature, especially if we saw thousands of them. If it was littered in iPhones, there'd be some kind of process on Enceladus that would create and select for a complex object. So this kind of idea is that life makes complex things, it makes a lot of them. And what assembly theory does is specifically measure that. Give a measure of the complexity, give a measure of how much memory is part of the system that makes something really complex, and a lot of it. So kind of what this is, what we're talking about, is specifically it's a number of joining steps required to build an object from a base set of fragments. That's a lot of words. That's really confusing. So start with Legos and we'll go up from there. If you were to make this thing, like this big square, rectangle, whatever thing, you would start with this green and red block, and you would start joining them together in the most optimal way possible, essentially in a way that minimizes the joining steps to make that thing at the end. Specifically, there's 5 of them here. You notice that you reuse this double a couple times, and you reuse the square once as well. So you're able to reuse the thing you already make. There's 5 joining steps. The MA of this particular Lego block would be 5. And you can do this for lots of different things. You can do this for strings, like Gage was talking about yesterday, where if you want to make abracadabra, you're going to have a number of steps, particularly 7. You're going to reuse abra along the way. And you can do this for chemicals, which is kind of more astrobiologically relevant. You're able to start with your base fragments. In this case, it's a element, a bond, and a different element, which is defined by the thing you're looking for. And you're able to build up the steps along the way. I think one thing I want to emphasize is that these steps don't necessarily have any physical meaning. Like this windmill guy isn't, maybe you can't make this in a lab, who knows? And it doesn't particularly matter for this metric. This is not, I'm saying this is a physical property, it's a theoretical way of reusing the symmetry of the object that you're ending up with. So kind of keep that in mind. When you're doing this is all from paper in 2021 from Stuart Marshall and Cole Mathis, both at the University of Glasgow. And we're able to do an MA over a ton of things. It unsurprisingly correlates with molecular weights, because as things get bigger, you get more steps to make them. But it's not a 1-to-1 ratio. There's a lot of things kind of here that are high molecular weight below assembly theory because they have high symmetry. So they're not necessarily as complex. They require less steps to make. Just, again, keep that in mind. And the reason why we're so excited about this, the reason why we want to use this for an astrobiological signature, is that when you look at these compounds in a mass spec, you're able to see a lot of these different peaks. A mass spec takes a compound, fragments it based on ionization and a lot of different things. There's lots of different ways to do it. This one particularly was an orbitrap, so it fragments things twice, and you end up with a number of different peaks. Now, kind of notice as a correlation, the lower things, the lower MA things, the less complex things, don't have as many peaks as the higher complex things. Again, kind of makes sense. Bigger things are more complex. There's a really strong correlation between the two, which is really, really exciting. Again, it's not intuitively obvious that you have a theoretical measure that has no correlation in physical reality actually corresponds to a mass spec signature. So when we saw this, we kind of ran with this and we're saying, hey, we can put a mass spec in space. We've done it before. We've done it since the 1970s. So why don't we look at what kind of mass specs are needed, think about MA as a specific biosignature, and then use mass spec to go out and find it. And the thing we're looking for specifically, again from this 2021 paper, is that all of biochemistry has an MA greater than 15. Anything below 15, at least we see on Earth, is a mixture of biotic, abiotic things. They're found throughout the geosphere and everything. But above 15 is only things made by things that we know are alive, like whiskey, a few other things. They kind of had some fun at Glasgow measuring a bunch of stuff. But essentially, anything above 15, what we say is, hey, this, from what we know about life on Earth, let's extrapolate it to be a universal property. That's something that's complex. For the rest of the talk, I think this 15, it might be a little fuzzy. I also measured 20. I consider 20 as a specific biosignature. So you'll see two numbers later on. That's where the 20 comes from, is just give it a little wiggle room. So now the issue with that, if we're going to send a mass spec into space, it needs to be high resolution. You can't have something like this where you only have a couple peaks. You need something that has the right number of peaks in order to find something that's high and complex. If you send something that's low resolution, it's not going to be good enough. And when we look at stuff today, you'll see this chart a couple times, so I want to explain it real fast. This is essentially M/Z ratio, essentially a measure of how big the molecule is. And this is the mass resolution of the particular object times 10,000. All of these ones off here are off the chart. Like they just really have big M/Z ratios. And these two would have a really high resolution. So this is good. Now, these things take up rooms. Like an orbitrap's not that big, but you need a bunch of vacuum stuff. Like it's about as big as this podium, roughly, if you want a really good one. You can't just launch that on a spaceship. NASA gets really mad when you launch something that big. So how do we, like the stuff we do today, it's roughly down here. Ricky Yaravalo's group at University of Maryland College Park has this mini orbitrap that's decent, but still still on that scale. So how good can we get? How is that good enough? How much do we need in order to determine definitively that you have a mass spec signature? So what we did some chemical enumeration. We built some graphs, specifically built some formulas, and said, hey, given a specific number of chemicals, in this case 0 to 6 carbons, any number of hydrogens, then nitrogen, oxygen, phosphorus, sulfur, how many different formulas do we get? How big is the chemical space that could potentially be out there? Answer is pretty big. You get lots of different formulas, unsurprising. They can be modeled with a normal curve. So I can do this for any number of upper limit, and any number like up to 10 atoms, up to 5 atoms. If I want to measure more, I can do a different normal curve. This next slide might trigger people. I apologize. I did random chemistry based on that. Because again, we don't know what that is going to look like. So I built random structures from random formulas, essentially putting random bonds together. This might not exist. This probably doesn't exist anywhere. But I kind of hope it doesn't, because that would be weird. But what we did is when we built it, we put it through RDKit's 3D embedder software. So we know this is at least physically possible. It doesn't break the rules of physics. The thermodynamics are really weird. Who knows how long this lasts? But again, our assumption is we don't know what this looks like. And this actually is a good assumption. You'll see a few graphs later that we're not actually that far off from reality, but just bear with me for now. So I did this for 10,000 different structures, made a bunch of random chemicals, and found the MA of them. So we have molecular weight, we have assembly index, and you see that most of them started to get high MA, and you get a likelihood very quickly of, well, what is the likelihood of finding a high MA object at a particular molecular weight. So we have size of chemical space, we have molecular weights, and we know how often those things are high MA. We're essentially able to then put that on a precision curve and say what's the precision, which can be translated into resolution, of the particular number of chemical species that have a high MA in that case, or that particular M over Z ratio. We take the integral of that particular line. Our goal is to find 10 or fewer, just to put a number on it. And then we end up with something that looks like this. So in an ideal case, what we have is something about 552,000 M over delta M mass resolution, which is far fewer than what we have in commercial orbit traps. Those are on the orders like millions, 10 millions. But it's not what we've sent to space. It's about 4 times better than what we've sent to space so far. Those ones sent into space are decent. Like in this little curve here, they're good. They're able to determine high MA molecules, but we still want to get as high up on this graph as possible. So it's more of an engineering challenge. This is more saying, hey, engineers, if you can go out and build something like this, given unknown chemical space, we're confident that you'll be able to detect a high MA molecule if it's out there. And quickly, just to finish up, I know the chemicals were really bad and really not Earth-like. So we determined our resolution based on existing chemistry. We used KEGG, Kyoto Encyclopedia of Genes and Genomes, and mostly saying how good is our prediction based on those random chemicals. This is MoMA. This is the one that's launching soon to Mars. It's not that great at distinguishing formulas. There's a lot of overlaps. But if you look at something like corals or our recommended one, you're really not that bad. You're getting a maximum of 5. So it's pretty good. And even better, when we start saying, hey, does random chemistry correspond with reality? It does, thankfully. Kind of as a test, we took 200 formulas from that formula enumeration, got 100 different isomers of those formulas, both from PubChem, so existing chemistry, GDB, which from John Louis Raymond's group in Bern, which is a generated database of potential chemistry here on Earth, and then random structure generation like we did. And if they were separate, we'd say we have a problem. But all of these, kind of the MA space of all those chemicals is about the same. So we actually end up, roughly, our recommendation on random chemistry seems to be sufficient based on life we see today. So kind of a recommendation, if we take molecular assembly theory as a biosignature, we have a mass range of mass specs to shoot for, we have a resolution, and it's the worst case scenario, and what we're showing is that this roughly represents MA of chemical space. There's lots of people to thank, mostly the ASU group that is mostly sitting at the front table. So thank you very much.
Thank you, John. Any questions? All freaked out by the chemistry.
Hi. Great talk. I'm wondering, why is the random set smaller on the area that it takes than PubChem?
Yeah, that's a great question. I think my answer is that it's possibly a sampling issue of random space is probably bigger, but the density of different compounds that it could sample in random chemistry is just so high on that little part right there. Like I'm just not sampling enough to get a distribution, or I am, and I'm not getting the edges as much. I think it's an interesting question of how life can be a little more spread out. I think there's an interesting functionality argument going on. I think, yeah, random chemistry, I think it's so dense in the middle that I'm just not exploring the edges as well as I could be.
Thanks.
Hi. This is very, very interesting. So I guess, would you mind maybe going over the basically what led you to your resolution and max M over Z calculations a little bit, I guess, more in detail about how that connects to MSMS measurements. Is this just with M over Z, or okay?
Yeah, so yeah, it's a great question. So I'm not assuming any fragmentation here, mostly because we don't know exactly what we're going to send or if it's an MS1 or MS2 machine. So I'm just assuming that there's a particular structure, it's ionized, so a knockoff a hydrogen, and then that's a single peak that you get. What's the resolution to distinguish those peaks? Which one I'm saying this is worst case, add fragmentation in, add like add a decent orbit trap, and this probably becomes a lot better. But it's hard to predict exactly what that fragmentation is. There's a team in Glasgow, led by Emma Carrick, that's like trying to figure that out right now. As you can imagine, it's a difficult, like mass specs are weird. It's a difficult problem to predict and extrapolate.
Yeah, because I guess I'm wondering, obviously, ion neutral mass spectrometer on Cassini did not have nearly this resolution, but if the fragmentation that you can assume happened when those ice grains collided with it could be assumed to be an MS2-like event, then, and if that, if MS2 makes it that much better, then maybe you could look at it from this perspective.
Yeah, no, I think if we had I would love to see a number of how much that correlates. Yeah, I think that's probably the next step on where to go with this. Yeah, absolutely.
Okay, we could probably take one more question, and you're the lucky man right next to me.
So very interesting talk. You talked about the lower limit on MA. Is there any upper limit on MA?
So, like, on an upper limit of how far biochemistry can go?
Yeah.
That's a great question. So, we're using it so far in small molecules. We're not using this in peptides or anything, mostly because the base fragments that we're talking about in this case are elements to bonds. And when you talk like something like a DNA molecule, then things become so massive that since it's an NP complete problem, that'll take forever to compute. So I think like it quickly depends on your definition of a base fragment and what you want those joining steps to be. Essentially, DNA, I imagine, would be in tens of millions, if not higher, if we're using this particular definition. If we're using amino acids or base pairs, things become a little different. I have some interesting results in like patent chemistry that I'm happy to share afterwards to show like we have a little bit of upper limit of like what chemistry can look like, but I mean that's more of a computational limit than anything.
Thanks a lot.
Yeah, absolutely.
Thank you, John. The extra guys, go find him in the break because I know you have awesome questions for him. Up next, we have Macy Houston. She's coming from Penn State University.
Hello, my name is Macy Houston. I'm sort of a fifth-year grad student at Penn State in astronomy, as you may have guessed from my background. But I just successfully defended my thesis last week, so I've gone ahead and assumed. I don't get my diploma and start my postdoc until August, but I'm still going to call myself Dr. Houston now. So I'm going to be talking about something that was not in my thesis. So I hadn't thought about too much for a couple months, but I'm getting back to it now. This is some work I'm doing as part of the Penn State Extraterrestrial Intelligence Center. And this work is actually being led by Dr. Sophia Sheikh at the SETI Institute. So this project came out of a collaboration called Characterizing Atmospheric Technosignatures, or CATS, which I'm very glad we found a good abbreviation for. And so what this group is doing is just kind of creating a library of possible technosignatures and especially focusing on atmospheric technosignatures as JWST launches and we're making a lot of advances in our ability to characterize exoplanet atmospheres. But this project we're talking about today actually goes a bit more broad than that, and we're thinking of all the technosignatures that we produce here on Earth. So the project we're calling Earth Detecting Earth is establishing benchmarks for detectability based on how strong our technosignatures we produce here on Earth are, and how far away you would be able to use our telescopes to successfully detect our technosignatures. So this is a very preliminary version of our plot here. We're going to have more technosignatures than this, and we still have to finish up a few calculations to get all our distances right. But we're basically just trying to calculate the detectable distance for our telescopes to observe our technosignatures for all of the technosignatures that we could think of that humans produce. So this is related to a similar concept called the ICNO scale, which was proposed by Socas Navarro et al. A couple years ago. This term is defined as the relative size or intensity of a technosignature in units of the same technosignature as produced by Earth's technology. So kind of the first step in our project is to quantify the strength of Earth's current day technosignatures. And this is kind of defining the power level. That is an ICNO scale value of 1. And then we're going to determine what distance we can use our technology to detect those technosignatures and to keep things kind of uniform among all the technosignatures we're looking at. We're adopting a signal-to-noise ratio of 5, but we're also going to talk a bit about scaling relations you can use if you want to get higher signal-to-noise or something like that. So I'm just going to go through a few of our calculations here. I don't know why it's covering my... Oh, well. So the first kind of technosignature I want to talk about is intermittent celestially targeted radio transmissions. So the types of signals that would produce this are MEDI signals, so intentional messages that we have sent out ostensibly to communicate with extraterrestrial life, but we don't really do a lot of that. So the more common types of signals we send out are powerful radio signals targeted at planets and asteroids in the solar system in order to characterize them with radar. So for our calculation, we are assuming that our radar transmitter is Arecibo, RIP, but our observer for radio observations, we are using the currently under construction square kilometer array. If we assume an observation time of 1 hour, then we get our Earth detectable distance of 12,000 light years for our most powerful radio signals. So this is the highest number that we're going to see in terms of our distances here, but I wanted to start with it to really emphasize that I see technosignatures as a really important part of the search for biosignatures, because when you think about all of the signs of life that we produce here on Earth, our radio signals are by far the most detectable thing that we produce. So I really hope that the fields of biosignatures and technosignatures can work closely together, because I think we want to take as many approaches as possible to find any types of life we can in the universe. So the next category of technosignature is just another type of radio signal, intermittent celestially untargeted leakage. So these are signals that we intentionally send into the sky, but not necessarily with the aim of going to space. So things like military and commercial aircraft radar. We're just kind of assuming these standard aircraft radar systems for our transmitter, and again, observing with the square kilometer array. And our Earth detecting Earth distance is a bit over 200 light years. So this is still a pretty big distance. This includes quite a number of stars. If we're considering, the stars within this distance range. The next technosignature I want to talk about is persistent omnidirectional radio leakage. So there was some early work done on this topic actually in 1989, where Sullivan et al. Simulated the output of Earth's television tower transmissions as you might be able to observe them from space, and concluded that it's possible that other life out in the universe knows that we're here. Our TV signals aren't quite as powerful now as they were in the peak time, but we've got all kinds of mobile cell phone towers all over the world now. So there's a really great paper that just came out a few weeks ago by Mira Said et al. that kind of does a similar calculation to the Sullivan paper, but using mobile phone towers instead of television. So we adopted their value of a transmitter strength of 4 gigawatts, and again, using the square kilometer array as our radio detector. And we got a detectable distance of just under a light year. So this is a little bit too short of a distance to reach any nearby stars, but it's getting pretty close. And as radio technology improves, this kind of thing is going to become more feasible. The next technosignature I want to talk about is intermittent targeted laser leakage. So these are laser signals that we happen to be sending out into space. So for the non-astronomers in the room, the example that I want to use here is adaptive optics lasers. Adaptive optics is an astronomy technique where you take ground-based telescopes and distort their mirrors in order to account for the effects of the atmosphere on the light that we observe from space. There are kind of a lot of factors that goes into that, but one thing is that sometimes we need to create an artificial guide star to calibrate these. And so what we do is send really powerful lasers shooting into the atmosphere so that some amount of that laser power hits the atmosphere and bounces back for us to observe, while a lot of that laser power just happens to go out into space wherever it's headed. So for our calculation for laser leakage, we use the Keck 10-meter telescope and its adaptive optics system. And we get a detectable distance of about 10 light years. So this distance does include a few nearby stars, but it's important to note that we're not actually directing these lasers at any nearby stars because you only need to use adaptive optics, the laser artificial guide star, if you don't have a real well-known bright star you can look at. So we're never really doing that right at nearby stars, which would be pretty bright. So the next category of technosignatures I want to get into are exoplanetary technosignatures that you might detect, for example, in the atmosphere of a planet. So we've got an example here of one possible atmospheric pollutant, which is nitrogen dioxide. And this is based on work done by Kaparapu et al. A couple years ago. So this simulation was performed using the planetary spectrum generator and assuming that our observer is LUVEX, which I guess is now called Habitable Worlds Observatory, which is a space mission that's under development, but is a combination of LUVAR and HabEx mission concepts that was for a few months called LUVEX, but now this is already out of date. So our detectable distance here is a little over 3 light years. So this includes some nearby stars. But it's important to know that NO2 can also be created through natural means. So there's a lot of complicated chemistry at play here to determine whether it's actually artificial. But a really important thing about these spectral atmospheric pollution signatures is that you can use the same observations to search for technosignatures and biosignatures when you're looking at these spectra. So I think it's a really great way that these two techniques can work together. And then the last technosignature I'm going to talk about is city lights. So I'm showing a picture here of Earth as each part of the world appears at night with city lights. So for this calculation, we're using some work done by Thomas Beatty, where he assumes that our lights are primarily from high-pressure sodium lamps. In this simulation, our observer is LUVAR-A, so a slightly earlier version of the LUVEX I talked about last time. LUVAR-A was an earlier mission concept for that. So this exact design is not going to be launched into space, but we're going to have something similar. And our distance for this one is only 0.075 light years. So this means that we could only use something like LUVAR to detect our city lights if we're in the Oort cloud, which is just kind of the outer regions of the solar system. So if you want to detect this kind of thing, you're going to have a planet that has a lot more lights than we do. And so I'll just kind of leave up my summary slide here as the list of the technosignatures that we're looking at. The first few on the list here are the ones that we quickly went over. I've got a few more highlighted in yellow, and for those, our calculations are still underway. And then we've crossed a few out that turned out to be technosignatures we've crossed off of consideration for various reasons, mostly because it's just not feasible to observe them from space at all. We'd be talking about still in Earth's atmosphere for our distance, or because another possible technosignature is observing the contents of Earth's atmosphere over time and how it changes. But we decided for this project that we're not going to get into things that are based on changes over time because this is already a really big paper as is. So yeah, I can take questions. I also have my email and Twitter up there.
All right, thank you, Macy, our new Dr. Houston. Unfortunately, we only have time for one question, so I want to see some real enthusiasm.
Hi, thank you so much for your talk. I definitely agree with you that technosignature and biosignature scientists need to work more closely together. I was wondering, I know the paper is already super cool as it is, but as a sort of follow-up, would it be possible to estimate what sort of like how those technosignatures would evolve in the future, and if there's one that's going to shoot up, and at what point in our future would we be detectable to most terrestrial planets in our galaxy? Or, I mean, of course, like
yeah, we'll talk a little bit about that in the discussion, but we're not going to get too quantitative. But that is something that comes up as in, you know, one of the main things you hear people talk about this in is like radio leakage, because like if our cell phone towers were more directed, you know, down at the Earth, they could be more efficient, and maybe more advanced technology has less leakage into space just because it's a waste of energy. So yeah, these are things we think about. I don't have any definitive answers right now.
Cool, thanks.
Okay, our final speaker, no pressure, is Evan Sneed. Come on up. Evan is coming from University of California, Riverside.
Good afternoon.
All right, we're going to get started. Our second keynote speaker of the conference holds the Chancellor's Distinguished Professorship in Physics at UCSD. He's a theoretical physicist whose work is wide-ranging and whose Twitter bio says, "I'm interested in everything." Before joining UCSD, he was at the University of Illinois at Urbana-Champaign for over 30 years, where he led the biocomplexity group within the Carl R. Woese Institute for Genomic Biology, and where he both founded and directed the NASA Astrobiology Institute for Universal Biology. His research has been highly multidisciplinary, ranging from condensed matter and hydrodynamics to the ecology and evolution of living systems. Among his many accolades, Nigel received the 2020 Leo P. Kadanoff Prize from the American Physical Society for, quote, profound contributions to the fields of superconductivity, fluid turbulence, and dynamical pattern formation. It's been a pleasure to have him as a professor, and it's a pleasure to have him with us here today. Please welcome Nigel Goldenfeld.
Thank you very much for the kind invitation to speak at the AbGradCon. I love this conference. I've sent my students to it. I've been in it before. I think it's absolutely wonderful, and I was really thrilled to see that NASA is still supporting it, and even to catch up with an old friend and acquaintance from my days at the NASA Astrobiology Institute. Hi, Mike. So I'm going to talk about something that by all rights, shouldn't exist. And I don't mean life itself. I mean universal aspects of living systems. I'm a physicist, as you heard from the introduction, and so my approach to anything is ridiculously simple and is almost surely destined for failure. But we try to fail in a grand way and at least see what we can learn from our attempts to understand the physical principles that govern life. So I'm going to talk about universal biology, the genetic code, and the first billion years of life on Earth. And I have collaborators. My first collaborator I want to mention is Carl Woese, who will feature in this story. Many of you may know Carl Woese. He discovered the archaea. He was a very famous evolutionary biologist, and he was my mentor when I started doing biology about 20 years ago. Colin Vertsigian was one of my graduate students who did fantastic work on the genetic code and was in fact also at the University of Wisconsin, where Alex was as a student before. Farshid Jafarpour is now in the Netherlands, and Tommaso Biancalani is now working in Genentech here in California. All right, so I'm going to tell you about work that was done over the last 10 or 15 years or so through the NASA Astrobiology Institute, and I hope you're going to find it interesting. If you have any questions, feel free to interrupt during the talk, especially if it's a clarification, and I'll of course be happy to take questions as we go through to the end. So the thing I want to understand is what are the sorts of evolutionary transitions that life must inevitably pass through. This is part of a program that NASA discussed in their marvelous astrobiology roadmap from about 15 years ago, trying to understand universal biology and look for universal characteristics of life. And the idea is, if we can understand what features of life on Earth are not idiosyncratic, but are actually just something that we should expect on other planets, then understanding these processes, understanding these transitions may help us to come up with biosignatures, and we'll see that, in fact, there is some prospect for that. So I want to understand, basically, can we understand some features of life, universal features, which you may say may not exist, but we'll see it's the contrary, and can we understand them from general dynamical principles without necessarily having to worry about all the chemical details? So I'm going to talk about two things in this talk. I'm going to talk about the canonical genetic code, and that's going to be the most of my talk. I will talk about biological homochirality because it is important as a biosignature. It's been assumed to be a biosignature, but actually we'll see in this talk that actually there are dynamical reasons for thinking that homochirality is an inevitable outcome of living systems. So I want to first start off, though, by talking about, are there any universal features in biology, and how should we think about them? So I'm a physicist, so I start off by asking, is there universality in physics? So here's an example. This is thermal conductivity of various glassy materials. This is raw data. And then when we process it in a certain way, the data from different materials all collapse onto one universal curve, except for this regime over here. And so that's something that we try to understand if we want to understand glassy materials. Here's another example, which is a much better one. This example is looking at the magnetic field or the magnetization in a magnet exposed to an external magnetic field H at temperature T as you go through the ferromagnetic phase transition, the transition that makes stuff be magnetic at low temperatures and not magnetic at high temperatures. And the data you take from different external magnetic fields, different temperatures, and then if you process the data in the right way, all these data from 5 different materials, none of which look anything alike, all fall onto one universal curve, and the prediction for that curve is the solid line, which goes embarrassingly close to all the data, and it has no adjustable parameters. So that's another example of scaling and universality in physics. And you might say, well, this is really great, because what did the physicists do? They made a model of a magnetic system, and then they took that model, worked out its consequences, did some calculations, and then showed that it gave a precise prediction in agreement with experiment. That's what physicists usually do. In fact, it's nothing like that at all. Well, actually it is. It's a model of a model of a model of a model of a model, and that does all the work. The first model is a model of quantum chemistry, then there's a model of electronic structure, then there's a model of the dipole moments on the electronic spins. That uses quantum mechanics, and then you say, well, quantum mechanics is too hard, so let's get rid of quantum mechanics. So then you have classical, and you still can't do it, and then you make some sort of approximation that physicists call Landau theory, and then you get the results that I showed you. And the thing I want you to understand, the reason why I'm tormenting you with this physics stuff, is because every step along the way here is a non-systematic approximation. You cannot justify these approximations starting from first principles, from the Schrödinger equation, or whatever else it is. So the point is, here is an example of how a ludicrously simple model that has no right to actually be able to describe reality actually describes it precisely. And we know in this case why it works. It works in this case because of a thing called renormalization group theory, which Ken Wilson won the Nobel Prize for inventing in the 1980s. And so we understand how all these approximations that we made threw away stuff that really doesn't matter for the thing that we were trying to calculate. So that tells you that it is not impossible to make ludicrously simple models and still have some understanding of how the system actually behaves. Okay, so we're going to, of course, apply that type of modeling philosophy to biology. But first of all, let's ask another question. So for me as a physicist, I want to know, do we learn new physics when we study biology? Or is it just insanely complicated material science? Are there universal phenomena? Do they reveal anything important? And what do we miss by not understanding universal phenomena? Okay, I'm going to show you that there are universal phenomena. Some of you will be very surprised at the examples I'm going to show you. I'm also going to show you that if we don't understand these universal phenomena, not only can we not understand how life started at all and how it evolved, we certainly can't understand how to do things like respond to a pandemic, or deal with antibiotic resistance, or herbicide resistance, or cancer. All of these things depend on understanding evolution and these universal properties. Okay, so let's talk about universal biology. So let me give you an example here. So this was a headline on the NASA website at some point in 2013, about 10 years ago. Mystery of the missing waves on Titan. So basically, people knew that from looking at the fluid mechanics and the atmosphere of Titan, that there should be waves on the surface of Titan. So there was a mystery. They weren't there. We couldn't see them. Nobody knew why. And then about a year later, Cassini spies the wind-rippled waves on Titan. So suddenly, sigh of relief, thank goodness, you can sleep at night. We found the waves on the surface of the oceans of Titan. Okay, so that's a real headline, okay? Here's one that you, okay, I forgot this. We know the waves on the ocean of Titan are missing because there's a general theory of two-phase fluid flow interfaces that predict waves and their dispersion characteristics. So we knew what to look for. Okay, here's a headline that you didn't see. Mystery of the missing life on Titan, and then definitely not this one, Cassini spies the long-sought life on Titan. Okay, anybody seen that headline? It never occurred, okay? And it's a joke, right? Because it's a joke because we don't know if there's missing life because we don't have a theory that predicts the existence of life as a physical phenomena. So that's the first thing. Why does life as a phenomenon exist? And we certainly don't understand what sort of life can exist in different environments. So actually, going back to Cassini, Cassini may indeed have actually seen life, but not on Titan. It may have seen life on Enceladus. Okay, so how many people here know about Enceladus? Great, a lot more people than would at a typical physics colloquium, right? So good. So as you know, Enceladus is an isolated world orbiting Saturn. It has a global ocean of liquid water underneath the ice, and we know that because we can see how it wobbles, and because of the way it wobbles, we can detect that there must be life underneath, there must be water underneath, and it also obligingly has a crack in the ice, lots of cracks, and so water squirts out through the cracks. And so you've got a fountain, a huge fountain, and you can fly satellites through the fountain, and you can look at the water that you pick up. And that water, you can analyze its chemistry, and its chemistry looks very similar to what we might see as an alkaline hydrothermal vent here on Earth. So Cassini wasn't instrumented for looking at life, but we may have seen some signatures of life through that experiment. So what is universal biology? Well, universal biology is the idea that we are interested in general principles and not specific carbon chemistry details. And so we want to develop a theory of universal biology divorced from idiosyncratic details of the actual chemistry and the geological context and so on. And this will involve abstractions, and we use abstractions all the time in biology, and we'll talk about one of those in a minute. So on this slide is pretty much all we know about universal biology. So are you looking at it carefully? There's not much there. So let's talk instead about something where we do have an understanding, and that is universal computation. So I want to tell you now about what universal biology would look like if we could do it, and use as a model a computer. So here's a picture of my computer, or something close to my computer. Here's another computer. This one you can see a few hundred miles up the road at the Museum of Computation in Mountain View, or in my case, I saw it at the Science Museum in London. This is a computer made out of cogwheels and springs, designed and partially built by George Babbage in the 1900s. It is the authentic steampunk artifact. These two things are the same. They're the same algorithmically. This thing over here, the left-hand side, is a computer, and you know that it's not just a shiny chunk of glass, plastic, and silicon. It's actually a universal Turing machine. The thing on the right is also a Turing machine because it has conditional branching in its instruction set, and so it can be shown that it can be mapped onto a universal Turing machine. So in fact, the two things are the same, although one of them is many times faster than the other. So a Turing machine with a von Neumann architecture is really what a computer is, and we have hardware to instantiate that algorithm. So the medium is not the message. Here is John von Neumann standing in front of another computer that he built at the Institute for Advanced Study in the 1950s. In this computer, it's built out of thermionic valves. It's built out of relays and switches. And so neither this nor this, we're seeing here the evolution of computational hardware. But in all of these machines, they all do the same thing. They're all universal Turing machines. And so if we're looking at life, we should be thinking about life as making a progression, as you see over here, but executing the same sort of algorithmic processes. Now, is there new physical laws in biology? Well, Schrödinger and Delbruck were the first physicists to work in biology, and their partial motivation was to find new physical laws. They were thinking about quantum mechanics in the 1930s as they might see some deviations from quantum mechanics or something like that. But today, not many people, well, some people think that could be still true, but most of us think that the real big question is trying to understand emergence and the existence of life itself. How is it that matter, molecules and atoms, self-organize, hierarchically, create replicating and evolvable structures? We don't have a clue about how that happens. How do molecules come to life? So if we want to understand biology in the same way that we understand physical phenomena, we need to understand the existence and not just the specific realization of living systems. And I'm going to take the perspective here that living systems are dynamical systems that are able to reprogram themselves. So let's think about that. So here is the fortune cookie. The program is the data is the program. Okay? This is Niels Baricelli, who was the first person to write a computer virus. He was working at the Institute for Advanced Study, and in the day while John von Neumann was using the computer, one of the first computers, to solve the equations of hydrodynamics, to design hydrogen bombs, Niels Baricelli went in at night and made computer viruses and then had them compete and evolve with each other inside a fixed ecosystem, which was the memory of the computer. And he understood that what he was seeing here was actually many of the phenomena that we see in evolvable ecosystems. So what do self-programming systems can do? Well, living systems have the capacity to evolve, and evolving systems can reprogram themselves so they're able to respond to perturbations by creating new functionality. That is the defining characteristic of living systems. And this is very different from physical systems or engineered systems, which obey a fixed or predetermined equation of motion or behavior. So the future state of an evolvable system is inherently unpredictable and maybe Gödel undecidable, don't worry about that. And so this feature means that it's very difficult to control evolving systems. And we'll come to that, we'll turn to that at the end of the talk. Now, what do most biologists do? Well, most biologists do something rather strange. You could call it the inverse problem. Imagine that you came down from Mars and I gave you my computer and you had no idea what this thing was. What would you be able to do to figure out that this thing is not just an expensive doorstop, but actually is a universal Turing machine with a von Neumann architecture? It would be very, very different, very, very difficult to figure out from the electronic circuits and the hardware and so on that that's what the thing actually did. And so what we want to do in biology is we have the inverse problem. The biology is already created, and we want to understand what is the abstract theory of which it is an instantiation. And that abstract theory would underline all systems that exhibit the characteristics of life. So could you, if you didn't know about the universal Turing machines with a von Neumann architecture, could you deduce a theoretical framework just by somebody giving you a highly evolved computer? Okay, we've talked about abstraction, so now let's get down to a real abstraction. So I want to talk about the genetic code. And I frequently find that people from various wide-ranging audiences don't quite know what I mean when I talk about the genetic code. So let's just take a pause to go through that. So in the modern world, as you know, DNA contains our genome. The DNA is built from 4 nucleotide bases. RNA polymerase reads the gene coding segments and spits out mRNA. That's also built from 4 nucleotide bases. And then the ribosomes go along the mRNA and they spit out the proteins, and they choose which proteins should go into the protein. They choose which amino acids should go into the proteins from the code that they're reading from the mRNA. And the way they read that code is they read it in triplets, so AUG, ACA, GGG, and so on. These are codon triplets of nucleotide bases. And the genetic code, it tells you, if you read this thing here, what amino acid is going to go into the protein that you are building. And so this is a sort of cartoon here of the whole translation process. And you're supposed to think of this huge machine moving along like so. So just to summarize, what the genetic code is, it's a map. It's the map used by the ribosome to translate the message from mRNA triplets of 4 bases into the 20 amino acids of life. And we're going to discuss how that code evolved. Now, this is Carl Woese sitting in his office and on the New York Times front page, Thursday, November the 3rd, 1977. Why is he there? Well, it says here, scientists discover a form of life that predates higher organisms. I guess fake news is not just a new invention. It happened back in the 70s as well. This is partially true, not quite true. But in any case, he had discovered the archaea. So let me just tell you what he had discovered. So this is the tree of life. This is from a paper by Norm Pace in '97. You can see here there are 3 domains, the bacteria, the archaea, and the eukaryotes. You are over here. Virtually everything else here is microbial. And this phylogenetic tree is a kind of map. It's built, it's been elaborated on by now, and it's out of date, and there's some debates about whether there's 2 domains or 3 domains and so on and so forth. But fundamentally, this is what he discovered. Now, how did he discover this? Well, what he did was looked for patterns in molecular sequences from parts of the ribosome, the 16S, a small subunit of the ribosome, and by looking at those sequences, was able to look at what today we would call comparative genomics and map out this tree of life. And somewhere around here is the last universal common ancestor, or the last universal common ancestral community. So this is the paper that they wrote in 1977, and the mystery that this work left us with is the following. We know that the planet is about 4.6 billion years old. We know that the last universal common ancestor, even then, was dated to at least 3 billion years. Today, we think it's about 3.6, 3.8 billion years, depending on who you're talking to, based on static, what do you call them? Various geological evidence and so on, stromatolites and so on. So basically, but something like this. But the point that Woese and Fox were making is that for a lot of the time, the planet was inhospitable to life. You had less than 1 billion years in which life could evolve, and it evolved the complexity of something like the modern cell in less than 1 billion years. And then after that, there wasn't very much cellular evolution, maybe dinosaurs and multicellularity and things like that. But from the point of view of the architecture of the cell, very little. So what Woese and Fox, here's some pictures of them doing their work at the time. What they wrote was that it wasn't that the evolution speeded up at the beginning and then slowed down the last universal common ancestor. What they wrote was that actually maybe evolution had a different character in its early phases. And we're going to see that there is evidence for that. Now, what kind of different mode could there be of evolution? Well, most of us, when you think about evolution, you think about what is really called vertical evolution. That is, you have your genes, you give your genes to your children, they give their genes to their children, and so on and so forth. And so there's a transfer of genetic material, of genes, through the generations. Horizontal gene transfer is a different thing altogether. Horizontal gene transfer is the transfer of genes from one organism to another that it is not related to. And this is what happens in bacteria. There's 3 ways that this are known to happen here. On Earth, genes can be transmitted through viruses, through direct contact, or through uptake of free DNA from the environment. So the question is, what happens when all the microbes in the world do this? What happens when all of early life is able to transfer genes? Okay, let me just give you 2 quick anecdotes about that. So this here is a cyanophage. It's a phage that infects Prochlorococcus, one of the most abundant organisms on the planet. And this here is a phylogenetic tree of a gene that is involved in photosystem 2. And if you can read phylogenetic trees, it doesn't matter if you can't, but if you can read them, what this shows you is that this gene was transferred back and forth between a virus and the bacterial host multiple times during evolution. And in fact, the group that discovered this, Sullivan et al. In Penny Chisholm's lab, they wrote that host-like genes acquired by phages undergo a period of diversification in phage genomes and serve as a genetic reservoir for their hosts. So the idea is, I have a gene that is a photosynthesis gene. That gene helps in photosynthesis. That gene gets transferred by a viral attack to phage. In phage, that gene can evolve much more rapidly because there are less proofreadings and things like this that go on in phage replication. So as a result, the bacteria get infected by new genes from the phage, but those genes have evolved much more rapidly in the phage than they would in the bacteria. And so there's a mechanism by which you can have rapid evolutionary change mediated by phage or by other mechanisms of horizontal gene transfer. And because that is a network effect, it's extraordinarily efficient. And I'm not going to have time to show you work that we did actually modeling that whole process. Now, this is with that, having said that and told you about that other mode of transfer, let me now tell you about the genetic code. So here is the genetic code. So the way you read it is like this, U, and then the first column up here. So that brings you to this cell, that's phenylalanine, and you can do the same thing for all of these. Of course, it's a code of triplets of 4 nucleotide bases, an alphabet of 4. So in principle, there are 64 things you could code for, but there's only 20 amino acids. So the code is redundant, but it's not just redundant, it also has structure. So if you look here, these are the most hydrophobic amino acids, these are the most hydrophilic ones, and you can see that in the way that this code is written, there is structure here. The amino acids are segmented in this genetic code table. So one of the things that Carl Woese did back in the 1960s was to measure a quantity that he called polar requirement, which measured this balance between hydrophobicity and hydrophilicity and gave a single number, which is small up over here and large over here. And so he was able to quantify that chemical difference. Now, you all know that the genetic code is pretty much universal. It's not exactly universal. There's small variations and stop codons, but it's basically universal. But what I want to tell you now is something that you may not know about, and that is that the genetic code is pretty much optimal in minimizing errors. Okay? So let's discuss what we mean by that. So let's suppose that you were given the task of designing intelligently a genetic code. Okay? Well, you might say, well, translation is fundamentally important to a cellular operation, so we want to make sure that any mistakes, any mutations, or any misreadings give you an amino acid which is pretty close in chemical properties to the one that you should have got. And if you could design a code like that, then that would be great. Okay? It would be robust to errors. So the question is our genetic code like that? I'm going to show you that it is. So here's the actual genetic code. So what you can do is you can make in the computer alternative genetic codes just by permuting the labels. So here I'm permuting the labels, so I get new codes, albeit with the same pattern of degeneracy. There's 20 factorial, which is about 10 to the 18 possible genetic codes that you could have in the computer. Okay, so now I can say, all right, I've made this whole suite of genetic codes. How good are they at minimizing errors? And there's a way that you can compute that, and I'm not going to go into the exact metric that one uses. So there's a way that one can do that. So then one can ask, well, what should be the output if we take all our genetic codes that we've constructed in the computer, measure how good they are at minimizing errors, and then plot the probability distribution, how many times we see a particular code with a particular score at minimizing errors. And the smaller the number here is on the horizontal axis, the better the code is at minimizing error. Okay, so one possibility that you could have is something like this. You've got some roughly bell-shaped curve, and then that's what you would get for any random genetic code. And then you look at the actual genetic code. It happens to be here in the middle in this sketch. And so you would say, okay, well, if that's what happens, then that means that the current genetic code is just a frozen accident. There was some ancestral organism. By accident, it happens to be the one that we're all descended from, all life on Earth. It had some genetic code. We all have the same genetic code as it, because if we had a different genetic code, then we'd be mistranslating our genomes. We'd be getting the wrong amino acids and the wrong proteins, and so we wouldn't survive. And so the code must be what Francis Crick in 1968 called a frozen accident. It's an accident because it just comes from whatever was the last universal common ancestor, and it's frozen because if it evolves, the changes that it would happen would be deadly. Well, the other option is something like this. You get a bell-shaped curve like this, and then the actual genetic code is somewhere down here in the tails. And if that's true, then that says, heck, the genetic code that we have is not a frozen accident. It had to have evolved. So here are the data. These are data taken from an experiment that was done by Freeland and Hurst in 1998. So they generated 1 million genetic codes, and they scored them in a way that I'm not going to go into in detail. And the actual genetic code is way, way down here in the tail. So all these random codes look nothing like this actual universal genetic code, the canonical genetic code. And so the title of their paper was, "The genetic code is 1 in a million." Okay, you generate 1 million genetic codes, and they're all worse than the one that we actually have at minimizing translation errors. Actually, we know that it's actually more like 100 times better than that. Okay, so now we have to ask the question, how did the genetic code get like this? How is it possible for the code to evolve? Because Francis Crick already told us that it can't evolve. If you change the genetic code, you're going to start making the wrong amino acids. You make the wrong amino acids, you make the wrong proteins, everything dies. So we have to figure out how to do it, and this is what we did in this paper over here. And I want to walk you through, I'm not going to go into any of the modeling and the math and so on. I want to give you a feel for how we can understand how it is possible for a code to evolve. Okay, so we're going to do a thought experiment, and we're going to do the thought experiment by involving in our little story here the experts on codes. Who are the experts on codes? Spies. You're right. These characters from bad and possibly sexist 1960s TV shows. All right, so we're going to do an experiment which involves these spies. And we're going to imagine that the spies, of course, have their secret code book. So there's their code book, and the spies are trying to communicate with one disreputable member of their community, shown here on the right. And so we're going to do a thought experiment about what can happen when one spy tries to talk to the other. So let's start off with a message, which is emitted over here. So this is the message that she wants to send. That is received by the person on the right, uses their code book, and they correctly decode it as that sequence of amino acids. So far, everything is good. There's only a single message that you can deduce from this signal that you receive. Okay? So this is the standard operating procedure. But the person on the right was chosen not just for their glamorous sartorial style, but for the fact that they're very incompetent. And so I want you to imagine that this person has lost half the code book. And so the code has now been changed, because you've missed half the code book. And so now he translates it as E equals mc squared, which means nothing to him, but it may mean something to you. And so what we've learned from this is that if you evolve or change the code, in this case by losing half the code book, the message gets garbled. So far, Crick was right. Suppose, however, that we have a statistical code book. Not a code book that gives you one message, but a code book that gives you an ensemble of messages. And from those messages, you look at them and you say, oh, that makes no sense, that makes no sense, that makes no sense. Oh, phenylalanine. Okay, great, perfect. This must be what they meant. If you have a code plus its context, then if you just have a probabilistic code book, you have a chance of being able to interpret the message. So the idea then was that if you have a probabilistic code book, then that means that you may need to have statistical proteins, a process of translation that doesn't just produce one protein, but produces many. And this would make complete sense. Because think about early life. Think about early life, which we know was dominated by endosymbiosis and all sorts of events like that, which of course led to many of the structures that we see in modern cells, like mitochondria and chloroplasts and so on. So we can imagine that early life was a bit like early automobiles. Okay? Remember how early automobiles were. Okay? 100 years ago, or a bit more than that, automobiles did not look like they do today. They were rickety old things. They were sort of held together by string and sealing wax. And if I drove over to one of my friends in my car and then the wheel fell off, she would just say, well, no problem. I've got an old bicycle in the garage here. We'll just screw on the wheel of that old bicycle onto your car and you're good to go. That you could do. You could mix and match parts 100 years ago, 120 years ago in the early cars. Try doing that today to a Toyota Corolla, right? To taking a bicycle wheel and sticking it on when you've got a flat tire. That's not going to work at all. Modern cars are more highly evolved, and so they're very intolerant of anything that is not exactly right. And so we get the idea that evolved systems become very intolerant of any kind of ambiguity in what's present, but systems that are very early on, are very simple, are able to tolerate ambiguity. And so you can have this idea that the codes are floppy, that the statistical proteins that are made are not always the same proteins, and then somehow the messages can be interpreted. So in other words, what I'm saying is that the code book and the message can co-evolve as the organisms become more and more complex. You get a probability distribution of codes that can be the outcome of translation. And as the organisms become more and more complex, that distribution gets narrower and narrower and very intolerant of any kind of errors. Now, you might ask yourself, well, wait, this doesn't make any sense. Selection pressure acts on the phenotype. It doesn't act on the code. But I want to show you that it acts on the code too. Okay? So here is a thought experiment, but for me it was an actual experiment. So I'm a physicist, so I like to write papers with mathematical equations. And so when I write a paper or a grant proposal, I write it in a thing called TeX, a typesetting program that enables you to write equations. My biological colleagues, of course, use Microsoft Word, which is fine. And so, hey, I guess the age of satire is not over yet. And so you can imagine the situation where I'm sitting with my friends in the Institute for Genomic Biology, and I'm saying, hey, let's write this proposal together. And they say, sure, but so we're going to write it in Word, and I send them my stuff in TeX. And of course, it's a complete disaster. And what happens is our proposal never actually gets written, it never gets submitted, and so it never gets funded. Meanwhile, down the corridor, another person is collaborating with their co-workers. They just write it in Word, no problems. And even if their proposal was less good than ours, it still has a chance of being funded. So the code actually does matter. Now, what is the basic way that the genetic code evolves in terms of its context? So here's an interesting factoid. This slide is now quite old, but this you may not recognize this person. This is Bill Gates. This is the late Steve Jobs. Both of them with examples of their company's computers. And actually, my computer is a Windows computer, but many people like the Apple computers. And the reason that the reason I use a Windows computer, well, I mean, everybody does, right? Like 96% of all the world's computers run Windows, and a very small fraction run the Mac operating system. And the reason is that the Windows operating system is much better than, oh heck. Well, that's a very inopportune time to have a blue screen of death. The Windows operating system is, to put it mildly, rubbish. It has all sorts of things like this. But the reason why it is so popular is not because it is the best computer system. It's because any program that you want to run, you can find it on Windows, but you may not be able to find it on the Mac OS. That may not be so true today, but it was certainly true certainly 10 years ago. And so what you learn from this is that the community, with access to the broadest range of innovations, has an evolutionary advantage. Anything that you want to do, you can find a gadget in that operating system that does it. And so what's important for platforms, for operating systems, for processes that are fundamental to cells like translation, is that you have the broadest reach. So what we did in our mathematical model, which I'm not going to go into in detail, was we considered a simulation, a digital life simulation, just like the computer virus ones that I showed you at the beginning of the call, at the beginning of the talk, the ones run by Niels Baricelli at the Institute for Advanced Study. So we have an asexual population of evolving, reproducing digital organisms like computer viruses. Their phenotype is a function of their proteins, and the proteins are obtained by translating the genome with a code, but with errors. The individual reproduction rate is a function of fitness, and the messages change faster than codes, and so forth. And so everything that's in this system allows codes to evolve due to selection of the phenotype through the mechanism that I was showing you. So now what we're doing is simulating a whole population of different organisms which have different codes, and now the question is, which code is the one that wins? All right, so let's imagine that we've done this experiment. So I start off with a bunch of organisms, all of which have slightly different genetic codes, and they all co-evolve and are trying to deal with the environment that they're in, and we watch how they evolve in time. Now, we did 2 experiments here. I'm going to show you this graph, and I'm going to show another one similar to it in the next slide. This, on the vertical axis, is the quality of the code. It's how good the genetic code is of those organisms, minimizing error. And this is time over here. And here's what happens when you do this with regular vertical Darwinian evolution that you're used to. And you can see that what happens is as I evolve the system, the codes get better, smaller is better, and then eventually it stops and it just stays constant in time. And maybe if we waited like 100 times longer, maybe there'd be some other change down here or something like this. And you run it again, and for this one you get something like this, and you run it again, you get something like this. And if you ask, I've got a whole distribution of codes here, what would I have got at random? Well, you can work that out, and it would be something like this. And so what I've learned is that without, in this experiment with vertical evolution only, I evolve organisms that have codes that are indistinguishable from random codes, and they're not unique, and they're certainly not optimal. But if I switch on horizontal gene transfer, then what happens is the codes follow this blue trajectory here, and as you can see, end up with a very optimal code, and one which is very far from what you would get at random. And so what you learn from this is that the process of horizontal gene transfer as an evolutionary process leads to optimality of the genetic code. Now, if we look at how many codes we have in our system, that's shown here. And again, the same thing is true, that if you just use vertical evolution, you don't get much selection of the genetic codes, as we saw on the previous slide. But if you switch on horizontal gene transfer, you get a universal genetic code. And so what we've learned from this is that the phase diagram of life must have looked something like this. So we're somewhere up here, we're in that blob over here. Early on, the evolution was a network process, shown schematically over here. Rapid evolution, and then over here we have the vertical evolution, which we saw was incredibly slow, and that's the process that we are in today. And somewhere over here was a transition that Carl Woese liked to call the Darwinian transition, a kind of phase transition between a collective network phase of life and a transition to a life where organismal identity and individuality becomes more important. All right, so I'm going to skip my section on homochirality. So I'm just going to skip through that. And I wanted to tell you about some of the things that are universal in biology. So anyway, the bottom line of this is that we made a mathematical model of the evolution of chiral autocatalytic self-replicators, and we could show that you ultimately end up with broken 100% broken chirality. Not just you get some right-handed or some left-handed, but 100% effect. And that's the thing that we observe in biology, and that's the thing that was difficult to explain, and we have made a theory for that. Okay, so let me just very quickly show you some examples of universality in modern biology. Even today, there are things that are universal, not just the evolutionary processes of, say, the genetic code, which may have happened billions of years ago, but other things too. So one example of this is the universal statistics of gene expression. So if I have genetically identical cells, they can exhibit different protein copy numbers. That's something that we've known for about 20 years. That's called stochastic gene expression. The whole process of expressing genes is a random process. And so the protein copy numbers are not thermodynamically large. And so what happens is you have large fluctuations in protein copy numbers in cells. And here are experimental data showing you for a variety of different cells here, and I'm not going to go through the details, showing you that there's a universal distribution for the protein copy number. Notice that all these data are collapsing onto one universal curve, which can be predicted. This is very much like the universality I showed you in the magnetic system at the beginning of the talk. Here's another one which is absolutely fantastic and is still not understood, and that is universal metabolism. So here's the experiment. So what you do is you go into the lab, and you get some paper and some mud and bits of egg and water and stuff like this, and you throw in some microbes, and then you make a bioreactor. And the bioreactor is producing, let's say, methane. Okay? And so you get this thing running, and the bioreactor is producing a fixed rate of methane coming out. You're feeding the bioreactor, and the rate of methane coming out is a constant. So you say, well, that's great. I wonder what's in my bioreactor, what's in my chemostat. So you go and do a metagenomic survey, and what you find is that even though the methane that is coming out is constant, when you look at the community structure that you see, and here I'm showing you examples, these are real data from different, from a reactor, what you find is that, let's say day 900, you go and draw a pie chart showing you the different operational taxonomic units that are present in your system, and you say, that's it, I'm done. And then your advisor says, aha, you're not done. Wait 2 years and do the experiment again. So you twiddle your thumb for 2 years and then do the experiment again. And then what you find is a completely different set of organisms that are in the bioreactor, but it's still producing methane at exactly the rate that it was before. Okay, this experiment was actually done by Ana Fernandez and in 1999, and her advisor basically said this can't be true. We can't publish this. We can't publish these data. But they published it in any case. And this has been replicated many times since. So what we've learned then is that the functional properties of a community are insensitive to taxonomic fluctuations. Here's another example. This is from Luca and Derbley and Puffrey. This is decoupling function and taxonomy in the global ocean microbiome. And basically the same story, that despite the constant metabolic function of the ocean microbiome, there are large taxonomic fluctuations. And we don't have any idea why this is happening. Okay, so these are examples of universal things that are going on right now, and they need to be understood, and they're telling us something about the collective properties of microbial communities. Now, if the NASA Astrobiology Institute was still a thing in existence, and I hadn't moved from Illinois to here and so on, one of the things that I would be thinking about doing is exploiting this. For example, suppose I want to know what are going to be the biosignatures of say, life that lives under the ice of Enceladus. Well, it turns out that the metabolic output of microbial communities doesn't depend sensitively on what organisms are there. So if I have some knowledge of the geochemistry, I can then exploit this functional redundancy to be able to make predictions about what metabolic biosignatures I might find. Okay, so let's end with discussing about whether or not universality is or is not useful. So here is an example of another scaling law. And this is a scaling law in ecology. This scaling law has been known since the 1850s in England. These are data taken from bird lovers. Actually, not bird lovers. These are plants. Never mind. These are plants. People in England like two things. Oh, actually three things. They like plants, they like birds, and they like beer, or they like stinky pie, or they like football, or whatever you want. But they like plants, and they like birds. And so there's a lot of data going back 150 years. And here is showing you the number of species as a function of the area of the habitat. And what you can see from these data is that the number of species scales like the area to the 1/4 power. So you might say, here's a field, count all the bugs in the field, count all the plants in the field. Double the size of the field, count how many there are in there then. You might say, okay, the number of species are going to double. Not true. It goes like roughly like the area to the 1/4 power, not the area itself. So this is a very important law because we can use it to make extrapolations. For example, if we know how much deforestation happened today in the Amazon, let's say, then we can figure out how many species might have got affected by that. So that says these universal laws are useful. Here's an argument that says they're not useful. So here's an experiment that was actually done. This is Barra Colorado Island in Panama. And this is an island which is beloved by ecologists because it has lots of trees and plants. And we know every single tree and every plant on that island. It's heavily studied. Okay? So you might ask yourself the following question. On this island, what is the number of species, fraction of species, with a given number of individuals? Okay? How many species have 100 individuals? How many species have 1,000 individuals? How many species have 4 individuals, and so on? Okay, so you can produce a species abundance curve, and then you get data that looks like one of these curves here. I don't even remember which one it is. So that would be a measurement, and you could make a theory for that, because you could say, well, we have to look at the soil, we have to look at the weather, we have to look at the interactions between the trees, the canopy, and so on and so forth. And if we had a detailed model, we could probably predict this curve. But there's another way to think about it, which is just to say, well, let's suppose it's just a random process. Something has to be the most abundant organism. Okay, so whatever it is, that's it. We don't care what its name is. Then something else has to be the next most abundant, and you can work out a theory that looks like the general statistics that you would expect for abundance, just like the central limit theorem in statistics. And so in a neutral theory, the species are functionally equivalent. They're not different. They don't occupy different geochemical or biological niches, metabolic niches. So you've got these two completely different theories, and one of them gives the black curve, one of them gives the green curve. They both explain the data equally well. So this is, again, not helpful. So the upside of universality is that you can make predictions based on the minimal model, and that's a good thing. Like trying to predict the metabolic signature of putative life under the ice cap of Enceladus. The downside of universality is that statistically similar results can be obtained from microscopic models that are completely different in their assumptions. And so if you have something universal at a high level of description, that means you can't understand the actual processes that went on that caused the thing in the first place. Okay, I want to end by asking, what do we miss if we don't understand universal phenomena. And I'm going to talk about an example that may not be meaningful to some of you, or many of you even, but it doesn't matter. I want you to just understand the point. So this is about something in superconductivity, and there's a couple of students here from my class on emergent states of matter, so they'll be familiar with these examples. So what is superconductivity? It's the fact that you can have a current flowing through a material, and there is no electrical resistance and no heat that comes out. So that's the idea of superconductivity. It's a superconductor. If you have it, you can make levitating trains and transmit power over long distances and solve all the world's problems. That was discovered in 1911. 1933, it was also discovered that superconductors don't just have a current that lasts forever and just go round and round forever, perpetual motion. They also expel magnetic fields. Okay, don't ask why, it doesn't matter. 20 years later, after that, it was discovered that actually, nope, it's not true. They don't expel magnetic fields. Well, some do, but some don't. Some allow magnetic fields to penetrate a superconductor, but in a lattice of so-called vortices or flux tubes in a way that is, I'm not going to go into, but that can happen. And then finally, whoops, wrong thing. Then finally, about 10 years or so after that, something called the Jolla effect was discovered. The idea that I can have a current flowing which will be oscillating with a frequency that is just determined by quantum mechanics and doesn't depend on the material or anything like that. So you can use this to create a universal standard of voltage and of time. Okay, so this is a complicated quantum mechanical effect, and it took 50 years. And most of the people on this who discovered these things ended up getting Nobel Prizes. These were very important things scientifically and technically. And the question is, why did it take so long to make these discoveries? Are physicists stupid? Well, maybe. But the thing is this, it's even worse, because in my class, I derive all of these things in basically one lecture in a few lines of algebra from some mumbo-jumbo that's written down here. Okay? So what was going wrong? Well, what was going wrong was that people were focusing on the wrong level of description. And I want to explain to you what I mean by that. Okay, so in the world of superconductivity, you have to make a superconductor, so that's a problem in quantum chemistry and material science. There's a theory that applies to at least the classic superconductors, but not the ones that everybody's excited about for the last 30 years, the high-temperature superconductors. So there's a theory of that, which is very nice and so on. And then lastly, there's a theory, which I've given this name here. It's basically a theory that looks at the quantum mechanical symmetries of superconductors. Now, when we talk about biology, we have another set of levels of description. So this level is quantum chemistry, this is electrons moving around, and this is looking at symmetry and wave functions. All right, here in biology, we start off with the lowest level of description with atoms and molecules. There's an intermediate level of description where we talked about with translation. We look at DNA, we look at how elastic it is and how proteins fold and things like this. We look at liquid-liquid intracellular complexes and things like that in cell biology. And then finally, on the larger scale, I talked about the dynamics of how systems evolve, the dynamics of evolving systems like the genetic code. So those are levels of description. These levels of description answer different questions. So in superconductivity, well, quantum chemistry and material science says, how do you make a stuff? What's the specific recipe of putting the atoms together in such a way that you make a particular superconductor? This intermediate level of description tells you about what is the basic mechanism by which electrons form what's called a Cooper pair, a composite boson inside a superconductor, and then do something called Bose condensation. So this is a sort of more detailed description that applies to many different superconductors. And this level of description, this symmetry wave function quantum mechanical theory, describes why the phenomenon of superconductivity exists at all, how you can get all the phenomena of superconductivity just from one very simple mathematical description. Now, in the world of biology, atoms and molecules tells us something about how specific biopolymers interact and fold, undergo template-directed synthesis, and so on and so forth. If you want to understand those questions, you have to deal with atoms and molecules. There's no way around it. If you want to understand the basic functional cellular processes, you don't need to have such a detailed description. You can just think about phase separation inside cells and sort of bending rigidity of cell membranes and DNA and so on and so forth. And if you want to understand why the phenomenon of life exists at all, well, that's surely a question that would be answered if we understood more about the dynamics of evolving systems. Different levels of description apply to different levels of universality. So if I look in the quantum chemistry and material science, that tells us something about very specific materials, like yttrium, barium, copper oxide, or something like this. If I want to look at this level of description, it tells us something about what are called weak coupling superconductors. And finally, this level of description, this symmetry wave function theory, tells us about all superconductors, whether they're made in a material science lab or whether they occur in the heart of a neutron star. In biology, this level of description applies to very specific biopolymers, the chemical structure of RNA or DNA or some particular protein. The elasticity theory for DNA and so on and so forth tells you about the physics of subcellular components, and the dynamics of evolving systems would be applying to all life, and just in the same way that a universal Turing machine with a von Neumann architecture applies to all things that we call computers. Now, why do we need this universal level, this top-level description of stuff? Well, if I have a superconductor and I want to understand this level of description, not only does it tell me that superconductors exist, but it also tells me everything that a superconductor can do. It tells me the Meissner effect, the vortex lattice, the Josephson effects. It tells me how a superconductor responds to electromagnetic fields. So if I don't have this, I can't predict how a superconductor responds to an electromagnetic field, and that's a big problem. By regarding superconductors as collections of atoms, we're missing the emergent laws that act at the system scale and govern the large-scale response to electromagnetic fields. Just like when we were looking at our bioreactor, it produces methane at a constant rate. If we just focus on the bacteria that are in there, we won't be able to understand that. We need to understand how metabolism can be emergent in a community. This problem we know how to solve. It took us 50 years to do it, and we had to rejigger the way we think about physics. For living systems, we know that this level of description would apply to all of life, and what happens if we don't have it? We can't predict the response of living systems to selective perturbations. We can't tell what happens when you apply antibiotics or herbicides or insecticides or chemotherapy to somebody with cancer. Okay? And we know what happens in the real world. Whenever we do these interventions and treat living systems as engineered systems, what happens is they fight back. They evolve. The cancer tumor evolves, and the chemotherapy stops being effective. Roundup stops being effective against weeds. Antibiotics stop being effective against bacterial infections, and so on and so forth. By regarding biology as complicated physical systems, we are missing the emergent laws that act at the system scale and govern the large-scale response to control perturbations. And we do not know how to solve that problem. All right, if you want to read about any of these things that I've been talking about, there is an article I wrote called Life is Physics with Carl Rose, and another one on the statistical mechanics of early life in Phil Trans A. This one was called Life is Physics for the following reason. When I used to go to astrobiology conferences, on the first day, somebody would get up and show some extremely complicated chemical pathway that they thought might have existed in the RNA world, or the sugar world, or lipid world, or whatever was the fad of the time, and they would say, life is chemistry. And I fundamentally disagree. Chemistry does matter. It does matter. You can't build a superconductor without atoms and molecules, but you have to understand the emergent physical laws as well, the dynamical processes that go on. And so that's why we talk about this as life is physics. All right, so did we learn new physics when we study biological systems? Yes, we do. We realize that they actually do things that physical systems don't. Are there universal phenomena in biology? Yes, genetic code, homocarity, patterns of gene expression, distribution of species, metabolism, and so on. Do they reveal things that are important? Well, yes, they tell us about the phase diagram of life. They tell us about cell structure and principles and how things evolve. And what do we miss by not understanding universal phenomena? We don't understand why life exists at all, and we don't understand how biological systems respond to control perturbations. So here is the history of life. We know that somewhere around here was a homochiral transition, then the genetic code, the Darwinian transition, and finally 3.8 billion years ago, the last universal common ancestor. All of this happened super fast because it was dominated by network effects. And what I didn't tell you about this in detail, autocatalysis leads to 100% homochirality. Horizontal gene transfer and networks drive the evolution of the unique optimal genetic code. And horizontal gene transfer eventually becomes ineffective compared to vertical selection, and you get this transition to the vertical phase of life that we are in today. I want to end with a quote, since I'm a physicist. I study biology not because I love biology. I have a sort of love-hate relationship with biology, but because it teaches me things that expands the scope of physics. So ask not what physics can do for biology, build you a better microscope, build you a better computer simulation, understand the structure of some protein. Ask instead what biology can do for physics. It can teach us wonderful things. Thank you very much.
So I'm very recently coming to appreciate the importance of this horizontal gene transfer, but mechanistically I don't understand why this trade-off is tied to optimizing the genetic code.
You don't understand why what?
Mechanistically, I don't understand why its massive advantage is tied to having a suboptimal genetic code.
The horizontal. So the question is why is, if I understand it right, why is horizontal gene transfer important in evolving the genetic code? Is that what you're asking? Yeah. So the fundamental reason is this. What I showed you in the simulations was that if you just have vertical evolution, which I explained to you what it is, you kind of get trapped in local minima. Okay. So horizontal gene transfer is a very non-local shuffling of genes that wouldn't otherwise happen. And so it's a much faster way of exploring the space of possibilities. And so what happened in early life is organisms were very porous. There's a lot of endosymbiosis. So today we only, you and I are not horizontally transferring genes. The bacteria in our guts are. But in early life, organisms would sort of go through each other and collide and subsume each other and so on. And so there was a very natural built-in mechanism for genes to be horizontally transferred. And so when we model that in our simulations, what we see is that it is enormously effective in accelerating the evolution rate. So bottom line is, horizontal gene transfer is just one way to accelerate evolution. And if you accelerate evolution, you don't get stuck in local minima. If you don't get stuck in local minima, as it were, you then find the true best code, or the best whatever it is that you're optimizing, and that's why it works. So did I answer your question?
Yes, thank you.
What was the bit that I hadn't explained that made the penny drop?
I saw empirically that it was true, but the mechanism.
Oh, okay. So I explained that. Yeah. Got it. Thank you. Okay. Yeah. Hi there.
Hi, I'm Maddie from MIT. Great talk. I was kind of interested, based on your idea of evolution of this pro-genote, horizontal gene transfer dominated system evolving to this Darwinian phase. Where do you think kind of the universality of essential dogma kind of starts to evolve when we think of the genetic code of codons to proteins and DNA? Is that something that might have existed with this pre-state, or would this be something we only see with like the rise of like more
Well,
of a Darwinian?
I don't think the central dogma even exists today. Okay, we know that that's not true. We know that there are ways that that there can be post-translational modifications. You have retrotranscription and so on and so forth. So organisms even today can rewrite their genome, and so. When did the of course at first people didn't know about that. Crick called it the central dogma as a joke, but today we know that viruses are doing this all the time. So we have lots of endogenous retroviral DNA in our own genomes. So I'm not so convinced that the central dogma world, as it were, ever existed, or at least even exists now. But the extent to which genome editing, self-genome editing, evolved in time, that's not something that I've looked at. But you certainly could imagine it certainly being accelerated during the progenote era, for example. But it's going on today. I don't know, did I answer your question, or did I just dismiss the premise of the question and so swept it under the rug that way?
No, it's a very fascinating answer. I would say biologists would have a lot to discuss with you.
Say it again?
I would say biologists have a lot to discuss with you about the idea of the central dogma. But I think that is a fascinating way to think about it.
Yeah. No. I mean, it may be broadly true, but there's certainly lots of exceptions to it, and so that's why I say it's not like it really has to happen. It's just the balance of, okay, mostly these things work, but the fact they're not forbidden by any symmetry or any laws of physics or anything like this. So how, fundamentally, I think the main principle of trying to underlie genome stability is essentially reproducibility. In other words, if everything is fluctuating too much, then you're making too many possibilities, and then you're getting generalists, as it were, but no specialists. And so it's really tied up with, whether the organisms are optimized for their particular environment and for where their niches in the ecosystem. So I think these things are balanced like that.
Thank you.
Sure.
So I'm very excited to see you here because I'm also a physicist by training, and I have two questions for you. So first of all, can there be nuclear signatures for life? And second question is, we just can observe 5% of our universe. The rest of the universe is dark energy, dark matter. Can there be dark matter life?
Okay. So the question is, are there nuclear signatures of life? When you say nuclear, what do you mean by that?
At the nuclear level. Like we talk about biosignatures of life. Can there be signatures at the nuclear level?
I don't understand what you mean, sorry.
Like, can there be nuclear physics going on which can lead to life?
Oh, I see. I don't know about nuclear. There's certainly atomic. I mean, there's. I don't really know. I don't know the answer to your question, but I'll give you an example. There is a particular excitation in carbon, the Hoyle excitation, and it's probably the first or maybe only successful application of the anthropic principle, where he guessed that there had to be such an excitation for some process to occur that was essential for life, and indeed it was later discovered to be true. So I don't really know the answer to your question. It's not impossible, because this Hoyle example is a sort of a very strange one. It's obviously something that, if you take a sort of perspective that you should be looking at large scales of systems, you would never think that there would be this kind of thing happening. But we also know in physics that there is scale interference, and that small negligible effects can have large consequences. I have a whole other talk about that in trying to understand the tree-like evolution of life, which I'm not going to talk about. So I don't really know. There was a second question.
Second question was, we can only observe 5% of our universe because the rest of the universe is dark.
Right.
So can there be dark matter?
Can there be dark matter, and can it have life?
Yeah.
Yeah. Why not? I mean, basically, I tend. So, okay, someone is very, very enthusiastically waving at the back. One second. So, hang on. So I think that life is, is essentially an inexorable consequence of the laws of physics. I don't think it's unique or an accident. So yes, that's why I answered that. But I have no scientific reason for answering your question in the affirmative. Yes, please go ahead.
Yes, hello, Professor. I just cannot express how excited I am after your talk. So thank you so much. Actually, I have the similar notion. Whatever you have presented here, I'm literally feeling we share the similar vibe. Actually, I'm the second year PhD student in astronomy, and I have a degree in physics. And I'm sorry, I'm a little nervous, but I have a lot to talk. So. I want to ask I also the Earth-centric investigation of life. It really doesn't convince me to see the life outside the universe, and so I'm really interested to study the physical evolution, how we can study the life outside the universe, and it is true that we should have a generic definition. How should life look like? So that's why I'm very much interested in the thermodynamic evolution of life. So I just want to know, what are your thoughts about, what do you think about, because there are many researchers who are doing great work on that, on the thermodynamic evolution of life. So I just want to know your thoughts on that. And I'm super excited to work on this field. And even I'm in second year, and I have already decided I want my second PhD in biophysics, and I want to study the thermodynamic evolution of life. So yeah, thank you.
Well, thank you very much for your kind words. And now I don't quite understand what is the question that you're asking me, though.
Okay. So yeah, I want to know,
because the microphone is next to you. Yeah.
Yeah. So. There is the third law of thermodynamics.
Third law of thermodynamics, yes.
Yeah, the entropy. So it says every natural laws in the world, they have a particular direction, and it find this is if we think about that, that's itself is a very great It tells every natural process in the world, they have a specific direction. And what I feel what I feel that's my hypothesis, that life is not the most the most probable state of the nature. Nature doesn't want life. That's what I think, and I want to study this with thermodynamic evolution of life. That's why, okay. I want to study that. So I wanted to know your opinion on that.
I think
I'm sorry, I was so long.
I think I can paraphrase your question. So tell me if this is a reasonable paraphrasing of your question. Why does life inexorably become more and more complex? And I think that is a very important foundational question, because you might say, okay, let's suppose you believed in the RNA world, which I actually, as it happens, I don't believe in it. But let's suppose you did. Then you might say, well, okay, so I get these autocatalytic replicators. I have RNA doing all the functions of life. Why isn't the world just knee-deep in self-replicating RNA molecules? Why do we have us and elephants and blue whales and things like this? And so I think the fundamental question is, why do you have this evolution to greater and greater complexity? And I think that's a question that we don't have a good answer for. Now, I'll tell you what happens when we try to model living systems. When we try to model living systems, say in a computer, you make an artificial ecosystem, lots of things interacting with each other, and you run it. And what happens is it does evolve in complexity just a little bit, and then it just stops evolving. It just stays constant, and the simulation does not evolve more and more arbitrarily complex life as time proceeds. So we try to figure out what is the fundamental mechanisms genetic mechanisms that could enable this increase, that give you, as you put it, this directionality of life. And what we discovered was this, and it relates to things I emphasized in the talk. Mostly, when we think about evolution, you read the newspapers, you think about mutations and point mutations and things like this. I don't think those things are very important at all for evolution on the large scale. What we discovered in computer simulations was that there's two things that cause life to inexorably get more and more complex. And that is, first of all, you have horizontal gene transfer. So you have mechanisms that enable essentially an evolving system to really find its local maximum, or local minimum, or optimum. And the other is gene duplication. Gene duplication is very powerful because you make a copy of a gene, and then one copy goes off and carries on doing what it was supposed to be doing. The other one can evolve without deleterious effect on the organism. And when you look in the evolutionary history of life, and you look at genomes, you see throughout this pervasive influence of horizontal gene transfer, certainly in microbial organisms, and gene duplication. And you see gene duplication in all branches of life. So I think what you have to try to understand is the interplay between these different processes at the genetic level then have consequences for the large-scale complexity of organisms. So we built what I think is the first computer model of an evolving ecosystem which has continual growth of complexity due to those particular genetic operators. And it's not a very realistic model, and the model and the method of the way we measured complexity was completely unrealistic. We measured it by the length of the genome as opposed to something like Kolmogorov complexity or some other algorithmic complexity measure. But it does show you that certain genetic processes can give rise, when they interact with the environment, and that was important in our calculation, can give rise to this direction of life, this ever-increasing growth of complexity. So that's the best I can do in answering your question. Is that helpful?
Okay, unfortunately, we've run out of time for questions, so hopefully you can find Nigel at the dinner. But let's thank our speaker one more time. Okay, so I'm sure everyone's pretty hungry and tired at this point. But if we could just get about another 10 minutes or so just to finish up sitting Surfside. But in the meantime, it would be incredibly helpful if people could help move, clear the tables, because we have the event company that needs to get rid of the linens and such. But there's some garbage cans outside the forum, so that'd be helpful. Thank you.